out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to start and learn about fractional numbers. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about fractional numbers. And as we work with these numbers, I want you to keep in mind that any piece of data you work with in your C++ program is ultimately going to be stored in the form of ones and zeros in memory. Fractional numbers are also called floating types in technical terms. They are used to represent numbers with fractional parts in C++ and many other languages. And we have three types that we can use in C++. We have float, double, and long double. And the main difference is in the size they occupy in memory. A float takes 4 bytes, a double takes 8 bytes, and a long double takes 12 bytes typically. So as the size goes up, you can also notice that the precision goes up. So what is the precision? The precision is basically the number of bits you can represent with that type, starting from the number in front of the decimal point. So if we look at this number here, we can try and figure out its precision. So we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The precision here is 12. If we go back to our table, we're really not able to represent a number like this with a float. The smallest thing we can use to represent this number well is a double, because the precision is 15 and it is more than what we need for this number, which is 12. One thing you should remember is that the number in front of the decimal point is also counted in when you are trying to figure out the precision for your floating point numbers in C++. So here we have an example of how we can declare and initialize floating point numbers in our C++ program. Number one is a really huge number, so you can guess that this is more than we can handle with the float. We're going to see how this is handled by our compiler. A double has a precision of 15, so we should expect to store more numbers than we did in a float. A long double should be able to handle this without a problem, because if we go back to our table here, our long double here should be able to handle this better than double, but it is possible that it is the same thing as double, depending on the compiler implementation. And if we try to print out the sizes here, we're going to see what the compiler gives us. We're going to do this when we try this in Visual Studio Code. Okay, and here we are trying to print out the precision of these numbers. We can use a special setting on our stream to control the maximum precision that we can see. Here you see that we are trying to show the precision for each number. There is a special setting we can put on stdc out to make it control the precision to a given number. Here we are using 20, and we're going to see that for number one, this is going to be 7 digits. For number two, it should be 15 digits or something close to that. The specifics are really dependent on the compiler implementation, and for long double, it should at least be the same as double, or even more in some cases. Okay, here we want to see that we can also have narrowing errors if we try to store something big in a float, and a float can't really handle it. Here we have a number with a lot of digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we know that a float can only handle 7 digits. So this is probably going to give us a compiler error, as we've seen for braced initialization. If we use functional initialization, this problem is not going to be code at compile time, so we're going to end up with a chunked piece of data, and we're going to see this when we play with this with Visual Studio Code. And another format we can use with floating points is that we can use scientific notation. And it is basically a way we can use a power of 10 multiplier to multiply with our floating point number. So for example here, number 5 is going to be this number, 192400023. We can use a floating point scientific notation to represent this. So what we're going to do, we're going to say 1.9, and we're going to multiply this with 10 to the power of 8. This is what this means. This E8 here means to multiply with 10 to the power of 8. And if we multiply with that, that basically means moving the decimal point 8 digits to the right. So we can go 1, 2, 3, 4, 5, 6, 7, 8, and it is going to end at these 3 here, and it is going to be basically the same number. Number 7 is also another one, and if we do this, we're going to add with zeros after these 4, and we're going to end up at this same location as the 3, but it is going to be a 0. We're going to see about that in a minute. And number 8 is another floating point number, and we can use scientific notation to represent it, just like you see with number 9. We're basically going to have the same thing. When we have a minus in here, it means we're going to multiply with 10 to the power of minus 11. And this is going to give us a number below 1. Think 0.007 or something like that. So we're going to go 11 digits after the 0 here. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the decimal point is going to go after 3, and we're going to basically end up with the same thing here. We're going to play with this in a minute, and you're going to see that all this makes sense. And don't forget that any piece of data we store in a computer is going to be ultimately represented by ones and zeros in memory. And for floating points, we don't use the number systems like we've done for integers. There is a special system that is used to do that, but it is a little bit complicated to cover in a course like this. I am just going to point you to it if you are interested. And when you are done with this course, you can come up and read on this. The main point is that any piece of data that you represent in your C++ program is going to be represented in terms of ones and zeros in the memory of your computer. Okay, there are a few things you can do with floating points that you can't really do with integers. For example, you can divide with 0. If you take a floating point number and divide that with 0, you're going to get what we call infinity. If the number is positive, you're going to get positive infinity. If the number is negative, you're going to get negative infinity. And you can take two floating point numbers that are zeros and divide them. And what you're going to get really is not a number. It's something called nan, which stands for not a number. And your program is going to not crash, but there are a few things you can't do with these things. For example, you can't add them up. You shouldn't really do this. It's probably going to end up bad for your program. Here we have a few examples. We have 3 numbers declared. They are doubles. They must be occupying 8 bytes in memory. Number 10 is initialized to 5.6. 11 is initialized to 0 because we are using braced initialization and we have nothing in here. And infinity here is the result of dividing a number by 0. So it's going to be positive infinity because number 10 is a positive number. If you go down, we're going to print number 10 divided by number 11, and we're going to say yields. We're going to put the result out. We're going to see that. Down here on the second line, you see that we are trying to add something to infinity, and this is also going to yield infinity, because think of infinity as something super big. And if you add something small to something big, it's still going to be something big. Down here, you see that result equals number 11 divided by number 12, and these two are zeros, so we're going to end up with none, and that's what we're going to print in this statement here, down to the bottom. Okay, you should really remember to put in the suffixes when you are initializing your floating point numbers. Otherwise, the default is going to be double. This is what we mean by this. You see this floating number, we have a suffix that is f to mean that it is a floating number. If you don't put that in, this is going to be interpreted as double, and the compiler is going to try and turn that into a float by chopping off things that can't really fit in a float. So to really make it clear that you are storing in a floating number, please put this f suffix here. For double, you don't need to put anything because it is the default assumed by the compiler, but for long double, you have to suffix this with l, just like this. So that's what we really mean here. We have seen that the precision for float isn't really enough for many of the computations we might want to do in our C++ applications. Okay, we have talked a lot about floating point numbers. Let's head to Visual Studio Code and actually play with them. Okay, here we are in our folder that is going to contain our project. The project is going to be called fractional numbers. So we're going to copy our files, go up a little bit, and put those in, and we're going to go up again and open this in Visual Studio Code. We're going to close whatever it is we have opened now. We're going to close folder, and we're going to open our project in Visual Studio Code. And we're going to do the usual and remove things we don't need in here. The first thing we want to do is to store a few floats in our program. We're going to declare and initialize a few floating point numbers. We have number 1, number 2, and number 3, and we want to make it clear that the sizes are what we expect. We are going to open a terminal window here, and we're going to build with GCC, run the task to build with GCC. The build is going to be successful. We're going to come to our terminal, click a little bit, and we're going to type dir. We're going to see that our program is in place. If we run it, we are going to see that size of float is 4, size of double is 8, and size of long double is 16. This is what we expected. Another thing we can do is try and play with the precision of these numbers and see what we can really go away with. Okay, so we're going to actually put in a piece of code to play with this. We're going to add a setting to our SDDC out stream so that we can control the precision. But for this to work, we need to bring in a library that is called IOmanip. So we're going to include that. IOmanip. And how do I know this? I usually consult the C++ standard library documentation, and you are not at a point where you can really understand it right now. So we're going to be putting in these things here and explaining them as we go. And I made a typo here. It is IOmanip, and you see that now this is recognized. Our program should compile. So we're going to try and build it so that we can try this out. We're going to build with GCC. The build is going to go through. We can run our program. We're going to do dir and clear and rooster to run. You see that things start to go off at 6. And if we count what we have here, it is 1, 2, 3, 4, 5, 6, 7. We can only represent 7 numbers accurately with a float. And after that, we're just going to have garbage because the computer can't really make sense of whatever we have after our 7 digits that we can legally represent with a float. So the precision for our floating point number here is 7. I really hope this makes sense. Let's check out number 2. We are using double, so precision should be around something like 15. So we are putting in a number 1 through 9, and we are starting over 0, 1, 2, 3, 4, 5 up to 0 again. If we look at what we have in the output here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, and here things start falling off after our 6 here. And if we count, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. This is the precision we are having this compiler for double, 17. So it is something around 15, and we should expect to have something more than that, or at least the same thing as double with long double. So if we look at this, you see that it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are able to represent up to 20, and you can see that long double lives up to even the precision of 20. 20 that we have set with std set precision here. Okay, I really hope now that you have an idea about these precisions we have with our floating point types in C++ programs. Another thing I want you to see is what kind of narrowing errors we can get if we try to initialize with something that can't really be represented by a floating point number. And here we have a float, it is called number 4, and we are trying to put in something that is bigger than we can really fit in. It has more than 7 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It is more than 7 digits, and we would expect to have a problem with us because we are using braced initialization. Let's try and build this with GCC. We're going to do that, and this is going to build successfully. So this is going to silently chop off our number. If we try to print it out, we're going to say stdc out number 4, and we're going to build again, run the test to build so that our changes are taken into effect. We're going to do dir and do rooster, and this is going to print our number. You're going to see that after the zeros, we have junk. Our number has been basically chopped off, and this is junk because we can't really represent this with the double. The 16 here has been chopped off because we can't basically represent this with the floating point number. If we change this to double, this is going to probably give us what we expect. So let's run again. Build with GCC. The build is going to be good. If we run the program, it is going to show us the same thing. Okay, this is a really good learning change. Why are we having the same results as before, even if we changed the type to double? Try to think about it. The reason is the suffix here is still saying F. And this is going to be stored as float in memory. So if we want this to really be treated like a double, we can take out the float here. And if we build again and run the application, now you're going to see that we see the 23. This is basically being correctly stored as a double. This is a really good thing you should keep in mind. If you don't put in your suffixes here, the number is going to be interpreted as double. By now, I hope you see that if you really try to put more than your floating point can handle, the number is going to be chopped off, and only the precision that it can handle is going to be stored in. I hope this makes sense. And you see that the behavior for numbers is really different. We got a compiler error when we try to do narrowing conversion with integers, but now it is silently chopping off our number. If we try and use functional notation, I think we're going to get the same result, and change this back to a float and use float here. And if we build again, let's go to terminal, run a task, use GCC. We're going to run this. Let's run rooster, and you see that we get the same results. Our 23 is chopped off here. We can also use the assignment notation here, just like we did with integers, and this is going to do exactly the same thing. It is going to chop off the 23 here, and we're going to have some garbage, which is 16 in this case. If we build again, the build is going to go through, and if we run, we're going to see a 16 here. Okay, narrowing conversions are something you should be aware of when storing your floating point numbers, and you should really remember to put in your suffixes here. Another thing we have seen that we should really play with is scientific notation. As the comment here says, what we have seen so far in floating point numbers is fixed notation. It is what we have here, but we can also use scientific notation, which is exactly what we described in the slides. And what we have here, for example, is E8, and it means that we are going to multiply this number here with 10 to the power of 8. If you go down here, we have number 9, so we have 3.498, and we have E minus 11. And what this is going to do is multiply with 10 to the power of minus 11. This is how I can represent this here. And we can print these numbers out to really play with them. To make a difference with what we have been doing before, we're going to do stdc out and put a dividing line here. This is one way we can do this. So we're going to do stdendl. We're going to build this. So we're going to run the task to build with gcc10. The build is going to go through. If we do rooster, we're going to see that our number here, number 5 is what we expect. Number 6 is the same thing, but we used scientific notation to do this, because we took this number and multiplied by 10 to the power of 8. Number 7 should be almost the same thing, but the lower 23 here is going to be chopped off because we haven't specified it. We're just multiplying with 10 to the power of 8, so that's why we have 0, 0 here. I hope that makes sense. And if you look at number 8, you see that we stored it like this without using scientific notation. We used fixed notation. But on the terminal, it's going to be printed out in scientific notation, and this may be pretty cool. The main usage for scientific notation is to make sense of numbers that are really huge. So the way you interpret this, you're going to move these numbers after the decimal points with 0 in front, and it's basically going to be like this. So if you count the zeros you have here, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is going to be directly after 3, and you're going to get the number here. This is what we mean. And number 9 was explicitly stored in using scientific notation, and you see that we have the same thing. You can play with these things and really make sense of them. And again, we didn't specify any suffix here, so these are going to be interpreted as doubles, but this is not a problem because they are doubles here. Okay, we are making some progress with this lecture, which is a little lengthy. The last thing we want to do is to play with infinity and nan. We're going to put a message here to say what we want to do, and we're going to have number 10, which is going to be positive. We're going to have number 11, which is going to be 0. Number 12 is also going to be 0. If we take 10 and divide that with 11, we're going to get infinity because we are dividing a floating number with 0. If we try to print that out, we're going to get infinity, and we're going to get infinity for this result here because we are trying to add something small to infinity, which is something really big. And if we are trying to divide 0 with 0 in floating point, we're going to get what is called not a number. And if we print that out, we're going to see this in a minute. Let's build this with GCC. We're going to build successfully. Let's clear this out so that we don't have noise in here. and we're going to run rooster. And you see here it says infinity and none, which is what we said here. And if you go down here, it is saying number 10 divided by number 11, and number 11 is 0. You see that here, it's going to yield infinity. If we add 5 to infinity, we're going to get infinity. And if we try to divide a 0 by a 0, we're going to get none, which is really a way to tell you that you're doing something wrong. You should really be careful. One other thing I want you to see is that if you turn this 5 into a -5 and build again, we're going to build with GCC, and we're going to run this rooster. We're going to get minus infinity. So if you divide a positive number with 0, you're going to get positive infinity. And if you divide a negative number with infinity, you're going to get negative infinity. And this is what we see here. This is really all we set out to do in this lecture. I hope you found it interesting. And again, the big message is that any data type you're going to be handling in your C++ program is going to ultimately be stored as ones and zeros in memory. And we have learned about floating point numbers, float, double, and long, and they have these properties you see here, and you should use them with this in mind. Otherwise, you're going to have problems with your precision. Make sure you are using the correct precision that you need in your program. We are going to stop here in this lecture. The next one, we're going to try and learn about Booleans. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about Booleans. Booleans are types that can store two states in C++. It can store either true or false. And we can use this to really do decisions in our program. If you look in the program we have here, we have two variables declared. The data type is bool, and one is called red light, the other is called green light. And we have true and false inside. One thing we can do in C++ is make decisions. We can say if the red light is true, we can print a message that says stop. And if it's not red, we can print a message that says go through. We can do that. And Booleans are really used in this way to make decisions in your C++ program. We haven't really learned about if statements in this course, but I am throwing this in here to really drive the point home that we can use this to make decisions in our program. Down here, we have another way we can do this. We can actually use the variable itself without checking if it is equal to true or false, and we are going to get the same message. The point here is that if green light is true, we're going to say the light is green. If it's not, we're going to say the light is not green. You can do something like this. And again, the big point here is that Booleans data types are used to store two states, true or false, in your C++ program. Okay, by default, if you print a Boolean that has true in it, you're going to get true, and this is what you see here. And if you print one that has 0 in it, you're going to get false. We can change that with a special setting that we can apply to our std out stream, and you do that like this with std bool alpha, and we're going to play with this in a minute. You're going to see if we try to print with this setting applied, we're going to see true and false and not see 0 and 1 like we did before. We're going to play with this in a minute, and you're going to see. Another thing you should know is that Booleans occupy 8 bits in memory. They take up an entire byte. So you may think that this is wasteful, and it is, but with the amount of memory that we have today, this is really not a big problem. But if you are working on a device where memory is really a problem, there are techniques you can use to pack even more data in a byte, and we're going to learn about that later in the course. Okay, so this is really all I have to say about Booleans. We're going to go to Visual Studio Code and play with them in code. Okay, here I am in the folder for my project here. I am going to do the usual and copy the files over, and I am going to go in my project on Booleans. I am going to go up and open this up in Visual Studio Code. I am going to close the current folder, open the new one, and browse to my project. This is going to open up in Visual Studio Code, and I am going to close the welcome screen here. Chop off our number. If we try to print it out, we're going to say std cout number 4 and booster, and back to a float to run. So we took this number and we're going to be chopping IR. We're going to see rooster away, and we like put add on Booleans and project. This is going to open up in Visual Studio Code, and I am going to close the welcome screen here. I don't need it anymore. So I'm going to remove what I don't need, and we are going to play with the exact code that we had in the slides. We're going to declare two variables. One is going to be red light, the other is going to be green light. They are going to be Booleans. And in red light, we're going to store a true and store a false in green light. And we can make a decision like this. So try to guess what we're going to print in this program. We're going to try and decide and say if the red light is true, we're going to print stop. If it's not true, we're going to fall in this block here and say go through. If we look at our program, in red light we have a true, so this should really win, and we should get in this block here. I hope this makes sense. So let's try and build this program to see that it actually works. So we're going to build with GCC, we're going to run our program, and our terminal just went away. We're going to create a new one, no big deal. And if we do dir, we're going to see rooster.exe, we run it, it's going to say stop. Okay, so in red light we have true. The test is going to succeed here, and we're going to fall in this block and say stop. I hope this makes sense. You can try to store a false in here, and build again. We're going to build with GCC. If we run this program now, it's going to say go through because red light is not true anymore. This is really what we mean when we say that we can make decisions based on Booleans in our C++ code. We can also try another example. We're going to say if green light is true, we're going to say the light is green. If it's not, we're going to say the light is not green. And this is another form we can use instead of typing the entire thing, comparing red light to true here. And again, we're going to learn about all these comparisons here. It is just because I thought that talking about bools without showing tests like this is really not going to drive the point home for you. So try to understand this as simple tests you can do in math. If one value is true, I am going to do something. If it's not true, I'm going to do something else. This is what we are doing here. Okay, this program here is going to check if the green light is true. So we're going to look here, green light is not true. So we should fall here and print this message that the light is not green. Let's build the program. The build is going to go through. We're going to run this. And you're going to see go through and the light is not green. This is what we have here. Another thing we can actually try to see is the amount of memory that a boolean takes up. So we can use size of to do that. We have seen this before. If we build with GCC, we're going to go through and we can run our program to actually this message. And you're going to see that bool is actually going to take up 1 byte in memory. This is what we saw in the slides. Another thing that can be really confusing is printing out boolean values. For example, here we are trying to print red light and green light. Let's go up and actually change them a little bit. For example, take green light here and make it true. And we're going to go down again, and here we are trying to print them out. Red light is going to print whatever value we have stored in, and green light is going to store whatever value we have stored in. And again, true is going to be printed out as 1, and false is going to be printed out as a 0. Let's try and build this. We're going to build with our GCC compiler. The build is going to be good. We're going to run this, and you're going to see that red light is 0 because we have a false in here, and green light is going to be 1 because we have a true here. If you try to print out Boolean variables, you're going to get 1 and 0 by default. If you really want to see true and false, there is a special setting you can apply to stdc out, and you do that by saying stdc out std bool alpha, and you do it like this. And if you try to print again, we are going to get true and false right now. Okay, let's try and print again, and we're going to build this with GCC, and we're going to run this, and now you see that we see red light is false, green light is true. This is really all I had to share about booleans in this lecture. Red light is false, green light is true. This is really all I had to share about booleans in this lecture. I really hope it drives the point home that booleans are mostly used in making decisions in your program, and that's what you're going to be mostly using them for. And another thing is that they take up 1 byte in your memory. We are going to stop here in this lecture. The next one we're going to try and learn about characters and text. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about characters and text. And we use a data type called char in C++ to represent characters. And this is basically how you use it. You store in characters like A, B, C. In here you see that we have A, R, R, O, W. And you put your characters in single quotes like this to mean that they are characters. If you don't do that, you're going to get a compiler error. After you have your characters declared and defined like this, you can print them out with stdc out, and we're going to see them on the terminal. Char occupies 1 byte in memory, so it's going to take up 8 bits. Okay, so one thing we can do is map each value in these 256 possible values to a character. And we can do something like this. For example, we can say that 33 represents the exclamation mark, 48 represents the character 0, 49 represents the character 1, 50 represents the character 2, and we can keep going up and say, for example, 70 represents F, 71 represents G, or 112 represents P. You can really use a mapping like this and come up with representations of your characters in memory. And this is what we do. You can learn about this encoding on the link here. This is a real thing, and it is called the ASCII encoding that takes characters and stores them in 1 byte, and the data type to store these characters in C++ is char. If this doesn't make sense, please bear with me. We're going to play with this in Visual Studio Code, and it is most probably going to make sense. Okay, it is possible to assign a valid ASCII code to a char variable, and the corresponding character will be stored in that piece of memory. So once you have that, you can choose to interpret that either as a character or as a number, that is something like an integer. This is what we really mean if we declare a variable called value, which is of char type. A 65 is going to be stored in memory, but the C++ program is going to interpret this as a character. If we go back to our table and see what is represented by 65, this is what we're going to find. We're going to find that 65 represents A. And if we print this out, by default, it's going to print A. It's not going to print 65. But there is a way you can take this character value and turn that into an integer and print it out. And you see that here. We are saying value int, and we are saying static cast int, and in the parent we have a value. This is basically a way to say we wanted to take the value and interpret that as an integer. And we're going to learn a little more about static cast later in the course, but it is basically a way to transform between data types. And in this case, we are trying to transform from char to int. And we're going going to print this out. Okay, what we just described is the ASCII encoding, a technique by which we can map the first 128 numbers in a byte to characters and use that to represent characters. This technique doesn't work well if you have languages like Arabic, Japanese, and Chinese because they are completely different beasts. There are better ways to represent characters in your C++ program, and that's usually Unicode, but that's really out of scope for a course like this, so I'm not going to describe that anymore. Okay, this is really all we need to learn about characters. We're going to head to Visual Studio Code and play with them. Okay, here I am in my working folder. I am going to go in my template project. I am going to copy things over. I am going to put that in my characters and text project. And I am going to go up and open this up in Visual Studio Code. We're going to close the welcome screen here. We're going to open up main CPP, and we're going to put in the code to play with characters and text. The first thing we can do is declare characters like this. We can put in ARROW here, and we're going to see this printed out if we run this program. We are going to put in some code to play with characters. We have a few variables declared that are of char type. We go from character 1 through character 5, and these are the characters we are storing in. This is the format you're really going to use to declare your characters.
All right, so we wanted to answer the question once and for all, what is the best smartphone camera out right now? Maybe you think it's the iPhone, or maybe it's a Samsung flagship, or maybe it's one of those Pixels. Now, in years past, we've done a blind voting using social media polls, which was really fun and yielded some surprising results, but that would still depend on the matchups that I planted at the very beginning. So I specifically put the iPhone and the Pixel on opposite sides of the bracket, expecting the best ones to hopefully meet in the finals. But they never did, and there's always a bit of human input. It's actually possible I could have accidentally put the second best phone up against the best phone in the first round, and it got eliminated. So this time, we're gonna solve all that once and for all. Welcome to the Blind Smartphone Camera Test, Scientific Edition. So, here's the idea. We took 16 smartphones that came out during this year, the flagships, your expected heavy hitters, but then also some mid-rangers as well, all the way down to the unexpected, and then we took the same exact photo with each one of them. Harder than it sounds because you have to hold perfectly still for several minutes straight, but we actually did this for 3 different types of photos: a standard daylight photo, a low light photo, and a portrait mode snap. And then we take all these images, compress them, strip them of their EXIF data, and assign each one a letter. Now, for maximum statistical confidence, we would have to ask you guys to vote on every single possible matchup at least once. So A versus B, then A versus C, then A versus D, all the way through, and then B versus C, B versus D, over and over, 16 choose 2 for my stat heads. But that's clearly a bit too much. I mean, we want to be scientific, but having you sit there and vote over 100 times for each category was a bit of a tall ask. So instead, we got a little clever with it, and we built a power ranking system. Actually, an ELO rating algorithm, which you might have heard of. They use this in chess, they use this in table tennis, and basically in any video game you've played where there's a bunch of different matchups all happening at once and you need to form a ranking of them. But this time we'll be using it to sort of form a power ranking of smartphone cameras. So basically when you hit enough sanctioned matchups, you're given a rating based on the ratings of your matchups. So you, along with everybody else, get shown comparisons at random, and we have this little progress bar along the bottom. You vote for the better photo each time, and then after a little while, we have enough information to determine your individual customized, statistically significant winner. So we built this whole site with the ELO rating system in there. We loaded up all the photos, and then we actually tossed this first into our Discord to have some of you beta test this before anyone else knew it existed, so we could experiment with the data formatting on the out end so we could make sure it was all organized. So actually, shout out to Discord for sponsoring this portion of today's video. So with the launch of their new server subscription feature, we opened up an exclusive premium area on our Discord server where members can ask the team, including me, general questions about tech or any of the content, and get exclusive insider info that you won't find anywhere else, like this. And check out voted, and basically we got the data back in this text format. It looks kind of messy at first, but actually it's super helpful and we can work with this. A summary of how many times every single matchup got voted on and the votes for each side. And also, since I had a lot of help with building this site and loading up all the pictures, even though I know which phones were involved, I don't know which phones took which pictures, so I could blind test myself. And it was every bit as engaging as I was hoping. I could kind of tell some of the phones that I think took certain pictures, but for the most part, I would just take a glance, and if I was seeing those 2 pictures side by side on like Instagram or Twitter, I'm just picking the better one. No pixel peeping or thorough inspection. It's just picture, on the internet, vote. And in the end, My standard picture winner was G, my low light winner was K, and my portrait mode winner was also K. So everything looked like it was working. The data processing was working as we wanted. So the only thing left to do was send it live. And here we go. So as soon as it went public, you guys jumped right on it. It peaked at around 35,000 votes per minute, and it ended up totaling more than 21 million votes in about 3 days. There were essentially 0 bad actors, and now we have a load of data. Many of you may have gone through this, which means you've done the voting and now you have your letter, which means it's time to reveal all of the smartphones that were involved in this test. And here you go. A through P. That's all 16 phones right there in their orders, which means the winner when I blind took the test myself for my standard photo was the Pixel 6a. My winner for portrait mode and night mode was the Pixel 7. But what were the overall winners according to statistics?
After we have them declared, we can print them out like we print any other variable, and we can try and compile this program and see what we're going to get. But before we do that, I would invite you to try and guess. So let's open our terminal, and we're going to build with our GCC task. We're going to build, the build is going to go through, and if we run Rooster, we're going to see that we are printing out ARROW. We are storing our characters in, and we are able to print them out. This is really how you work with these guys. Another thing I want you to see is the size that a character occupies in memory. By that I mean card type. It's going to occupy 1 byte in memory, and that means that we can only have 256 different values that go between 0 and 255 if we have decided to store in positive numbers. We are using the knowledge we learned from the integers lecture. If these calculations we are doing here don't make sense, please go back and check that out. So down here we are declaring a character type, the name is value, and we are putting in a 65. The thing is, if you try to print this value here, it's not going to print 65. It's going to print A, which is a character representation of 65. If you remember from our ASCII table, we had these mappings between characters and integers, and 65 mapped to the character A uppercase. So if we print this out, this is going to give us A, but we have the option to interpret this as a number, and we can cast this through a static cast, and it is going to take value, turn this into an integer, and we're going to be printing this integer on the console, and we're going to see it. We're going to try this out, so we're going to run the task to build with GCC. The build is going to go through, we're going to run Rooster, and you're going to see that value is A for the first line here, and the value int is 65 because we decided to interpret whatever is in this value as an integer and not as a character as it is done by default. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to try and learn about the auto keyword in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the auto keyword in C++. This is a keyword that is going to let the compiler deduce the type for you. And this is going to come in handy when you have longer type names that are really hard to type. We can't really give you an example of that because that requires to have a good number of concepts mastered in C++, but we are mentioning this here for completeness because we are talking about variables and data types. So let's see how we can use this. Here we have an example where we are saying auto var1, and what we initialize this with is an integer, so the compiler is really going to try and guess the type of this thing, and that's the type it's going to assign to variable 1. This is what auto is really used for. If we pass a double inside, and it is a double because we have no suffix here, so it is going to deduce a double. If we pass a suffix of f, it is going to interpret this as a float. If we pass l, it is going to interpret this as long double. And if we pass in a character, it's going to interpret this as a character. And this is really the essence of what auto is used for. It is used when you don't really want to explicitly type the type of your variable, and you want the compiler to fill in that for you or guess it for you. Down here, you see that we have a few examples with integers, so we can make this unsigned long through these suffixes, and the compiler is going to deduce the type based on what we pass in our initializer here. Down here, you see that we have a few examples with integers. If we pass a suffix of u, this means that we are storing in an unsigned integer, so that's what the compiler is going to deduce. If we pass ul, it is going to be unsigned long. If we pass in ll, this is going to be long long, and that's what the compiler is going to deduce. Here you see that we are trying to print the sizes of these variables, and we trying to prove to ourselves that the compiler deduced the right type. And we are going to go to Visual Studio Code and actually try this out. Okay, here I am in my working folder. I am going to open my template project. I'm going to copy that, and I'm going to save my files in the auto project here. So I am going to go in and put in my files. I'm going to go up again, and I am going to close whatever it is I have in Visual Studio Code because we're going to create a new project. I am going to open my new folder. We're going to close the welcome screen here, and we're going to remove whatever it is we don't need for this project. And we are going to put in the code we basically had in the slides. I am pasting this code in to save on some time because I don't want you to see me type these things. We're going to save some seconds here. So the first statement here declares a variable var1 The type we don't really know, but we're going to let the compiler deduce that for us. And we can try and actually hover over this. And we're going to see that the compiler already deduced that this is an integer. If we go to var2, this is a double. If we go to var3, you see it's a float. If you go to var4, it's long double. If you go to var5, it's a character. You can see that Visual Studio Code can even see what the compiler is going to deduce before we even compile the code. This is the beauty of Visual Studio Code. We're going to look at var6. You're going to see that it's going to be unsigned int. If we go to var7, it's going to be unsigned long. If we go to var8, it's going to be long. This is really cool, and you can see that our types are correctly deduced. Visual Studio Code was really helpful in showing us these types, but we want to be sure by running this piece of code and seeing whatever size the deduced type is. For example, for var1, we guessed that it's going to deduce an int, so it better be a 4 in size. We're going to try and run this. We're going to open our terminal here, and we're going to go to terminal and run task. We're going to build with GCC. And by the way, if you want, you can build with the compiler from Microsoft by coming to terminal here and choose it with build with MSVC. But GCC is my favorite compiler, and I am going to use it if I can. So we're going to hit enter, and we're going to see that our rooster.exe file is in place. If we run it, we're going to see our sizes. So var1 occupies 4 bytes in memory. var2 occupies 8 bytes in memory because it is double. var3 occupies 3 bytes because it is a float. var4 occupies 16 bytes because it is a long double. And var5 better occupy 1 byte because it is a character. And we see the same data for var6, var7, and var8. And this proves that the auto keyword is really doing its job. It is deducing the types for our variables without us explicitly specifying the variable type. We didn't have to do something like int or double or whatever. We can let the compiler do that for us. And this will come in handy many times. This is really all we set out to do in this lecture, and I hope you found it interesting. In the next one, we're going to look at how we can do assignments and assign data to our variables in a unified way. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about assignments. And the basic idea I really want to drive home here is that after a variable is initialized, like we've been doing all along, you can later assign a new value to it. For example, here we have var1 declared. It is an integer. We can print it out, and it is going to print 1, 2, 3. But later in the program, we can put in another value. For example, here we are putting in a 55, and if we print var1, it's going to be 55 this time. The same idea can be extended to doubles. You see here we are doing the same thing. Booleans, we are doing the same thing here. The state is declared false, and we are printing that. And after we are changing this to a true value, and if we print that, it's going to be true. One thing you really need to be careful about is if you are doing auto type deduction, the type is not very apparent by looking at the declaration of the variable here. For example, here, by looking at auto var3, we don't really know what that is. And it is very easy to try and put in a value that is illegal. For example, here, we have deduced an unsigned integer, which is only going to store positive numbers, but we are putting in a -22, and this is going to be a disaster. We're going to get a compiler error, and this is going to be bad. So be careful when you are doing auto type deduction in your assignments that you do to your variables. This is really all we have to share in this lecture. Let's hop over to Visual Studio and show you this in action. Okay, here I am in my working folder. The project we're going to be working on is 49 here, assignments. I am going to grab my template files and put that in this folder here. And I am going to open this up in Visual Studio Code. So let's close whatever it is we have now and open the folder. And we're going to close the welcome screen here. We don't want it, and remove whatever we don't want from this file here. The first thing we want to do is put in the code for our integer variable var1 and show you that you can assign a new value to it after it was initialized. And if we run this code, we're going to see var1 to be 1, 2, 3, and the second statement is going to say var1 equals 55. That's what we're going to see. Let's bring up our terminal, and we are going to run the task to build with GCC. And if we hop over here in the terminal and do dir, we're going to see that our rooster.exe file is in here. If we run it, we're going to see var1, 1, 2, 3, var1, 55, exactly what we expect. We have stored in a 1, 2, 3 at initialization using braced initialization here, but after, later on in our program, we have decided to put a different value in this variable here, essentially reusing it to store something else. This is the basic idea here. We can do the same things with doubles, but before we do that, let's put in a separation line so that we can see these things clearly in the terminal. And we're going to go down and put in our code for a double. So we have a double variable called var2. Initially, it has 44.55 in, and then we're going to assign a new value to it, and that's going to be 99.99. If we print that out, we're going to see that. Let's build and see this in action. We're going to build with GCC. If we run the program now, it's going to say var1 is 1, 2, 3, var1, 55, but we're also going to see that var2 starts out 44.55, but after we put in the 99.99, it's going to show up here. Okay, let's put in another separation line, because we're going to need that in a minute. We can do the same things with booleans. Clearly, R2, initially it has 44. .55 in, and then we're going to assign a new value to it, and that's going to be 99.99. If we print that out, we're going to see that. Let's build and see this in action. We're going to build with GCC. If we run the program now, it's going to say var1 is 123, var1 55, but we're also going to see that var2 starts out 44.55, but after we put in the 99.99, it's going to show up here. Okay, let's put in another separation line because we're going to need that in a minute. We can do the same things with booleans. Here, we are using this as just an example, but this same concept essentially extends to any other kind of variable you're going to have in your C++ code. If you initialize it with some value, you have the option to change that value later on in your program by assigning that value to that variable. Essentially what we are doing here. The variable state, which is a bool, was initialized to false. We're going to print that out, and notice that we have this setting to allow us to see true or false instead of ones and zeros. We have seen this in a few lectures back. And later on, we are assigning true to this state, and we are printing that. So if we print these things out, we're going to see false and true for the state here. So let's build. We're going to use GCC, and the build is good. If we run the program, we're going to see false and true, and it is exactly what we expect. Again, you really need to be careful when you are using auto-type deduction, because you might have some serious problems if you are not paying attention. Let's put in the code so that we can play with it. Here we have a variable called var3, and the type of it is not specified explicitly. We are letting the compiler deduce this. And because our initializer here is an unsigned integer, the compiler is going to deduce that it is an unsigned integer. The problem will come if you try to store in a negative number. The compiler is not going to give you a compiler error. It is going to silently put in some garbage value that we don't really want in there. We want a -22, and you can see that this is what the compiler is turning our value into. We want a -22 in this var3, but if you hover over this minus sign here in Visual Studio Code, you're going to see that the value that we have in is not what we put in. We put in a -22, and we are getting a really large number, close to 4 billion. So this is really something that can go silently wrong in your code, and you're going to have a hard time trying to figure out why your code is not doing whatever it is you want. So be careful about this. Let's try and build this. So we're going to build with GCC. The build is going to be good. You're going to see that we're not even going to get a compiler error. If we run this, and we're going to see that var3 is exactly what Visual Studio Code guessed. And it is not good. It is this value here. And the problem is that the compiler is silently putting in a garbage value and not what we want here, because var3 is basically not capable of storing negative numbers. So the compiler is going to do its best and put in a garbage value. And this is not what you want. And you need to be aware of this. This is really all we set out to do in this lecture. I hope you know about assignments, and be careful when you are doing assignments on variables whose types are deduced with auto. And we're going to stop here in this lecture. In the next one, we're going to try and recap what we saw in this chapter. Go ahead and finish up here and meet me there. In this lecture, we're going to recap what we saw in this chapter. And this chapter was really all about variables and data types. We had a chance to look at different types that we can use in C++. We saw that we have fundamental types we can use to represent integers, floating points, booleans, and we also saw that we can do type deduction with auto. We had a chance to make it clear that data is represented in memory as zeros and ones, and that there are some kinds of transformations we do on these pieces of data to turn them into a form that is easily usable and manipulable by humans. And we saw that for integral types or integers, we could do that through number systems, and we had a chance to look at a few number systems like binary, octal, and hexadecimal, and we had a chance to play with all these variable types in Visual Studio Code and see the nuances of how you really work with them. I would like to welcome you in this new chapter. In this one, we're going to be looking at operations we can do on our data. And there is a bunch of them. We can add things up, we can subtract numbers, we can divide numbers. We're going to see all kinds of crazy operations we can do on the data, all the variables that we have in our C++ program. We are also going to have a chance to look at how we can format stuff when we print them out to stdcout. And we are going to be using some utilities from the C++ standard library to do some operations on our variables. This is going to be a fun chapter. I can't wait to get started. Let's go in the next lecture and start doing this. In this lecture, we're going to be looking at some basic operations you can do on the data in your C++ program. And we are going to be specifically looking at addition, subtraction, dividing numbers, the modulus operator, and multiplying stuff. We have seen addition before. Here we have a simple example. We have a variable called sum, and we are initializing it with two numbers that we are adding up, number 1 and number 2. This is something you can do in your C++ program. You can also do some other things. For example, we have another one called other sum, and we are adding up some other numbers, and we are going to collect the result into this other sum variable, and we're going to print these things out so that you can see them on your command prompt. This is how you can do addition, and we're going to have a chance to play with this in Visual Studio Code in a minute. We can also do subtraction. We can take a number and do minus another number like we are doing here. We're going to store the result in this diff variable, and we can do some other things. And down here you see another example in other diff here. We're going to subtract numbers and store the result in other diff, and we are also going to print this out. You can also multiply stuff. This is how you can do this. You use this operator here. It is the star operator, and this is an operator that many programming languages use to do multiplication. You should get familiar with this. And again, we print out the result so that you can see that this is actually working. We can also do division. Division for integers is a little tricky if you are seeing this for the first time. If we take, for example, 31 and divide that by 10, we're not going to get fractional numbers. C++ is going to try and figure out how many times it can fit 10 in 31, and we are visualizing this here. So in 31, we can only fit 10 3 times, so the result of 31 is going to be 3. This is the meaning here. Okay, with integer division, you're not going to be getting fractional numbers. This is something you should really understand. We have another operator that is called modulus operator, and this operator is represented by this percentage symbol that we are doing here, and the result of this operation here is going to be what remains after you have done the division of 31 and 10. And here the result is going to be 1, and you might be wondering why this is useful. It is going to be useful in many applications, and I think we're going to have a chance to play with this later in the course, but right now you just need to be aware of this operation and what it does. Okay, these are the operations we're going to be learning about and playing with in this lecture. Let's head to Visual Studio Code and actually play with this. Okay, here we are in our working folder for this chapter. You see that I have prepared all the lectures we're going to do in this chapter, and I have my C++ 20 template project in place. I am going to do what we have been doing all along. So I am going to take these files and put them in the current lecture, which is basic operations, and I am going to paste those in, and I am going to open this folder in Visual Studio Code. So let's do that pretty quick. We are going to close the welcome screen here, and we're going to open our main CPP file, and we're going to remove things we don't need here. The first thing we want to play with is addition, so we're going to say that, and we're going to declare two int variables. We're going to call this number 1, and we're going to put in a 2, for example, and we're going to do a number 2, and we're going to put in a 7. Why not? And what we can do, we can say result equals number 1 plus number 2, and we're going to store the result of this operation in the result variable here. So what we can do is say stdc out, and we're going to print the result. We can try and compile this and see the result. Let's open our terminal here, and we're going to build with GCC as we always do. The build is going to go through, and if we run rooster here, we're going to see that the result of our operation is 9. So this is how you can do addition. You can also do subtraction, and here we need to declare a new variable. We're going to store the result in our result variable here. So what we're going to do here is say subtraction, and we're going to say result equals, for example, let's take number 2 minus number 1. This is the operation we want to do. This is number 2. What we are going to be storing in this result here is going to be a 5 because we are taking 7 and subtracting 2. I hope this makes sense. So if we grab this line here and paste it in here so that we save on some typing time, and try to build again, we're going to run the build task with GCC, and we're going to run rooster again. It is going to say result is 5 because we are taking 7 minus 2 here. The result is going to be 5. We can also do a subtraction operation that is going to result in a negative number. So for example, we can say result equals number 1 minus number 2, and this is going to give us a negative number because 2 minus 7 is going to be minus 5. So we're going to print that here. I'm going to paste this in because I still have this on my clipboard. If I build with GCC and run my program, we're going to get minus 5 as a result of this operation here. This is how you can do subtraction. We can also do multiplication, so let's go down here and say that, and we're going to say result equals number 1 multiplied by number 5 as a result of this operation here. This is how you can do subtraction. We can also do multiplication, so let's go down here and say that, and we're going to say result equals number 1 multiplied by number 2, and this is the operator we use to do multiplication in programming languages. We're going to put in our print statement here, and we're going to build with GCC, and if we run rooster now, we're going to get 14 because we are taking 2 and multiplying that with 7. This is how you can do multiplication. So what happens if you take 7 and divide that with 2? Try to give this a guess based on what we saw in the slides. we're going to go down here and do division, and we're going to say result equals number 2 divided by number 1, and we're going to try and print this out. If we build this, the build is going to go through, and if we run this, we're going to see that result is 3. So to really make sense of this, let's look at these numbers. We are taking number 2 and dividing that with number 1. So it is 7 divided by 2. And because we can't store fractional numbers in an integer, the fractional part is going to be basically chopped off, and we're going to store a 3 because 2 can fit in 7 only 3 times. I really hope this makes sense. The last operation we're going to look at is modulus, and it is a way to capture the remainder of a division operation. So we're going to do result to play with this. And we're going to say number 2, and we're going to say modulus using the percentage operator here, and we're going to say number 1, and we're going to print the results of this, and take a look at this here and try to guess what we're going to be doing. What we're doing here is really 7 modulus 2, and we're going to take 7, divide this by 2, and the remainder of that is going to be 1, and that's what we're going to store in this result variable here, and if we print that, we expect to get a 1 here. This is what modulus does. Let's build, and build with GCC. The build is going to go through. If we run rooster here, we're going to get a 1. Let's do what we used in the slide so that this really makes sense. We're going to go down here and do equals 31 modulus 10. This is what we used in the slides. So we're going to print the result here. And here we are really asking what is going to be the remainder if we take 31 and divide that by 10. And that remainder is going to be stored in this result variable. So here we're also going to get a 1. So let's build with GCC, and we're going to run the program, and we are also going to get a 1 down here. Again, the modulus operator can be hard to understand for beginners, but it is really capturing the remainder of the division. Again, we can see that here. We are asking how many times can 10 fit in 31? And we visualize this here. It can only fit in 3 times, and the remainder is going to be this red thing you see here. It's going to be 1. And when we do a modulus operation here, we are interested in that remainder, and that's what we're going to be storing in whatever variable that is capturing the result of this modulus operation. And that's what we basically have here. And this is really all we set out to do in this lecture. Now, I hope you have a good understanding of these operations you can do on integers. We have used integers here, but you can really do these operations on numbers, except for the modulus operator, which is really going to make sense for integral types. So you can't really do modulus on floating points or fractional numbers. That's not going to make any sense at all. We're going to stop here in this lecture. In the next one, we're going to learn about precedence and associativity, a very important concept for your operations in your C++ programs. In this lecture, we're going to learn about precedence and associativity. So what do we mean by precedence and associativity, really? What we mean by this is a set of rules that we can follow to know what to do when we have multiple operators in the same expression, like in the example we have here. If they tell you to evaluate the result of this expression, if we don't have clear rules to follow, we might have multiple answers, and we want to know which one is right or wrong. For example, one might want to do A and B first, and then do C, and then do D, but one might want to do E minus F, and do B multiplied by C, and then do things in different ways and get different results. Hopefully, you are seeing that this may be a big problem. What we get from precedence and associativity is the rules we can follow to know which operator we have to do first. For example, in C++, the multiplication and division operator have to be done before you do addition and subtraction. And if you want to evaluate this expression here, you're going to have to do B and C first, and then do D and E. Once you have those results, then you can do addition and subtraction. But the question remains still. What do we do first if we have only addition and subtraction in an expression? And we solve that problem with associativity. Associativity defines if you do the operations from the left or from the right. And again, these things might not make sense yet. We're going to do an example, and you're going to really see what is meant by this. To summarize, precedence tells you which operation you can do first, and associativity is going to tell you in which direction you're going to go, from the left or from the right. And some operators are going to be left associative, and that means that you're going to start evaluating them from the left. Some operations are going to be right associative, and you're going to start evaluating them from the right. And I am not making these things up. There is actually a C++ operator precedence table that you can consult to know which operators you should do first if you really are evaluating this thing with your mind. Okay, for example, if you look in this table, there are many operators we haven't seen yet, but that's not the problem. The most important thing here is to know what precedence and associativity are, and when we get to learn about these new operators, you can come here and know where they sit in this precedence table. For example, we know how to do addition, multiplication, and modulus. We see that the precedence for multiplication, division, and modulus is higher than for addition and subtraction. And we can use this in our operators to know which one is going to be evaluated by our compiler first. Another thing I want you to notice in this table is this column here on associativity. If you go back to our familiar operators here, you're going to see that these operators are left to right, so you should start evaluating things from left to right, but some operators have right to left associativity. And when we get to these operators, you will start doing things from right to the left. Okay, I think it is time we went to Visual Studio Code and actually played with these things. Here we are in Visual Studio Code. We are in our working folder.
The 20+ million votes, according to science. I don't know if there's any other collection of data like this anywhere on the internet, so this is super cool to get into. So let's dig into it. So first of all, overall winner. So with the highest average ELO rating across all three categories, in third place is the Asus Zenfone 9. In second place is the Pixel 7 Pro. And first place is the Pixel 6a, the People's Choice camera of 2022. But there is a lot of fascinating information to unpack here. So first of all, doing well in one category did not necessarily guarantee doing well across any of the other categories, right? So the Pixel 7 Pro came in second, fourth, and first in the three categories. The Pixel 6a came in third, second, and second, but the Oppo Find X5 Pro actually came in first for standard, then third for low light, and 15th for portrait mode. This basically means that if you wanted, you could argue for the importance of the standard photo over the low light or the portrait mode photos. So let's say the standard photo is like 3 times as important to most people as the other two categories, which feels about right. With that weighted importance on standard photos, then the Oppo Find X5 Pro becomes the overall winner, which is interesting. And in case you're wondering where the iPhone was in all this, the iPhone 14 Pro tested in 6th place, 10th place, and 5th place. But a natural curiosity, for me anyway, was to ask, what were the biggest losers? Which ones got absolutely destroyed the most in this test? And your undisputed winners of losing the most is the Sony Xperia 1 Mark IV and the Moto Edge 30 Ultra. These phones performed terribly in these tests. So the Sony, despite its world-class sensor and extremely advanced apps, when in full auto like the rest of these phones, did not produce good pictures and ended up with the lowest average ELO rating across all three categories. And then the Moto Edge 30 Ultra actually had the most overall losses. It took a bizarre sequence of photos, including an extremely dark standard light photo and an incredibly over-sharpened low light photo, that it's the only one to have 2 million total votes against it. Now, here's another interesting thought. Votes per dollar. If we wanted to sort by bang for the buck, basically, which ones, if we account for the launch price, the MSRP, which one was performing the best relative to its price. And the two winners for votes per dollar, by far, are the Pixel 6a, no surprise, over 4,200 votes per dollar, and the Realme 10 Pro Plus also sneaks in there, the only other phone up over 4,000 votes per dollar. Sneaky good camera phone for $379. And then the obvious losers, again, are the $900 Moto Edge and the $1,600 Sony Xperia 1 IV. Also, I just had to look through the text files and find the biggest dunk, just the biggest overall matchup discrepancy between two phones in any category. And I found it. That would be portrait mode, Pixel 7 Pro versus Sony Xperia 1 Mark IV, with the Pixel winning 98% of the votes here. So to the 1,523 of you that voted for the Sony here, not sure what you saw that the rest of us didn't. But overall, just more than seeing which ones got the most votes is seeing why certain phones and certain pictures got the most votes. And the best way to do that was actually just putting all of the photos in order side by side in order of how many votes they got. And that's how we started to see some really interesting patterns. So like, for example, last time in the head-to-head, we kind of established that in a case of A versus B, if one photo is a little brighter than the other, it'll probably win. But how far can that go? Is there a such thing as too bright in this case? And it turned out, yes. This is all the standard mode photos in order. And yes, the 3 darkest photos are the 3 biggest losers, hands down. They crushed any shadow detail in my hair and the extremely comfortable sweater I'm wearing on shop.mkbhd.com. But right above that is 3 of the absolute brightest photos. Like, these were just overexposed straight up. Matter of fact, it looks like we kind of got this order of great photos, then too bright, then too dark. So it shows me that good exposure wins, but if you're gonna miss, then yeah, people would rather have it be too bright than too dark. With night mode all together and in order, you can kind of see a bit of the same thing. So the most neutral, correct exposures generally won if they were sharp. This time there's about 4 good exposures: Vivo X80 Pro, Pixel 6a, Oppo Find X5 Pro, and Pixel 7 Pro. Then there's the 2 brights, which people mostly preferred over the 2 darks. Also, there were some seriously wild things happening with some of these photos. In low light, the Vivo, it absolutely nailed it. It's clearly the low.
We are going to grab our template projects. We're going to copy this and put that in our lecture on precedence and associativity. We're going to put that in here. We are going to open this project in Visual Studio Code. We are going to get rid of things we don't need and remove this here in the body. And we are going to put in our test code so that we don't have to type this and save on time. We have a few variables here, A through G, and we have an expression here or a statement that is combining multiplication, division, addition, and subtraction. And we have to figure out which operation we're going to do first. I would challenge you to do this in your mind and try to guess what the result is going to be before we run this in our compiler. We're going to compile this with GCC, and we are going to open our terminal here. And if we do dir, we're going to see that we have rooster.exe. If we run it, we're going to see that the result is 30. How did we come up with that? Well, the precedence and associativity table says that multiplication and division have to be done first before addition and subtraction. We are going to take B and C and multiply those. So B and C multiplied, we're going to get a 24. We're going to try and do this in our brain. D divided by E, we're going to do that. So D divided by E, we're going to get a 3. So we're going to have a 3 here. And after we have this, we're going to do addition and subtraction. So we're going to take A and add that to the result of B and C. So we're going to say 6 plus 24, which is the result of B and C. We're going to minus the result of D and E, and we're going to do minus here. I hope you are following. And then we're going to minus F and plus G. We're going to minus F, which is 2, and do a plus G, which is 5. Okay, so this is our expression here. And now that we have this, we have to think about how we're going to do this. We can try to do this from the right, do 2 plus 5, and then do 3 minus 2 plus 5, and go from right to left. But our associativity table says that addition and subtraction have left to right associativity. So we will start from the left. So we're going to do 6 plus 24, we're going to get 30. We're going to minus 3, and we're going to get 27. We're going to minus 2, we're going to get 25. We're going to add 5, we're going to get 30. I hope you are following. And we are really following the rules from our C++ operator precedence table here. Okay, so this is really how you would use this precedence and associativity rules to evaluate your expressions. Okay, here I have another example for you. So try to evaluate what we're going to get from this expression here. We have A divided by B divided by C plus D minus E plus F. Try to do this in your brain and try to guess what we're going to get from the compiler if we print this out. We're going to put in our stdc out statement here, and we're going to try and build this with GCC, of course. We're going to run rooster, and you're going to get a 24. So how did we come up with that? We're going to start by division and multiplication. And again, where do we start? Do we do B and C first, or do we do A and B first? Well, we can check our precedence table here, and we're going to check the associativity of multiplication and division. We're going to go to this entry here, 13, and we see that it is left to right associative. These operations here are left to right associative. So what we're going to do, we're going to start from left and go to right. So we are going to take A and divide by B. If we take A divided by B, we're going to get it 2. So let's type that here. Then the result of that is going to be multiplied by C. And if we go up, we're going to see that C is 8. So we're going to multiply by 8 and get 6. So we can replace this with a 16, and we should be here. Then we're going to add D. D is 9. Then we're going to subtract E, which is 3. Then we're going to add F, which is a 5. So we have 16 plus 9. This is going to give us 25 minus 3. Okay, by checking this out, I see that I made a mistake. F is not 5, it is a 2 we have here. And if we do this from left to right, because addition and subtraction are left associative, we have to do them from left to the right. We're going to take 16 and add a 9. We're going to get a 25 minus 3, we're going to get 22, plus 2, we are going to get 24, and that's what we have here. I really hope this makes sense. Okay, so we have seen how we can use this precedence table, but sometimes you want to make it really clear which operations should be done first. And you can do that by using parentheses around your expressions. Let's grab the first expression here and do it again. We're going to copy it and go down and put that in place, and we're going to store the result in our result variable. And notice that we are reassigning these things to the result variable so that we don't have to declare another variable. I think this is clean, and that's what we're doing here. So what we can do here is make it clear that we want multiplication done first by using parentheses, and make it clear that we want the division to be done first. And when you do this, the compiler is going to see that you want this operation here done first. And that's what it is going to do. And if we print result again, we're going to get exactly the same thing we had before. stdcout result. And we're going to put result out. And let's make it clear that we are using parentheses here to signal which operation we want to be done first. We can compile this with GCC. We're going to run the task to build with GCC. And if we run the program, we're going to see that the result is 30, exactly what we had before. But now it is very clear to the reader of this piece of code that we want B and C done first. They don't have to go through the precedence table to really try and figure this out, potentially wasting precious time. Another thing you can do with this is, for example, what if the precedence table is not working according to your needs? For example, you really want A and B done first. You can specify this with parents here. And what this is basically going to do is going to force the compiler to do this first. It's no longer going to do B multiplied by C and D divided by E. It's going to evaluate this first. Then it's going to follow the order in the precedence table that we have seen before. So try to guess what we're going to get now. And I am going to run the code, and we're going to go through this together. So let's run task, and we're going to run rooster. Now you see that the result is 72. What is happening here? Well, let's go through this line by line. We are doing A plus B, which is 9. So we're going to get a 9 here. We're going to put that here as a comment. Then we're going to multiply that by C. So we're going to do 9 multiplied by 8, and that's going to yield a 72. And by that time, we're going to be here, and we're going to do the division first, D by E. Then we're going to take 9 and divide by 3. That's going to yield a 3, so we're going to have a 3 here. Minus 3. We're going to minus F, which is a 2. And we're going to do plus G, which is a 5. If we evaluate this, we're going to get 72 minus 3, which is going to be 69. Minus 2, it's going to be 67. Plus 2, it's going to be 72. And that's what we have here. Hopefully you can see that using the parents, not only can you make it very clear which operation you want to be done first, you can also define the rules that are prescribed by the precedence tables that are defined in C++. I hope this makes sense. And this is really all we set out to do in this lecture, to learn a little more about precedence and associativity. And my advice to beginning programmers is not to rely on the precedence table too much. It is to try and make your intent very clear using parentheses, and anyone reading your code won't have to go check these rules in their reference C++ documentation. They are going to directly understand what your expression is going to do, and that's a good thing. Readability of your code is really something you should strive for. This is really all we set out to do in this lecture. I hope you have a better idea about precedence and associativity. We are going to stop here in this lecture. In the next one, we're going to learn about some cool things we can do with addition and subtraction. Go ahead and finish up here and meet me there. In this lecture, we're going to be learning about prefix and postfix addition and subtraction. We have an example here, and it is a simple example we've seen a lot of times by now. We have a variable value, it is an integer, and we have a 5 inside. We can add a 1 to it, or we can increment it by 1. This is another term we use in programming languages. When we say we are incrementing a value, we are adding something to it. In this case, we are incrementing it by 1, and we are basically going to store a 6 in this value here. So if we print this out, we're going to get a 6 here. This is what we would expect. We are resetting the value to 5, and we are going to minus 1 or decrement by 1, and the result is going to be saved in value again. So the second stdcout statement here is going to print a 4. This is something you should expect. Now, another thing we can do in C++ is do something like value ++ here. And what do we mean by that? When you use a postfix increment operator like this, the first thing you should know is that this is going to increment by 1. It's not going to increment by any other value. C++ doesn't provide a way for you to specify another number to increment by. So value ++ here is going to increment by 1. But another thing you should know is that it's not going to increment directly. What's going to happen here, if you look to the top here, we have a value 5. When execution hits this stdcout statement, we are going to grab the value here. So here we're going to really print a 5, but as soon as this statement is done, the value is going to increment by 1. So the next time somebody is going to use this value here, he's going to find in a 6. And that's what we have here. So the first one is going to print a 5 because we're going to grab the value in here as is, But as soon as we have our value, this is going to increment by 1. This is what we mean by this value plus plus here. And the second statement is going to print a 6 because it is already incremented. And we call this postfix increment because plus plus is after the value here. And this is really what this operator does. And sometimes it is going to come in handy in your C++ applications. We can also do the same thing with minus minus. It is going to grab whatever value we have in this variable. So we have in a 5. So that's what we're going to print here. And the next statement is going to find it already decremented by 1 because after we have our 5, we're going to decrement by 1. That's what we are saying here. And we're going to find in a 4 because 5 decremented by 1 becomes a 4. I really hope this makes sense. Okay, so what we have seen here is postfix increment and decrement. But we can also do a prefix version of this thing. If you look at the example we have here, we have a 5 and we are saying plus plus value. So this is going to increment the value directly. So as soon as this statement is executed, the plus plus value statement here, we're going to have a 6 inside. And if we print it, we're going to get a 6. And this is what you see here. If we go down, we are resetting our value. And we are going to prefix increment in place. So in here, we are going to increment the value before we actually print it here. And we are also going to get a 6 here. I hope this makes sense. And if you have any problem with this, I think if we go in Visual Studio Code, you're going to have a better way to say this. You're going to see the code running and make sense of it. Okay, so I think that now you understand why we're going to have these numbers printed. If we go down, we can do the same thing with decrementing. We have a value here, it's 5. If we prefix decrement it, it's going to be a 4 here. And if we print it, we're going to get a 4. If we go down here, we are resetting that to 5. And we are going to prefix decrement in place. And this is also going to print a 4 because we have a 5 here. And if we decrement it by 1, we're going to get a 4. And that's what we're going to get here. Okay, this is really all these prefix and postfix increment and decrement operators are about. We are going to go in Visual Studio Code and actually see this running. Okay, here we are in our working directory. We're going to do the usual. We're going to copy code from our template project. We're going to put that in here. We're going to go up and open this up in Visual Studio Code. So we're going to remove things we don't need. And we're going to remove this. And we are going to put in the code we exactly saw in the slides. Here we have a value. It is an integer and it is 5. If we increment it by 1, we're going to get 6 here. Okay, and if we print it, that's what we're going to get. We are resetting this to 5. And if we decrement it by 1, we're going to get a 4 here. So if we run this piece of code, we should have a 6 here printed out and a 4 down here. We're going to bring up our terminal and build this with GCC. The build is going to go through. And if we run the program, we're going to get the value is 6 and it is 4. And this is really what we expect here. Okay, now that this is really clear, we're going to go down and play with postfix increment and decrement. I am going to put in a separator here so that we can clearly see in our terminal here. And we are going to put in our test code that we are going to use to play with this. Let's bring this down a little bit so that you can see everything. We can remove these things. We don't need them anymore. Okay, we are going to take the value we had. We're going to reset that to a 5. And if we value plus plus here, this is going to be a 5 because we're going to capture the value as is. So here we're going to get a 5. But next time we get this value, it's going to already be a 6 because we increment immediately after capturing the value here. So here we're going to get a 5 and here we're going to get a 6. I hope this makes sense. And if we go down here, we are resetting our value to 5 before we do any decrementation. We are going to capture the value as is because we are doing postfix decrement. And here we're going to get a 5 because we are capturing the value as is. But as soon as we capture our value, we're going to decrement it. And the other statement here is going to get a decremented value, and that's going to be a 4. So here we're going to print 5, 6, 5, 4. Let's try and build this with GCC to see that we have no problems. We have no problems. The build is good. If we try to run Rooster now, we are going to get the results we had before. But for this code we just put in here, the value is going to be a 5, and that's what we have here. And we're going to get a 6, which is coming from here. After, we are going to decrement, and we are going to capture the value as is. We're going to get this 5 here. And for the last statement, we're going to get a 4 because the value is already decremented. And that's the 4 we are seeing here. I really hope this makes sense. And this really covers the postfix increment and decrement operators. The last thing we want to see in this lecture is that we can also do prefix increment and decrementation. We're going to go down here and set up a place where we're going to be playing with this. So we're going to say prefix. And we are going to put in our code because I don't want to type all this. That would waste your valuable time. But I do encourage you to type these things out and really drill them in your brain because that's how you're going to learn. Okay, let's bring this down so that we can understand this piece of code. So we are starting by resetting our value to 5. And notice here that we do plus plus value. This is going to increment value right away. By this time, value is going to be 6. And if we print it out here, we're going to have a 6 printed out. We're going to reset it to 5, and then we're going to increment that in place. This is also going to be printing 6. And if we go down, we're going to do the same version of the same thing, but we are going to be decrementing. So we're going to decrement the value that we just reset here. Here it's going to become a 4, and that's what we're going to print. And if we go down here, we reset it again to a 5, and we prefix decrement it in place. So the 5 here is going to become a 4 in here, and that's what we're going to print out. If we build and run, that's what we're going to get. We're going to run our task to build with GCC. The build is good. And if we run our rooster application, the results for the code we just put in here are just going to show up here. And you see that we get a 6, 6. This is 6, the other 6. And for the last 2 statements, we're going to be getting 4s, and that's what we have here. I really hope that now you have a better idea of this prefix and postfix increment and decrement operators, and you're going to make use of them when they really help you design your applications better. Okay, so these are your tools. Use them when they make sense. Another thing that I want to emphasize here is that these operators only increment or decrement by 1. You can't make them do things in increments of 5 or 7 or 10. They are going to work in increments or decrements of 1. We are going to see a way we can do that with other operators in the next lecture, but these prefix and postfix operators can't do that. And another thing that some of you might be wondering about is if we have the same kind of operators with multiplication or division, and we don't have those operators in C++. Maybe we're going to have them in the future when they make sense, but in the current version of C++, we don't have them. We are going to stop here in this lecture. In the next one, we're going to learn about compound assignment operators. In this lecture, we're going to learn about compound assignment operators. And these are operators that allow you to do an arithmetic operation like addition, subtraction, multiplication, division, and modulus, and assign the result to a value in one go. Let's look at an example here. We have value here, which is 45. It is an integer, and we're going to print that out. But if you go down here, we are doing value plus equal 5. And if you look at the comment here, this is equivalent to if you did value equals value plus 5. So what this is going to do, it's going to take whatever value is in this value here, it's going to increment that by 5. So that's going to become a 50. And we're going to store that 50 results back in this variable here. So by this time, if we print this out, we're going to get a 50. Again, we're going to take the value. It is a 45. We're going to add a 5. It's going to become a 50. And we're going to store that result back in this value variable here. It's going to become 50. And if we print here, we're going to get a 50. This is the addition version of the compound assignment operator. We also have a version for subtraction, and we have an example of that here. So it's going to take whatever value is in this value variable. It is going to find in a 50. We're going to subtract 5. We're going to get a 45, and that's what we're going to store in this value here. And by the time we hit this stdcout statement, we're going to print a 45. Again, we have another version for the multiplication here so that we can really play with all these things. We're going to take whatever value is in here. We're going to multiply that by 2 here. We're going to get a 90, and that's what we're going to store back in this value. And if we print here, we're going to get a 90 printed out. We're going to go down and do a version for the division. The value is 90. We're going to divide that by 30, and we're going to store the result back in value here, and we're going to get a 30 stored in here. And if we print out, that's what we're going to get here. We also have a modulus version of this, and it works really well. Here we have in a 30. We're going to take it and do modulus 11. And what is the reminder of dividing 30 by 11? The reminder is going to be 8, because 11 can only fit in 30 2 times, and we're going to be left with an 8 because 30 minus 22 is 8. And that's what we're going to store in the value here. And if we print out, that's what we're going to get. Again, if you have trouble understanding this modulus operator here, please go back in a few lectures back. We had a chance to learn about it. Make sure you understand it, and then come back here, and this is all going to make sense. This is really all compound assignment is all about. We're going to head to Visual Studio Code and actually play with us. Okay, here we are in our working directory. We're going to copy our template project as we always do. And we're going to put that in our compound assignment operators lecture here. We're going to come up, and we are going to open this folder in Visual Studio Code. The project is going to show up in here, and we're going to open our main CPP file, and we are going to remove what we don't need. We are going to put in our code so that we can start exploring this. We have a 45 in this variable here, which is an integer. If we print it out, we're going to get a 45. And down here, we are doing a compound addition. So what we are doing here, we're going to grab whatever value is in this variable. We're going to add a 5. We're going to get a 50, and that's what is going to be stored in here. And if we print this out, we're going to get a 50. Let's put in a terminal here so that we can see this running. And we're going to run the task to build with GCC as we always do here. And if we run our rooster executable, we're going to get the value is 50, and that's what we expect here. Okay, this is the addition version of our compound assignment operator, and it is really equivalent to doing this in 2 steps, saying value equals value plus 5. You're going to get the same result if you do that here. Actually, let's do this so that you don't think that I am making this up. So let's comment this out, and we are going to say value equals value plus 5. And if we build again, run the GCC task, and run the application, we're going to see the same thing. We can also go down and run the subtraction version of this example here. Here we are taking the value that we have in here, which is a 50. We are subtracting 5, we're going to get a 45. And a 45 is what we're going to store in this value here. That's what we're going to see if we print this out. So let's run the task to build with GCC so that our changes are reflected in our output. We're going to run this and we're going to get a 45. This is what we expect. We are going to go down and do a multiplication version of this. Here we have our compound assignment statement. We are taking whatever value we have in here, which is a 45. We're going to multiply that by 2, and the result of that is going to be 90, and we're going to store that back in value here. And if we print value here, we're going to get a 90. Let's build this, run the GCC task, and we're going to run our program, and we're going to see that we're going to see this 90 here. We can go down by a few lines and put in the code to play with a division version of this. Again, this is going to do really the same thing, only it's going to be doing this for division. We're going to take whatever value we have in here, which is going to be a 90. We're going to divide that by 3. We're going to get a 30. And that 30 result is going to be stored back in value here. And if we print this out, that's what we're going to get. Let's build again. And the build is going to go through. If we run our program, we're going to get a 30. We are going to go down by a few lines and put in a modulus version of this. We're going to grab whatever value we have in this variable here, which is going to be 30. We're going to do modulus 11 on that value. And that's going to be basically 30 modulus 11. The result of that is going to be 8. And we're going to store that result in value here. And if we print that out, that's what we're going to see in this output statement here. We can build again, run with GCC. And if we run our rooster program, we're going to get an 8 printed out. And this is really all these compound assignments are about. And you might be asking, why go through the trouble to do something like this if I can do this like this? Well, C++ gives you different ways to do things. Different people have different preferences, and some people, me included, like to do things this way because it is compact. And once you use this, you're going to get used to this. You're not even going to think about it. In this lecture here, I just wanted you to be aware of this possibility because you are definitely going to see it in C++ code out there. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to learn about relational operators in C++. In this lecture, we're going to learn about relational operators in C++, and these are basically operators you use to compare stuff. Let's look at a piece of code here. We have two numbers. One is 45 and another is 60. They are stored in integer variables, number 1 and number 2. We can print them out and we're going to see them on the console or our terminal. And if we go down, we can really compare them. We can use the less than operator, less than or equal operator, greater than, greater or equal operator. We can check and see if two numbers are equal by using two equal signs here. Be careful about these two equal signs because if you use one, you're not going to be comparing numbers. You're going to be taking the thing on the right and assigning that to the thing on the left. So if you want to compare, you're going to have to type two equal signs. Another operator we can use to compare stuff is exclamation mark and equal, which is going to basically test if two numbers are equal. And we're going to get the result. One thing you should notice here is that we are wrapping our comparison expression into parentheses. That's because if we don't, we're going to get a weird compiler error that I am going to show you when we get in Visual Studio Code, but we don't have enough tools to really understand this error at this moment. So what we are going to do is avoid that problem by putting parentheses around our comparison expression here. We're going to go to Visual Studio Code and actually see this in action. Here we are in our working directory. We're going to grab the code from our template here, and we're going to put that in the current project, which is relational operators. We're going to go in and put in our code, and we are going to open this up in Visual Studio Code. We're going to get rid of things we don't need here. We are going to put in our code so that we can explore these things. We have two variables. In one, we have a 45. In another, we have a 60, and these are integers. The name for these variables are number 1 and number 2. We're going to print them out, and we're going to see them on the console. Now we are going to compare them. One thing I haven't told you yet is that these comparison operators evaluate to booleans. In other words, they are going to return true or false. If you look down here, we want to know if number 1 is less than number 2. And the result of that is whether that's true or false. And this really makes sense. So because of that, we are using std bool alpha here to force stdc out to print this boolean value here as a true or false instead of a 1 or a 0. And we have seen this before. So if we try to build this and run this, let's bring up a terminal we can use. And we're going to run the task to build with GCC. If we go down here and run our rooster program, we're going to get our two numbers, 45 and 6. And we want to know if number 1 is less than number 2. And that's true, 45 is less than 60. So the result of this expression is going to be true. Now you know how to use this operator. One thing I want you to see is what could happen if you didn't use these parentheses around this expression here. Let's try this out. We're going to remove these parentheses and we're going to try and build. We're going to run the task to build with GCC, and we're going to get a really weird error because the compiler is going to try and evaluate this operator first. If we go back to our C++ operator precedence table and look at the operators we are trying to use in the stdcout statement, we're going to see that the operator to print things on the console has high precedence than our comparison operators here. So the precedence for our operator to print things to stdout is 11, so it is higher, and the precedence for our comparison operators is 9 and 8. So the compiler is going to try and do this operator first. If we come back in Visual Studio Code, the compiler is going to try and think that you are printing number 1, but then again it's going to see this less than sign and things are going to blow up. We don't really have enough tools to understand what is going on right now, but I just would want you to see this error and show you a way to go around it and move on with your life by comparing stuff in your C++ programs. If you put parentheses around here, the problem is going to go away. Let's try and build again. We're going to build with GCC, and everything is going to go back to normal, and we're going to see our output if we run our Rooster program here. This is how you can do this. Okay, now that we have a basic understanding of this, we can try the other operators, and it is going to be a walk in the park. We are going to go down here and put in our remaining operators. We can use less or equal operator to test and see if number 1 is less or equal to number 2. We can use the greater than operator to test and see if number 1 is greater than number 2. We can use the greater or equal operator. We can use the equal operator to test that number 1 is equal to number 2. And we can use this operator here, which is made up of the exclamation mark and an equal sign, to test and see if two numbers are not equal. And all these operators are going to evaluate to a Boolean, basically saying if what you are testing for is true or false, and we can print this out. And notice that we have these parentheses around to avoid the problem I just showed you a few minutes earlier. And if we run this, we're going to see the results. Let's build this with GCC as usual. We're going to run our program, and you're going to see that number 1 is less than number 2. This is true. Number 1 less or equal to number 2. This is also true. Number 1 greater than number 2. 45 is not greater than 60, so this is false. It's not greater than equal, so this is also
like king. The S22 Ultra, interestingly, came in 5th place, even when completely missing focus on my stationary face and hitting the background for some reason. The iPhone 14 Pro did an enormous amount of HDR that had me looking kind of green like a zombie, but it still came in 11th place here. The Moto Edge Plus, as I mentioned, kicked out maybe the most over-sharpened photo the world has ever seen. And then in dead last is the iPhone SE, the only phone in this test that does not have night mode. And the sad thing is, like, it does have OIS, it does have a decent sensor, and it does have a new processor, but Apple just feels the need to protect their more expensive phones with more premium features, so they didn't give the SE night mode, and it suffered big time here. Then in portrait mode, we have the most variety of them all, because not only are we judging things that we normally would about a photo, like sharpness, color, exposure, etc., but we are also now adding cutout quality and artificially blurred background quality. And every phone uses a slightly different focal length for their portrait mode by default. Some of them do a 2x portrait mode, some of them 2.5, some of them 3x, some of them even do 1x. But combining all of these factors, the Pixel 7 Pro absolutely dominated portrait mode. This was the runaway winner here in this category. Great cutout, great exposure, great colors, and a nice soft background. It nailed it. But guess what? The Pixel 6a was in second, and the Realme 10 Pro Plus snuck in there in third, right above what I consider the best cutout of the entire competition, which came from this Galaxy S22 Ultra. I think it's pretty close to perfect at edge detection here, pretty similar to the Zenfone 9's cutout, but a better overall photo, so it got 4th place instead of 7th. I was also curious if there would be a correlation between how many votes a phone got and whether or not they used more of a telephoto focal length, just because maybe it would feel more natural having a blurred background if you're at 3x. But when we lined it all up, there was almost no trend line at all and no correlation, so that was interesting. Really, the only other definite thing I noticed about portrait mode photos is that the 3 worst photos that got the fewest votes by far were also by far the brightest photos. So see, it turns out you can overdo the brightness. And that, I think that is basically it. So, summary time, just from all the data that we have.
straight in and attempt to tick off one of these 5 quintessentially American side challenges off our little list. But what exactly would this challenge involve? Well, because we'd be completely useless in an actual game of basketball, we thought it might be better to approach a group of local youths and challenge them to a long-distance shootout. We had the perfect location in mind, but first we needed to kit ourselves out. The plan, before this demonic figure came to our attention,
Oh dear. That's good. Sorry, I'm not good.
was to make a beeline for the mall, where we would need a bit of guidance.
You can see a guy with dreads, his name is Marcus.
Awesome.
Tell him Jay sent you.
Jay sent us.
And
Okay.
he's gonna
And
find
he'll
you
sort us
that
out with free gear.
Well, he's not free, he's gonna get you hooked up with the jersey.
Yeah. Thanks, man.
Sweet.
Appreciate it.
Thank
Thanks a
you.
lot.
What are you saying, mate?
With the virus
What
and
do you think? Yeah, what do you think? We just buy one 50% off. Probably worth
how
it,
much
isn't
they
it?
are.
Yeah.
Unfortunately, Marcus's jerseys were a little out of our
False. Number 1 equals to number 2. This is going to be false. And the last statement that is going to test and see if number 1 is not equal to number 2 is going to evaluate to true, because number 1 is not equal to number 2. If this is not making sense yet, please go through it a couple of times. And if you have a problem, please do ask me. I will do the best I can to help you out. Another thing I want you to see before I let you go is that you can store the results of these operators into a variable and use that later in your program. For example, here we can take our expression to compare number 1 and number 2. The result of that is going to be stored in this bool variable, and we can print it out later like this. If we run this, we're going to build with GCC, and we're going to run the program. We're going to see that 45 equals to 60 is false, and it is coming from this statement here. You can try and change these numbers, for example, change this to a 20, and see the results that we get, and you can try and run these in your mind and see that they really make sense. If we run rooster now, we're going to get different results because we are now comparing 45 and 20, and here at the last statement you see that they are not equal. If we put in 2 equal numbers, we're going to get a true there. Let's try this out. We're going to run the task to build with GCC, and if we clear so that we get rid of all this noise and run rooster, we're going to get 20 is equal to 20, and this is true. This is really all we set out to do in this lecture. I hope you have a better idea of these relational operators in C++. We're going to stop here in this lecture. In the next lecture, we're going to learn about logical operators in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about logical operators. These operators will work on Boolean operands. We're going to look at AND first to really make sense of how they work. Here is a simple table we can use to try out the AND operation. It is going to be working on 2 operands, A and B, and in the third column here, we're going to have the result. So if A is false and B is false, and we do A and B, the result is going to be false. If A is false and B is true, the result is going to be false. If A is true and B is false, the result is going to be false. If A is true and B is true, the result is going to be true. The way you can think about this AND operator is that if any of the operands is false, the result is going to be false. And if you really use this way of understanding this, it is going to be really easy. In the first line here we have a false, so the result is going to be false. In the second line we have a false, it's going to be false. In the third line we have a false, the result is going to be false. But in the line number 4 here, we don't have a false. A is true and B is true, so the result is going to be true. Another operator we have is OR, and it is going to evaluate to true if any of the operands is true. Let's look at the first line here. A is false and B is false, so we don't have a true. The result is going to be false. On the second line we have a true, the result is going to be true. On the third line we have a true, the result is going to be true. On line number 4 we have a true, the result is going to be true. And you don't really have to memorize these tables. If you use these operators long enough, these things are going to be drilled in your memory. If you have any problem with these operators, just look up tables like this and you can find whatever it is you need without really memorizing these things. Another operator is the NOT operator, which is going to negate whatever you give it. So if A is true and we negate that, we're going to get a false. If A is false and we negate that, we're going to get a true. And we use this exclamation mark to say that we are negating something. If you go back to OR, it is denoted by these 2 vertical bars, and the AND operator is denoted by these 2 ampersand symbols here. Okay, now that we know about these logical tables for these logical operators, we can actually try to use them in code. Here we have 3 Boolean variables. We have A, B, C. A is true, B is false, C is true. We can print them out, and you see that we are setting up stdc out to give us the results in the format of true and false instead of ones and zeros. And down here, you see that we are trying to use the AND logical operator. Down here you have A and B, A and C, and we are doing this on 3 operators and chaining these things up. So we are saying A and B and C, and let's try and do this in our mind to see that we really understand this. We have seen that the AND operator evaluates to true when all operands are true. Another way to say this is the AND operator evaluates to false if any of the operands is false. So we're going to AND A and B. A is true, B is false, so the result is going to be false because we have a false in here. A and C is going to evaluate to true because A and C are true. A and B and C is going to evaluate to false because we have a false in here. Even if you have 1000 trues and you AND that with one false, that's going to be dragged down to evaluate to false. That's what we are seeing here. We can also do OR operations on these things, and this is going to give you a true if any of the operands is true. We know that A is true and B is false, so this is going to evaluate to true. A and C is also going to evaluate to true because A is true. A and B and C is going to evaluate to true because A is true. So let's go back and see this. These are the values we're going to be using here. We can also try out the NOT operator, and it is going to negate whatever we gave it. So if A is true, we're going to get a false. B is false, we're going to get a true. C is true, we're going to get a false. Another thing you can do is combine these logical operators. So we can do something like A and B and OR that with a C. And you should notice that we are wrapping our expressions here in parentheses so that we don't have the same problem we experienced and explained in the last lecture. And one thing you should know is that for the compiler to evaluate these things, we are going to follow the rules in our table for precedence and associativity, but we used parentheses to really make this easy to follow. So we are going to AND A and B, and the result of that is going to be ORed with C. And you can try and do this in your mind, and you're going to figure this out. But we're also going to go to Visual Studio Code in a minute, and we're going to see all these things in action. The last thing you can do is combine logical and relational operators into expressions. For example, here we have D, E, and F. They are integers, and we can print them out like we are doing here. But we can do something like D greater than E, and we're going to AND the result of that with D greater than F. And we know that these relational operators evaluate to booleans, so we can use these booleans with logical operators like we have been doing all along in this lecture. So for example, let's evaluate the first one here in mind so that you really see what this is all about. D is 45, E is 20, so D greater than E is going to evaluate to true. D greater than F, that's also going to evaluate to true. So true and true, that's going to evaluate to true, and this should print a true on the terminal. We are going to go to Visual Studio Code and actually play with these things. Okay, here we are in our working directory. We're going to jump into our template project and copy the files we need, and we're going to put them in our lecture on logical operators. We're going to put that in here. We're going to open up this folder in Visual Studio Code, and it is going to show up here in Visual Studio Code. We're going to get rid of what we don't need, and we are going to put in the code to play with these things. We have 3 Boolean variables. A is true, B is false, C is true, and we can print them out, and we're going to see their values, and you see the setup here so that stdcout is going to show things in the format of true and false. And down here we are ending a few values. We are using the AND operator, and it is denoted by these 2 ampersand signs. So A is true and B is false and C is true. A and B is going to evaluate to false because we have a false in here. And again, if this doesn't make sense, please do consult the tables for all these logical operators, and all these things are going to make sense. This is going to evaluate to false because we have a false in here. And A and C, we have true and true, so this is going to evaluate to true. And A and B and C, this is going to evaluate to false because we have a false in here. Remember, as soon as you have a false in your AND logical operation, you're going to get a false in your result. So we're going to have a false here. We can try and compile this and see if this is actually what we expect. We're going to bring up a terminal we're going to use here, and we're going to run the tasks to build with GCC. And if we run our rooster program, we're going to see that A and B is false. This is what we expect. A and C is true. This is what we expect. A and B and C is false, and this is what we expect. This is how you can really play with your AND logical operator. If you want, you can change things up to really try and see if they live up to your expectations. Now we have changed A to false. Let's try and build again. We build with GCC, and we're going to run our program, and we're going to get A and B is false because they are all false. A and B are false, so false and false evaluates to false. A and C is false because A is false, so we're going to get a false as the result. A and B and C is also going to evaluate to false. Okay, we have these things in here. Let's bring this back to what it was before. So A is going to be true, B is going to be false, C is going to be true, and we're going to try and play with the OR operator. We are going to go down and put in code to actually play with this, and it is really nothing special. We are just using the OR operator here, which is denoted by these 2 vertical symbols, and OR is going to evaluate to true when at least one of the operands is true. Okay, so we have our values here. A is true, B is false, C is true. A or B is going to evaluate to true because A is true. A or C is going to evaluate to true because A is true. A or B or C is going to evaluate to true because one of these things is true and A is true here. We can try and run this. We're going to build this first with GCC, and if we run this, we're going to go down here and run rooster again, and you're going to see that all these things are true here because one of these things is true, and as long as you have one true operand, your OR operation is going to evaluate to true. And again, this is following the precedence and associativity rules we have. If we go back to our table in our browser, we're going to try and look at logical OR. It is left associative, so we're going to try and evaluate this from left to right. So we're going to OR A and B, and the result of this is going to be ORed with C. We have also seen the NOT operator, which is denoted by the exclamation mark here, and what it is going to do is basically flip off or negate whatever it is you have. If you have it true in your variable, the result is going to be false. If you have it in a false, the result is going to be true. And not A is going to be false because A is true, not B is going to be true because B is false, and not C is going to be false because C is true, as we can see here. So let's run the application and see if this is what we expect. We're going to run and build with GCC, and we're going to run rooster, and we're going to see that not A is false, not B is true, and not C is false, and this is what we expect. We have also seen that we can do combinations of these operators. So for example, we can look at the expression we have here. We're going to take A and B. This is going to evaluate to false because B is false. We're going to negate this, and we're going to get it true, and we're going to OR that with C, but because it's true, we know that the result of ORing this with anything is going to be true, so we expect this expression here to evaluate to true. If we run this, we're going to see that this is going to evaluate to true, and it is what we expect. The last thing we want to see in this lecture is that we can combine these logical operators with the relational operators we have seen in the last lecture. We are going to put in a piece of code to play with this. This is lengthy, but you can play with this and see what this is going to evaluate to. To start you off, we are going to do the first one together. So it does test if D is greater than E, and if you look here, 45 is greater than 20, so this is going to evaluate to true, and we're going to end that with D greater than F. The result of this is going to be true, so we're going to be ending a true, and the result of this is going to be a true. And again, notice that we are wrapping this in parentheses to avoid problems with the compiler being confused with what we are trying to print. This is going to get rid of the otherwise ugly problems we might have to deal with if we didn't wrap this into parentheses like this. So we expect to see a true here, and we're going to build and run the task to build with GCC, and we're going to run rooster. And if we look at the first thing here, this is going to be true, and you can try and do the other ones in your mind as an exercise. And if you have a problem, don't hesitate to ask me. I am going to do the best I can to help you out. This is really all we set out to do in this lecture. I hope you have a better understanding of these logical operators. Again, you don't have to really memorize them. All you have to do is consult the tables, and you're going to basically know the result of your two operands depending on the values you have inside for AND, OR, and the NOT operator. We are going to stop here in this lecture. In the next one, we're going to see how we can format our output to make it really look better. Go ahead and finish up here and meet me there. In this lecture, we're going to look at output formatting in C++. And this is a way we can format stuff we send to the terminal through stdcout and make them show up better. As an example, let's say we have a table here that has names and ages, and you see that they are cramped, and through output formatting, we can take this and turn this into this. And hopefully, we agree that this is better. There are a set of tools we can use in C++, and those we're going to be using in this lecture are going to be coming from these two libraries, iOS and iomanip. And there are a lot of things in these two libraries. Here is a set of cards that show a lot of them. We are going to play with a lot of these in this lecture, so you don't have to worry if some of them seem scary right now. Before we start looking at them, I want to bring to your attention that there is a piece of documentation on these things. The link is here. The website is called cbpreference.com, and you can open this up and look at some of the things we're going to talk about in this lecture. Okay, the first one we're going to look at is stdendl. This is not new. We have been using it all along to print out a new line character so that our stdcout statements print things on different lines. And if we don't have this manipulator, you see here on the top we have hello and world, and if we print them out, they are going to show up on one line because we are not separating the lines with stdendl. Down below here, we have another way we can do this. We can put a \n after our text, and that's going to add a new line character just like stdendl does. Okay, stdendl and /n in here seemingly do the same thing. But they are different, but we don't have enough tools to really understand the differences right now. For now, just think of them as two things that do the same thing. They print out a new character that allows your text to show up on different lines, like we have hello and world here. Okay, stdendl is the first manipulator we're going to play with in this lecture. The next one we're going to look at is stdflash, and this is going to send whatever is in the output buffer to the terminal. And what the heck is an output buffer? Let's look at an example. Suppose we have STDC out here and we want to print on this terminal. And the message we want to print is hello world, how are you? So what is going to happen if the STDC out statement is executed? Things are not going to be directly sent to the terminal. They are going to go into an intermediary buffer. You can think of this as some kind of storage in which data goes before it goes to the terminal. And this is what's going to happen. We print out hello. Hello is not going to go to the terminal directly. We print out world. It's not going to go to the terminal. We print out how are you? It's not going to go to the terminal. And when the buffer is full, the data is going to be sent to the terminal in one go. And this may come in handy in some situations. So if you want the data to go to the terminal directly, you're going to add an STD flash after your STDC out statement. And we are going to play with this in a minute in Visual Studio Code, and you're going to see how this works. Another manipulator we have, which is really cool, is set width. And it is STD set W here. And what it does, it specifies a width for whatever text you want to print. Here we have two examples. The first one is our table that is not formatted well. And you see we just print out the data, and it is going to show up like we see here on the right. We can use STD set width to set the width of the text here. And for example, the last name here is going to show up in a field which is 10 characters wide. This is what we mean here. And we do the same for the first name and the age. And if we do this, data is going to show up nicely as we see here. And again, I hope we agreed that what we have down below here is much better than what we had here, which was not formatted with set width. And this is how you use this manipulator here. We can also use what we call justification to control whether our data shows up on the right or on the left in the width that is allocated to it. For example here, the justification is STD right, so the data is going to show up to the right in its respective cells. We can also use what we call internal justification, by which if we are showing a negative number, the sign is going to be left justified, so it is going to show up on the left, but the data is going to be right justified. And this may come in handy if you want to display some tabular data in your terminal. We can also use STD set field to specify the field character in our empty spaces. For example, here we set the dash as our field character, and the result is what you see down below here. We have seen STD bool alpha, and its effect is to force STDC out to show Boolean output in the form of true and false. If you don't put this manipulator in, you're going to see those pieces of data as ones and zeros. So for example, here we have two variables, condition and other condition. If we print them out, they are going to show up as 1 and 0. We are going to set our manipulator here, so the data is going to show up as true and false. We can disable this manipulator here with STD no bool alpha, and the data is going to go back to be shown in the form of 1 and 0. This is what this manipulator does. We also have one to show the positive sign for positive numbers. So if we don't enable it, the data here is going to show up like this, 34 and minus 45. You see that the minus sign is going to be shown regardless of the setting you have for this manipulator. But if we enable STD show pose, we're going to show the positive number, and this may make sense for whatever application you might be doing. We can disable this with STD no show pose, and after we do this, the data is going to show up in its default format that we have seen before. This is how you use STD show pose. We also have manipulators to control the base in which the data is shown, and we can show the data either in decimal, in octal, or in hexadecimal. If you look at the data here, we have an integer which is positive, we have an integer which is negative, and we have a double variable here, and we have some data n for us to play with. We're going to show our positive integer in these three bases, decimal, hex, and octal, and the result is what you see here, and this should be no surprise. You already know these number systems and how they work. We can take the negative number and also show it in different bases, decimal, hexadecimal, and octal, and it is what you have on the right here in our terminal. If you go down and try to show a double or a floating point number in these bases, the result is not going to change because these number systems have no effect on floating point numbers. If you remember, we have seen that floating point numbers are represented in memory following another protocol that is really advanced for a course like this. So we are just going to use this, but we're not going to try and understand it because it is out of scope for what we are doing here. We can also use STD show base to show the base of our output. So here we have a positive number, which is an integer, and we can show it in decimal, hex, and oct. And we're going to see what we see here to the right, but we can choose to also show the base of whatever it is we output. If we want to specify that the output is in decimal, we're going to say that here, but we can also decide to show the base, and we enable that with STD show base like this. And if we do this, we're going to see decimal is not going to have anything in front, hex is going to have a 0x in front, oct is going to have a 0 in front, and by this, it is going to be very easy to see the base in which your data is displayed. We can also use STD uppercase for the data we print out to be shown in uppercase where it makes sense. For example, here we are trying to print numbers in hexadecimal here in the middle. So if we don't use uppercase, which is the default, the number is going to show up like this. You see A and F are lowercase, but if we enable uppercase, we're going to see this in uppercase. And sometimes this is going to be helpful for whatever application you are using this in. We also have a few manipulators to control how floating point data is shown on the terminal, and the two of these are STD scientific and STD fixed. By default, STD out is going to show in scientific format where necessary, and it is going to use fixed by default. So what we have here, we have three variables, A, B, C, and if we just print them out, they are going to show up in this format here. If we use fixed, we're going to force the output to be in fixed format, and you're going to see that the third number in C here is going to show up as 0.0 and a few zeros after that. Because in the precision that we have now, we can't really show a number that is as low as we have here in C. Again, we have seen this scientific format. This is basically 1.34 multiplied by 10 to the power of minus 10, and this is a really, really low number. So we're going to do 0.000 up to 10, and that's when this decimal point is going to show. So it's a number that is really close to 0. That's why we are showing it like 0.0 here. I hope this makes sense. We can also use scientific notation if we want that, and if we force scientific notation, everything is going to be shown in scientific notation. Another thing that I really want you to be aware of is that there is no official way to set the floating point output to its defaults. And here is a hack I actually learned about when I was making this course. The explanation of this is really out of scope for this course, but just use this to set the floating point output format to the defaults. And if you do this, you're going to get whatever we had here with the defaults. You're going to see that it is the same things. The next thing we're going to look at is STD set precision, which we have seen before, and this is going to set the precision with which the data is going to show up on the terminal. If you use a precision of 10, that's what you're going to get here. Here you see that we have a double number. It is a number that has a lot of numbers after the decimal point. If we show it by default, it's going to show up like this. The precision is going to be 6. We can increase the precision to 10, to 20, and to 50, and it is going to show up at whatever precision that you specify here. Please note that this precision is going to be limited by the type of this A variable. If it is a floating point, the precision is going to be something like 7. We have seen that. If it is a double, the precision is going to basically double to something like 15. And if you have a long double, the precision is going to be something bigger than double, but it can't go below that of a double. We have seen this before. We also have show point, which is going to force showing the decimal point for floating point values. You see here we have a 12.0. This is the most important piece of data we have here. If we don't do show point, this is going to show up as 12 in the output here. But we can use show point to force for the decimal point to be shown, and you see that 12.00 here is shown. Another side effect of this is that show point is going to force the showing of trailing zeros, and it is what we see here in D, E, and F. We have seen a lot of manipulators. Here is a table that is going to show where many of these are going to be living. So if you need to use set width, this is going to be living in the IO manip header. And here we have a few other ones. So if you want to use a few of these things, these are the libraries that you will need to include with #include, as we have been including IO stream. And again, the documentation for these things is shown at cppreference.com. This is the exact link, and you can check this out if it helps out. Now that we have an idea about these things, we're going to go in Visual Studio Code and actually see these in action. Okay, here we are in Visual Studio Code. The project we're going to be working on here is output formatting. So we're going to be grabbing our template files and put those in our project here. And we're going to go up again and open up this folder in Visual Studio Code. Let's do that. We're going to close the welcome screen here, and we're going to remove whatever it is we don't need. We're going to take this out, and we are going to put in the first code we want to play with, and this is stdendl. You don't really need a lot of explanations for this because we've used this all along. If you don't put it out, the data is going to show up on one line, and you're going to have hello world on one line. If we put stdendl like this, we're going to have the data show up on different lines, so we're going to have hello and world on different lines, and it is possible to use a \n to achieve the same thing, but these work very differently underground. And we don't have enough tools to really understand the difference, so for now, just take this as the truth, and know that there are differences. And the most important thing is that you recognize these things if you see them in code out there. We are going to bring up our terminal and build this with our task that is going to build with GCC. You're going to see that the build is going to go through, and we can run our rooster binary to see the output. You see that we have hello world on one line, we have hello and world on different lines, and this is a result of these events we have here. You see we have stdendl. This is going to force the terminal to go to the next line and print world, and after that we're going to force the terminal to go to the next line, and that's where the next text is going to show up. After that we have hello and world down here in the terminal, and it is the output generated by the statements that we have in here, and you can see that it is going to basically do the same thing as stdendl, but again they work very differently under the hood. Okay, so this is really how stdendl works, and you get access to it by including the IO stream library here. The next thing we're going to play with is std flash. This is going to flash the output buffer to its final destination, and that's going to be the terminal in this case. And if we add that to our stdcout statement like this, this is going to be directly sent to the terminal. And this may come in handy in some applications. If we run this, we're not going to really see a difference, but underground, under the hood, the data is directly sent to the terminal, and we had a chance to explain this in the slides earlier. We can build this program and see it running. The build is going to go through. If we run rooster, we're going to see that this is a nice message is sent to the terminal. The next thing we're going to look at is set width. I am going to put in the code here because I don't want to type all this. And again, you can get the source code for this in the resource section of this lecture. You don't really have to type all these things. The most important thing is that you really understand how they work. Okay, you see here we are going to use set width, but we haven't really included the library that is going to give us access to this. And if you don't know which library you will need to include to get access to this, well, you can check the documentation. And to get access to the documentation, you might want to consult your favorite search engine. I am going to go in Google here and type in std set W, and I am going to search, and this is going to come up with a few entries. I am going to click on the one from cppreference.com because this is reliable in my opinion. And if we open this up, we're going to see that to work with us, you need to include IO minute. So this is what we need to put in Visual Studio Code to get rid of this problem. Let's do that. I really wanted you to see this process you can go through to know what you need to include. We're going to put this in, and hopefully the error is going to go away, and we can focus on studying the effects of these things here. This is going to print unformatted, so the data is going to be cramped close to each other, but we can format this using set width. And if we pass in a 10 here, we are basically saying last name is going to take the width of 10 characters, even if we don't really have 10 characters in this. So you're going to have spaces fill the remaining spaces so that the data shows up nicely. This is really hard to say in words, so I am going to run this in a minute so that you can see this. But before we run, I want you to see that you can also store the width information in a variable like this, and I use that instead in your STD statements. The benefit with that is that it is really easy to change this width if you happen to change your mind. Otherwise, you would have to change a lot of things, and this is really bad design. I did this to show you how you can use this, but in real code, you are most probably going to store your width information in a variable, and that way it's going to be really easy to change and update with GCC, and if we run it, let's bring this up a little bit. We're going to have our data that is unformatted, and you see that it is really ugly, but down below here, we have our formatted table, and it is really nice. We have last name, first name, and age, and it is easier to see these things. We're going to see that it is possible to force the data to show on the left or to the right with justification, and we're going to look at code that does that next. If we go down here and put in the next piece of code we want to play with, we're going to see that data is right justified by default, but we have seen this also. You see that gray is cramped to the right of the width of the cell for the first name. So data is right justified by default. And it is the same here. If we change the width of our data here and try to run, we're going to have a better visualization of that. So let's run a little bit. We're going to build, the build is going to go through. And if we run this, we're going to see that data is going to show up to the right. Gray is to the right, woods is to the right. And this is the default justification you get when you set width like this. You can also code for the data to be left justified, and you do that by coming here and changing this to left. You can do that, but let's keep this in here instead for your reference, and let's put in another piece of code to justify the data to the left. Okay, let's go down and do that. We're going to justify the data to the left, and if we print this out, the data here, gray, should come to the left and be aligned with the first name here. I hope this makes sense. We're going to run. We build with GCC, and if we run rooster, gray is going to be justified to the left. This is the meaning of std left and std right that we just saw. And note that data is justified to the right by default, and it is important to keep the defaults in your mind. Data is going to be justified to the right by default. The next thing we can do is to make our data internal justified. And what this is going to do is make the sign left justified, and the data is going to be right justified. And the best way to see this is really to see an example. So here we have the data. It's a negative floating point number. The width is set to 10. It's going to be right justified, but we are also going to set the justification to internal and see the difference. Let's build and run this. We're going to build with GCC, and we are going to run our rooster program. And if we look at the output here, you see that if we have right justification, the sign is going to go with the data. Whereas if we do internal justification, the sign is going to go to the left and the data is going to go to the right. And sometimes this is useful depending on the application that you are building, especially in applications where you have to display tabular data on the console or the terminal. We can also specify the field character using set field, and this is really how it works. The data is going to be left justified, but we are going to fill empty spaces with a dash here. And we can bring this up so that you see the entire thing. But you don't really have to type this out. You can use the code I have provided in the resources section of this lecture. You can just copy it, paste it in here, and use it to play with these things. Okay, with this, our empty spaces are going to be filled with this dash character. Let's build, and build with GCC. We are going to run this, and you're going to see that we have our field character here, and you can change this basically to whatever you want. If I want, I can change this to a star. Let's do that, and I can build again. If I run this, it's going to be filled with stars right now. The next thing we're going to look at is std bool alpha. We have seen this before, but what it's really going to do is force the output to be in the format of true and false, and the default is in the form of 1 and 0. Here we have a few variables, and they are of bool type. The first set of stdcout statements here is going to print in the format of 1 and 0. We are going to set the output to bool alpha, and it is going to be in the format of true and false. And we can disable the bool alpha with this setting here, which says std no bool alpha. You can build this and see the effect of this. So we're going to run rooster again, and you're going to see that condition 1 0, condition true false, condition 1 0. We are able to modify how our Boolean data is displayed on the console using these two settings here. Use them if they make sense for your application. The next thing we're going to look at is show pos, and we're going to just put in the data. We have two numbers, positive number, which is 34, and negative number, which is minus 45, and we can decide if we want to show the plus sign for positive numbers. By default, the plus sign is going to be hidden. It's not going to be shown. If you want it shown, you can use the show pos manipulator, and if you want to disable that when it was enabled, you can use no show pos, and this is going to do what you want. We can build this again, and if we look at the output, we're going to see that posnum doesn't have a plus sign in front because by default the show pos is disabled, and we set the setting here, and we're going to see the plus sign, and if we disable that, we're not going to see the plus sign again. This is the effect of std show pos and std no show pos manipulators. We can also affect the base in which the data is displayed on the terminal, and we do this by setting the output base system. We can set std dec to force the output in decimal, std hex to force the output to be in hexadecimal, and std oct to force the output in octal. And this is only to take effect for integral types. This is not going to have effect for floating point numbers, for example. Here we have a few variables, a positive integer and negative integer, and a floating point number, which is the double. And we're going to try and print these things in all these base systems. We're going to print these things in the default format. We're going to see how they look. We are going to take the positive number and show that in these different number systems. We're going to do the same for the negative number, and we're going to show that this doesn't have effect on floating point numbers because these number systems don't really work for floating points. We can run this and see the output. We are going to run the task that is going to build with GCC, and we're going to clear and run rooster. And what we're going to see is that by default, positive number is going to be this, negative number is going to be this, and our double var is going to be this. And we are going to take the positive number, show it in different base systems. In decimal, it's going to be like this. In hex, it's going to be like this. In oct, it's going to be like this. The negative number is also going to be in this format here. So if we show it in decimal, it's going to be like this. Hex, it's going to be like this. And octal, it's going to be like this. You can see that the double var, which is a floating point, is not really affected. It's going to be showing in the same format regardless of the base that we set here. One thing you should know is that this base setting here is going to stick. So here, for example, you see that we have set output to octal. So any other thing that we're going to print out is going to be shown in octal. And we have to be sure that's what we want. If that's not what we want, we will have to reset the output number system, and it's going to take effect. This is how you can use these things to affect different number systems for output in your terminal. We have seen that you can also force things to show up in uppercase if that's important for your application. For example, here we have a positive number. If we show that in hex, this is going to contain a few characters, and if we don't set uppercase, it is going to show up in lowercase, and if we want it in uppercase, we can set this setting, and it is going to show up in uppercase. This may be helpful in some applications, and I just want you to be aware of these things. We're going to build and run our application. We're going to see that. Let's bring this up a little bit so that we have some breathing room. Our positive integer here is going to show up in lowercase here in hex because this is going to contain characters. And if we set uppercase, you're going to see that the characters are going to show up in uppercase. And this is the effect of this setting here. We can also affect how floating point data is printed out on the terminal. For example, here we have a few variables A, B, and C, and by default they are going to show up with decimal points and use scientific notation where necessary. But we can choose to use fixed, for example, if that's what we need in our application, and the output is going to be shown using fixed notation with decimal points. If we want, we can force the scientific format, and we do it like this, and all output is going to be in scientific format, and we can disable all these settings and reset this to the defaults with this piece of command here. There is no official way to set floating point output to the defaults, and this is a hack I actually learned about when I was preparing the code for this course, and the proper explanations for this are really out of scope for this course. So if you want to reset the floating point output format to the default, you're going to use this, but we don't really have enough tools to understand this yet. So just take it by faith, and you're going to see that if we run this, it's going to work. Let's try and run this through the compiler, and the build is going to go through. If we run this and bring this up a little bit so that we have a little bit of breathing room, we're going to see that our double values are A, B, and C, and that's what we have in our code here. And by default, it's not going to be able to show these things because of the precision limits. So we're going to have 3.14159 is going to go up to here, and the rest is going to be chopped off. If we use fixed format, you're going to see that whatever we had in scientific format, it's going to show up in fixed format. And again, this is a really low number. That's why we have 0.0000 here. We can force the output to be scientific as we did right here. And all output is going to be in scientific format. Down below here, we use our hack to set to the defaults. And you see that it's going to go back to the initial format that we had before. This is how you use std fixed and std scientific to manipulate how your floating point numbers are printed to the terminal. We have also seen that we can set the precision of our output in the terminal. Here we have a variable A. It is of type double. As you can see in a Visual Studio Code here, if you hover over a variable, you're going to be able to see its type. We can choose to see this in whatever precision we want. 6 is the default in our case here, but we can choose to set the precision to 10, 20, or whatever it is really we want. Please note that this is going to be limited by the precision that your type supports. So for example, we know that a double has a precision of 15, and if we have more than 15 digits in here, the rest is going to be garbage. Just be aware of that. We're going to try and build this, and we're going to use GCC as usual. And if we run this, we're going to get our numbers in different precisions. The first one is using the default, which is going to be 6. If we use 10, we're going to get 10 digits. If we use 20, we're going to get 20 digits. But if we go over the precision that our type here supports, we're going to get garbage. I hope this makes sense. The last thing we're going to see is show point, and we have seen that this is used to force outputting the decimal point. Let's say that here. And a good example for that is this 12 here. If we print it out here, we're not going to get the decimal point by default. It's going to print 12. But if we go down and force output of the decimal point, here we're going to get something like 12.0. And another effect of this is that it's going to add trailing zeros to fill whatever space is allocated for your output variable in the terminal. Let's try and run this so that we can actually see this running. We're going to run our rooster executable. And in the first group here, we don't have the setting for show point. And if you look at the numbers that we had in our code, the first number is 34.1, and you see that we are padding a lot of numbers because we had set our precision to a really big number in the last example that we have run. Let's actually go there and show you that. That's why we're seeing the precision of 20 It is really huge, but no big deal. We can reset this to whatever we want if this is too much for us. The important thing here is that we have 34.1 and that's what we are seeing. And if you go to our 12 here, so you see we have 12.0, but our output is not showing the decimal point here. If it is important to show the decimal point, we can do std show point here, and it is going to show up. This is really what is important in this piece of code here. And this is really all we set out to do in this lecture. We had a chance to play with a lot of these manipulators, and the best way to learn about these things is really to try them out in code and try to change a few things and see how that affects the output you get in the terminal. And we had a chance to play with many of these things in this lecture. There is a lot of these guys. I tried to make this lecture as extensive as I can. That's why it turned out to be pretty long. But once you've learned about these things and played with them in code, you're never going to forget them. One last point I want to emphasize again is that the documentation is of utmost importance. It is really good to come here and check things out. For example, if we go to show point here, we are going to get a nice explanation of what this manipulator does, enables or disables the unconditional inclusion of the decimal point character, and you can read all this. And the nice thing is that if you go down, you're going to have a piece of code that you can use to really understand whatever it is they are talking about. And this is priceless if you are learning. It is a good thing to be able to use the documentation. This is really all we set out to do in this lecture. It turned out to be really long, but I really hope it was worth it for you. We're going to stop here in this lecture. In the next one, we're going to learn about numeric limits. Go ahead and finish up here and meet me there. In this lecture, we're going to be playing with a few functions from this library. Specifically, we're going to be looking at the minimum, the maximum, and the lowest functions. And this is really how you use them. You can think of this t as a placeholder for the type for which you want to know the minimum, the maximum, and the lowest point, respectively. I know this might be cryptic to some of you, so we're going to look at a few specific examples. Here we have a simple explanation of what these functions mean for floating point values. The minimum is going to represent the smallest positive number that is representable with that floating point type. The maximum is going to be the maximum floating point number you can represent, and the lowest number is going to be the lowest negative number you can represent with that type. Things change a little bit when you start dealing with integers, and these functions are going to look like this. The minimum is going to be the minimum number you can represent with that integer, and lowest doesn't really mean anything for integral types. The maximum is going to be the maximum number. One thing you have to keep in mind is that the minimum may be negative if you are using a signed integer. If you are using an unsigned integer, for example, for short, minimum is going to be 0 and maximum is going to be the maximum number representable with that integer type. Here we are looking at numbers for short int, but the same story applies to whatever integer type you are using, even if you happen to be using long int or int without any modifier. Remember that we had to do a lot of things to get this range, and it was really hard to even do this for floating point types. So this library is helpful in getting a sense of what we can represent with a given type, be it floating point or integral. Let's head to Visual Studio Code and play with us. Here we are in our working folder. We are going to copy code from our template project, and we are going to go in the current project, which is numeric limits. We're going to go in, put in our files, go up and down, and open this file up in Visual Studio Code. We're going to close this up, open the main CPP file, remove whatever it is we don't need. We are going to include the limits library. Remember, this is the first thing we need to do if we want to play with these facilities that we just looked at in the slides. And we are going to go down here and put in the code we want to play with. And it is ridiculously simple if you have watched the slides we just did in a minute. So what we're going to be doing here, we're going to be printing out the range for each possible type we want to play with here. So we're going to say the range for short int is from, and we're going to say std numeric limits. Short, that's what we want to deal with now, and we're going to call the minimum function. This is going to give us the minimum value we can represent with short, and we're going to say std numeric limits, and we're going to call the max function, passing in the type for which we want to get the range for. And the same story applies for unsigned short. You see, that's the type we are using here. We are also going to play with int, getting the range. We're going to use unsigned int to see how these things behave. We're going to use long and get the range, and we are also going to be playing with floating point types. So we're going to compute the range using the minimum function and the maximum function, and we are going to be also using the lowest function to see that this really is the same thing we described in the slides. We're going to do this for double and long double and see how these ranges come up in this program. What we're going to do is open up a terminal here. We are going to run the test build with GCC, and the build is going to be good. And we can go down and run rooster, and we're going to get our values here. The range for short int is from minus 32768 up to 32767, and you see that this is exactly the same thing we saw in the lecture where we talked about number systems. We saw a way you can do this manually by plugging the number of digits in some formula that we came up. You can go back and check that out if you want. We do the same for unsigned short int, and then we look at floating point types. We're going to print the range for float, and if we use the minimum function to get the start of the range, we're going to get the minimum positive number we can represent with a float. If we use lowest, we're going to get the lowest minimum number, and the maximum is going to be the same. If you think this is really small, you have the option to open up this folder in File Explorer, and you can open a command prompt or PowerShell window by hitting Shift and right-clicking and choosing this option here, Open PowerShell window here, and you're going to get a bigger window in which you can type things. We're going to run Rooster, and we're going to see things in a much easier way here. This is an option you can use, or you can even use the integrated terminal inside Visual Studio Code here, like we've been doing all along. There are a few other facilities you can use in this library of limits. For example, we can try and print out if a number is signed or unsigned, or get the number of digits we can represent in an integer type. These are a few examples I just chose because they are easy to understand and really helpful, but you can find more about this library in the documentation. And if you come here at cppreference.com, the link is here, you can really find all about this library here. This library provides a standardized way to carry various properties of arithmetic types. For example, the largest possible value of type int is this, and we have a bunch of things we can do here. Don't be scared off by this template thing. Just think of them as placeholders for the type for which you are trying to query information for. There are a few functions you can call on these things. For example, there is min, lowest, max, that we just played with in Visual Studio Code, but you can see that there are a lot of things you can play with, especially if you have some math background to understand all these concepts here. You can play with this and see if it is helpful for whatever application you are doing. Okay, this is really all we set out to do in this lecture, to learn a little bit about the limits library. It is helpful in trying to understand the ranges for your types. If you happen to need these kinds of things, this is going to come in handy. We're going to stop here in this lecture. In the next one, we're going to learn about some math functions we can use in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about math functions. And these are functions that are built into the C++ standard library that we can use to do some math. If you are doing some math operations, you're going to find these helpful. They live in the C math library, and if you want to use them, you're just going to include that, and you're going to have access to them. What you see here is a simple summary of some of the things you can use in these math functions. You can use stdfloor to round down, or stdceil to round up. You can use the ABS function to compute the absolute value of a number. You can do trigonometry, you can do the cosine, sine, and things like that. You can compute the exponential of a number. You're going to see what this means in a few lectures. You can use stdlog. And again, if you have some math background, these concepts are not going to be foreign to you. Many of these functions are documented here at CPP reference, so it might be worthwhile to go there and check what functions are available there. Here is an example of something you might want to do. For example, you have a variable, it's called weight. Inside we have a 7.7, and if you do stdfloor of this variable, this is going to be rounded down to a 7. If you want to round up, you're going to use stdceil, and you're going to get that, and we're going to see what this is going to give us in a minute when we hit Visual Studio Code. Here is how you would use the absolute value function. You have a few variables here, and if you try to plug them in, this absolute value function, you're basically going to get the weight of the number without any sign in front of the number, positive or negative. The absolute value is the weight of the number without caring about the sign, if I may say it like that. Okay, we also have the exp function, which is going to compute the exponential of a number. This is a math concept, so if you don't have a background in math, this is going to be a little hard to wrap your brains around. But in math, we have this number, which is called e, and its value is approximately 2.71828, like you see here. The exponential function is going to do what fx here is doing. It's going to take e and elevate that to the power of x. And for example, in our code here, we're going to get the exponential of 10, which is going to be e elevated to the power of 10. And we're going to play with this in Visual Studio Code, and you're going to see the value of this. We also have the power function here, which is going to take the first parameter and elevate that to the power of the second parameter. So this is going to be 3 to the power of 4 and 9 to the power of 3, and we're going to get the answer if we plug this into Visual Studio Code. And we have log functions, which is basically the reverse of the power function that we just looked at. If you do log 8 in base 2, for example, it is like you are asking, to which power should I elevate 2 so that I get 8? And the answer here is going to be a 3, of course. But the catch is that the log function by default works in base e. So what we are asking, for example, if we say log 54.59 is to which power should we elevate e to get this number in here? And it is going to be computed, and you're going to see this if you plug this into Visual Studio Code, or you can try to use one of the calculators available to you, and you're going to see that this makes sense. We also have a special function that is going to do the same thing, but in base 10, and this is going to be easier to understand. For example, here we are computing log 10. So what we are really saying is, to which power should we elevate 10 to get 10,000? And this is easy because the answer is a 4. 10 to the power of 4 is 10,000. I really hope this makes sense. We also have a square root function we can use. So square root of 81 is going to be 9. We have a function called stdround, which can round. And what it's going to do by default, halfway points are going to be rounded away from 0. So if you have a 2.5, it's going to be rounded up to a 3. And if you have 2.4, it's going to be rounded down to a 2. We also have a host of functions we can use in trigonometry. We have a sine function, we have a cosine function, we have a tan function. If you know these concepts in math, this is going to come in really handy if you want to do this. I have to say that what we just talked about is a small set of what we can do with these functions here in CMath, and we are here at cppreference.com, and we can see all these functions here. We can do reminder, we can do fmin, and if you want, you can check these out in the documentation. For example, if you go to tan here and click on it, you are going to get the description and explanation of what this function does, and you're going to have a simple example of how you can play with this. Okay, now I hope you have a better idea of what we can do with these functions in the CMath library. We're going to head to Visual Studio Code and play with some of these functions. Here we are in Visual Studio Code. The current project we're going to work on is math functions. We're going to copy over our template files, and we're going to put them in our directory here, math functions. And we are going to open this up in Visual Studio Code, and we are going to remove whatever it is we don't need. And we are going to include our library, which is CMath, and we are going to put in our code so that we can play with this. And here we have a variable called weight, and we're going to try and use a few math functions on it. So we can use std floor to round down and std cell to round up. So weighted rounded to floor is going to be printed out, and weight rounded to cell is going to be printed out. We're going to have a number here. In this savings variable, it's going to be a negative number, and we're going to try and compute the absolute value of this. We're going to see it printed out. Another thing we're going to compute is the exponential of the value. We're going to do std_exp10, and what this is going to do is going to take e and raise it to the power of 10, and that's what we're going to get printed here. The other thing we want to do here is compute the power of a number. We're going to take 3 and raise it to the power of 4, and take 9 and raise it to the power of 3, and we're going to see what these things evaluate to. We're going to open up our terminal here, and we're going to run the task to build with GCC. The build is going to be good, and if we run Rooster, we're going to get these things here. So 7.7 rounded to floor is going to be 7, so we're going to round down. 7.7 rounded to cell is going to be 8, and that's what we're going to get. And the absolute value of weight is going to be 7.7 because it is a positive number, and the absolute value of minus 5,000 is going to be 5,000. And again, when you compute the absolute value of something, you are interested in the weight of that thing without considering the sign, without really worrying if it is positive or negative. You just want to get the magnitude of a number. That's what we use in math to mean that, magnitude. Okay, so if we go down, we're going to get the exponential of 10 is exponential, and you're going to get that here. And again, what this function does is take e and raise it to the power of 10, and that's the answer here. We can try and prove this with a calculator. So I am going to open my Windows calculator. You can use whatever calculator you have access to. I am going to use a scientific calculator here, and you see that we can hit E, and we're going to get the value of this E number in math. Here it is simplified, but if I take it and raise it to the power of 10, the answer is going to be 22.026. And if we look in our program, we have 22.026.5. Okay, it is rounded up a little bit, but it is almost the same thing. Okay, we also want to play with log functions a little bit. Log is basically the reverse of the power function, and we just talked about this in the slides, but if we do log 8 in base 2, we are basically asking to which power should we raise 2 to get an 8. And the answer to that is going to be what this log number in base number is going to evaluate to. The catch is that the log function, if you use it row like this, it is going to be using base e. And we just saw that e is 2 to the power of 7 or something. Let's go back to our calculator and see if we can see that. Why not? Why try to guess when we have a good calculator in our hands? We are using the scientific calculator, so if we hit e here, this is the value of e. Okay, so when we do log, we are basically asking to which power should we raise e so that we can get this 54.59. And the answer is going to be computed and printed out here. We have a version of this that is going to use base 10. So if we use this, we are basically saying to which power should we raise 10 to get 10,000, and the answer is going to be printed out here, and it is going to be a 4 because this is easy to do in your mind. So let's run this. We're going to build the task. We are going to run the task to build with GCC, and we're going to run our program, and we're going to get our output here. To get 54.59, you would elevate e to the power of this number here. This is the answer, and if you want, you can prove this with your favorite calculator. You're going to get something close to this. To get 10,000, you'd need to elevate 10 to the power of 4. That's what we're going to get in here. Let's print this out. Again, many mistakes. Sorry, but I hope you get the point. If we build again so that we can see things properly and run, we're going to get proper data, and this is really what we expected to get. We have a few more functions we can play with as we saw in our slides. Let's play with square root and the std round function. Here we are going to get the square root of 81. We're going to get it printed out, and we're going to see what std round does. It is going to round away from 0 if we are at half point, and if we are not at half point, if we are below that, we're going to round down. If we are higher than that, we're going to round up. We're going to run this so that you can see this running, and we're going to call rooster, and 2.5 is rounded to 3, 2.4 is rounded to 2, 3.6 is rounded to 4, This is what we expect, and the square root of 81 is 9. This is really all we set out to do in this lecture, to play with a few of these CMath functions. They are not really hard to use once you have the basics of math nailed down. And again, if you want to check the full list of these functions, please come to our reference documentation here.
Price range, and even more disturbingly, Satan was still there when we got outside. With time a serious factor at this point, we tried our luck in the most quintessentially American store.
Oh, Jesus. That's insane.
And we were in luck.
Oh, yeah, 98, mate.
Yeah, it's extremely Philly.
That's alright, mate. That's pretty good.
Yeah, that's like a good fit. Yeah, that's like a perfect fit.
Do you sell basketballs as well?
No.
Okay.
But you can go right down the street. There's a store called Five Below. They'll have basketballs, all types of stuff.
Great.
Or the Target down the block that way. Target will have all that shit.
I'm trying to save that money by going to Five Below. Target, a basketball.
So we do want a good one, actually.
They want a good one.
Maybe.
Yeah.
See?
Maybe Target.
They want a good one.
No bickering now.
Right? Receive the bag. Good luck.
Yeah.
Thank you very much.
Thanks so much, man.
Have a great day.
Yeah, appreciate it. Cheers, guys.
Nothing but net
Armed with a freshly pumped series ball from our friends at the Nike store and the name of a Philly legend on our backs, it was time to head out into the infamous Philly suburbs. We'd already been told by numerous people that we must not set foot in certain areas of Philly.
It is with a Macy's bag, mate. I know that. That needs to go right in the bin.
Right away.
The area that we had in mind was meant to be a bit rough around the edges, but we were hoping that it would be worth it.
Okay, here we are in Overbrook. It's not an area that many of you will have heard of, but it's actually home to the school, the high school, where many famous an NBL player...
MBA, isn't it?
Many a famous NBA player plied their trade, along with Will Smith, which is particularly relevant.
Okay.
And that's what we're gonna... Oh, fuck.
Around there, I think, so...
I'll follow you, mate.
Yeah, I think just this way, and hope that we're greeted with open arms, to be honest.
Well, that's the thing, like, this was the main question mark with this, is how are we going to be greeted? Are we going to find some friendly, not too dodgy people who are going to embrace what we've got in store for them?
I think we're going to go with the idea that this is something that they love and spend most days doing.
Yeah.
And we just want to come and find out what it's all about and just...
Yeah, and just relate to them and just get their faces on YouTube, basically.
Yeah.
Have a good time.
Right, mate, I think it's time to get rid of that.
Get that right in the bin, mate.
Yeah.
See you later.
As you can see, we were itching to get on the court, and with darkness not too far away, we needed to get a move on.
Is Overbrook High School directly this way, though?
Yeah, I don't know.
Second line? Yeah. Make a left? Make a left.
All the way down.
Yeah.
The Domino's Pizza. That's what the Kobe Bryant gym, the thing at there.
Really?
Yeah.
Oh, perfect.
Awesome.
Yeah.
Having been put right, we had time to grab a quick drink in a local corner shop where we got an unexpected insight into the early life of the man himself.
Yeah, exactly.
That's partly why we're here.
Yeah.
Shoot some b-ball in West Philadelphia.
Yeah, even though we can't play, we're terrible.
Yeah, he graduated with my cousin.
No way. What was he like? Nice guy.
Yeah, he used to come to my house every day.
What?
Down the street, down the street.
That's amazing.
I wasn't born, so I couldn't meet him.
No, yeah.
Well, it's great to meet you.
Yeah, thanks a lot, guys.
Take care.
Thank you. Bye.
That was fast, man. You got it.
Oh,
Come on, you got it.
nice. Nice, man. Woo!
Yeah.
Just around the corner, though, the leafy suburbanness came to an abrupt end.
Greg, it's getting a bit rougher.
Rough. but
I think we took a wrong turn.
oh no, I remember the KFC.
I think that might be it.
Might be it. There's a park.
I think we found it.
Marching swiftly out of view of a street gang took us into a preschool.
You're going to find a lot of them, and if you want to see how to use one of these, for example, if you click on log 10 here, you're going to come here, you're going to get an explanation of the function, and even better, you're going to go down and get a nice piece of code you can play with and really make sense of what is happening in these functions here. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to learn about some weird integral types. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about some weird integral types. And what do I mean by this? Well, if you look here, integral types less than 4 bytes in size don't support arithmetic operations. And these are operations like addition, subtraction, multiplication, division. You can do these operations on those types. And here I have an example of some of those types. We have a car. It is 1 byte on those types. And here I have an example of some of those types. We have a car. It is 1 byte in size, and short int is 2 bytes in size on most processors. So you can't do arithmetic operations if your integer value is stored in these types. Why is that? Well, this has to do with processor design, and they decided to choose int as the smallest type, integral type, for which they can do these arithmetic operations. But compilers are really smart enough to notice if you are trying to do arithmetic operations on these types, and they are going to implicitly convert from these smaller types to int. And this is something you need to be aware of. If we look at this program here, for example, we have var1 and var2. They are stored in variables that are of type short int. And we have var3, var4, which are stored in a variable of type char. We can try and print their sizes, and we're going to get 2211 for these variables because a short int occupies 2 bytes in memory for my computer here, and a char occupies 1 byte in memory. But the catch is down here. If you try to add them up, the result is not going to be the same type as the things you added up. And you would expect auto to deduce to the same type as var1 and var2. And it's not. Result is going to be an integer because int is the smallest type for which we can support these arithmetic operations. So if we print the size of result 1 and result 2, we're going to get 4. But this is the behavior you're going to get, and we need to be aware of it. The same behavior can be observed on other operators that we will have a chance to look at in a few chapters ahead. And these are called shift operators. You use them to shift bits. But I don't want to talk any more about them because we're going to have a chance to learn about them in detail. Okay, now it's time to head to Visual Studio Code and actually see this in action. Here we are in our working directory. We are going to copy our template project. We're going to copy this, quickly put that in our folder on weird integral types. This is our current project here. And we're going to open this up in Visual Studio Code. We're going to open this up, and we're going to open our main CPP file, remove whatever it is we don't need. And we are going to put in our code. This must be very familiar because it is what we just saw in the slides. So what we are doing here, we have 4 variables. var1 and var2 are short int, so these are going to take 2 bytes in memory on my computer here. And char is going to take up 1 byte. And we're going to print their sizes. We're going to see them printed out. And we are adding things up here. We are taking 2 short int variables and adding them up. So what the compiler is going to do, it's going to take this, turn it into an int, and then do addition, and the result is going to be an int. The same story is going to happen for result 2 here. var3 is a char, so it is 1 byte in memory, but the compiler can't really add up integral types, which are smaller than 4 bytes in memory. So what is going to happen? var3 is going to be transformed implicitly behind the scenes to an int, and var4 is going to be transformed to an int, and then we're going to add that up, and we're going to store that in an int variable, which is result here. If we print this up, we're going to see that size of result 1 and result 2 is 4, and this is what we expect here. And this is a behavior you need to be aware of, because sometimes your application logic is going to depend on the size of data. If that's the case, you need to care about this, and if you don't know this, you're going to be beaten by this, and it is really hard to find problems like this. So what we can do is open up our terminal, and we're going to build this with GCC, as we usually do, and we can run our program rooster, and we're going to see that this is what we expect. var1 is 2 bytes in size, var2 is 2 bytes in size, var3 and var4 are 1 byte in size, but our result is 4 bytes because the compiler implicitly converted our operands here to ints to be able to carry out this arithmetic operation. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to try and recap what we saw in the chapter. Congratulations on hitting the end of this chapter, and this chapter was really about doing operations and manipulating the data that you have stored in your variables. The first thing we saw was that we could do arithmetic operations on the data. We can add things up, multiply, divide. We also saw the modulus operator, which may seem weird for beginners, but we had a chance to really play with us. After that, we learned about precedence and associativity. We saw that that's a set of rules we have to follow to know which operation to do first if we have multiple operators in our expression. We also had a chance to learn about prefix and postfix increment and decrement operators. We had a chance to do compound assignments, things like plus equal, minus equal, multiply equal, modulus equal. Now these things must be making sense to you. We had a chance to look at how we could compare things using relational operators like greater than, lesser than, and equal or not equal. We also had a chance to look at output formatting, and we saw a host of things we could do to make data show up better with STDC out. After that, we learned about numeric limits, and this is a cool way to know the ranges for your data types, but there are a host of other properties you can use in this limits library. We learned a little bit about math functions, and we played with things like the power of something, the exponential, the few rounding functions that we have in the CMath library, and now you must have a good idea about these functions that you can use to manipulate and do math on your variables. We ended the chapter by looking at some weird integral types, and the main message in that lecture was that you can't do arithmetic operations on data types whose size is less than 4 bytes in memory. If you try to do that, the compiler is going to insert implicit conversions, and if your application depends on the size of things, this is something you need to be careful about. Otherwise, you're going to have a hard time finding these problems. I would like to welcome you in this new chapter where we're going to be learning about a new way we can do things in C++, and we're going to be doing conditional programming. In other words, we're going to be able to do different things based on the conditions that we have set up in our code. Just to give you an example here, we have a few variables, they are booleans, and we have a few initializers in there. Red is false, green is true, yellow is false, police stop is true, and we can do different things based on these boolean conditions. For example, if the light is red, we may be told to stop. If the light is yellow, we might be told to slow down. If the light is green, we might be told to go and do whatever it is we want to do. So we're going to be able to do these kinds of things. And C++ provides different constructs to be able to do conditional programming in your C++ code. We just have one of them in this slide, which is this if statement here. This if keyword allows you to do things like this. We have a few others. We have the else keyword, we have the switch keyword. We also have a completely separate operator that is called ternary operator that allows you to do these kinds of things. And we're going to be learning about all these things and more in this chapter. We are going to start and learn about the if statement in this lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the if statement. And this is a statement that is going to allow you to do things based on some condition being true or false. Here is a simple code example. We have two variables, number 1 and number 2. And we have a statement here that is going to compare number 1 and number 2. And we're going to store the result in this Boolean variable that we have on the left. Then we're going to do something based on the value that we are storing in this result here. If the result in there is true, we're going to print number 1 is less than number 2. If the result is not true, we're going to say number 1 is not less than number 2. And notice in the first if clause here, we are testing for the case where the result is true. But sometimes we need to do something when this condition here is not true. One way to do that is to negate what we have here inside the if parenthesis and test for the reverse of whatever we have in here, if that is making any sense. If you look here, we are testing for the case where, if not, the result is true. And in other words, we are testing for the case where the result here is false. And we're going to say number 1 is not less than number 2. This is one way we can go about this. Again, the if statement is used to do conditional programming. This is the syntax we use to do it in C++. We say f, we put a set of parentheses, and inside the parentheses, we put the condition we want to test for. And after that, we're going to have a pair of curly braces. And what we have inside these curly braces is going to be the body of our if statement. And it is basically going to be the code we want to run if the test here is successful. We can also use an else clause to catch the case where the test hasn't been successful. In this case, we can say if result equals true, we're going to do something, and else, we're going to do something else. In other words, if result is true, we're going to say is less than. If it's not true, we're going to say is not less than. And this is a more compact way of doing what we just did in the slide here. You can also directly use your expression as a condition, and the requirement here is that the expression evaluates to something that we can treat like a Boolean, because the condition has to be a Boolean. It has to be true or false. Okay, here is another simple example. We have seen this in the last lecture. We have a few variables containing our conditions, and we are saying if the light is red, for example, we're going to do something. If it's yellow, we're going to do something. If it's green, we're going to do something. We can also nest conditions. For example, we can put our outer if statement, and inside that if statement set up other if statements. And if our logic needs something like this, you can do this, and you can take advantage of this to achieve whatever it is you want to do. In this case, if the light is green, we're going to fall in here, and we're going to do another condition. So if the light is green, and if the police officer has stopped you, you're going to stop. And if they haven't stopped you, you're going to go because the light is green. And you can do something like this. We can also use logical operators to kind of achieve the same thing. And we say, if the light is green and the police officer hasn't stopped you, you're going to go. else you're going to stop. And you can do something like this. And you see that you can combine the logical operators we've learned about with the conditional programming techniques we are learning about here to do really powerful stuff. And we're going to be doing this all over the place in the course. So we're going to head over to Visual Studio Code and play with us. Here we are in our working directory. We're going to be working on if statements, and we're going to grab our template project, the template files, I should say, and we're going to put them in here. And we're going to open this up in Visual Studio Code as we always do. So let's do that. Open folder, and we should fall in here and open our main CPP file. Let's do the usual and remove what we don't need. And we are going to put in our code so that we can really play with us. We have two variables in here, number 1 and number 2. They are integers, and we have the values 55 and 60 inside. We can do a comparison between these two variables, and what this comparison is going to yield is a Boolean value that we're going to store in our Boolean variable here, which is called result. And what we can do is use this to do some conditional programming. So we're going to say if the result is true, we're going to do something, and if the result is not true, we're going to do something else. And this is how we say it. This syntax here may be confusing to new students, but try to think of it, if not, result is true, and that's really the same thing as saying if the result is false. Try to spin this in your mind a little bit, and you're really going to understand. Okay, so now that you have seen this piece of code, try to guess what we're going to see if we run this. What are we going to see on the console? Okay, give it a try. So we're going to run this in Visual Studio Code. Let's open up a terminal first, and we're going to build with GCC as we always do. We're going to bring this up a little bit so that we have some breathing room, and we're going to run rooster. Let's see what we have here. We have result equals true, and that's coming from this statement here. And we have freestanding if statement, which is coming from here. And we have our meat of this program, what we really are interested in. We have 55 is less than 60. So our test here succeeded, and we fell in this body and executed this stdcout statement. That's why we're saying number 1 is less than number 2, and number 1 is 55, which is what we see here, and number 2 is 60, which is what we are seeing here. So what can we do to make the second statement here execute? You know, it is testing for the case where not result is true. So it's going to exactly do the reverse of what this test here is doing. And if this fails, this one is going to succeed, which is what we have now. So what we can do to really play with this, we can go up and change, for example, number 1 to 65. This is going to flip the order of these numbers, if I may say it like that. And if we run it, we're going to build with GCC and run this. We're going to see result is false. So result became false because number 1 is not less than number 2. So this is going to be false. And the test here is going to fail. Result is not true. So we're not going to go in here and look at here. If not, result is true. So result is true is false. If we negate this, this is going to become true. And this test here is going to succeed. And we are going to fall in here. Take some time to really understand this, and if you have a problem, ask me. I am going to do the best I can to help you out, but make sure you understand this, because this is really fundamental in your journey as a software developer, not just in C++. Any career, as a software developer, you're going to need to understand this. Okay, what we're going to do is comment out what we just did here, because we're going to see another way to do this, and we don't want to have noise output in our terminal. This is going to just make things hard for us to see. So what we're going to do, we're going to go down in here and put in another piece of code, and the result was commented out. We don't want to comment that out, so we're going to take this out because this is our condition. We're going to grab it and put that outside our comment section. This is going to do. And if we go down again, we're going to click on this file icon and give ourselves some more breathing room here. We don't really need to see that main CPP file anyway. So if we come here, we can use the else clause to test for the case where our condition fails. And if you look here, we are essentially saying the same thing. We are saying if result equals true, we're going to fall in here, and else, we're going to fall in here. So we don't need to do the double if statements that we just did here. And this is much more compact and easy to read. Let's look again at the numbers we have here. Number 1 is 65, number 2 is 60. This expression here is going to be false because 65 is not less than 60. We're going to have a false in here. And if we come down, result is going to be false. This is going to fail, and we are going to fall down here. We're going to say number 1 or 65 is not less than 60, which is what we have in our values. So we're going to build this again, and we're going to run rooster. That's clear so that we have some breathing room. We're going to run rooster, and you're going to see that 65 is not less than 60, which is what we expect. Again, if you go up and change these numbers to whatever you want, try to change these numbers to different values to see what you get as output. If we do this, we're going to see that number 1 is less than 60, so this is going to be true, and we're going to have a true in this result variable here. If we go down, result is true. This test condition here is going to succeed, and we are going to fall in here. Let's click in our terminal and hit enter. We're going to run rooster. We're going to see 55 is less than 60, which is what we have here. Okay, now I hope you have a better idea of how you can use the else clause to make your if statements really compact. And this is really cool. Okay, another thing I want you to see is that you can not go through a variable like this and use an expression as a condition directly. C++ allows you to do this. So what we're going to do, we're going to comment out what we just did. Let's do that. We're going to use a block comment. I hope you know how to use this already. and we're going to go down and put in our code. It is exactly the same thing, but we took the expression and put that in the place of our condition variable here, because this is going to evaluate to a Boolean anyway, so we can use this as a condition, and this is something very legal to do in C++. So if we run this, we're going to see, let's see what we have in the numbers. I have forgotten by now. So 55, number 1, 60, number 2. Number 1 is less than number 2. This is going to be true. So the test here is going to succeed, and we are going to fall in here. That's what we're going to say. We're going to weld with GCC as usual, and going to clear and run rooster, and you're going to see that this is the output we expect. If we change up the numbers again, let's take this and make it a 75, number 1. So number 1 is less than number 2, is going to evaluate to false. The test here is going to fail, and we are going to fall in this block here. We're going to fall in the else clause of our test here. We're going to say 75 is not less than 55. Is that what we have in there? It's a 60. But this block here is going to execute. That's the most important thing. So we're going to run this, and we're going to try and clear and run rooster. We're going to get what we expect. This is one way we can do this, and it is really cool. Let's comment this out and see another example. And if we go down, we can see the example we saw in the slides, which was using red, green, and yellow to simulate a traffic light. So what we really want to see here is that we can nest stuff, but before we do that, we need to try and use these conditions because it is just fun. So if red is true, meaning that the red light is on, we're going to stop. If yellow is true, we're going to slow down. If green is true, we're going to go. And if we look at what we have here, red is false, green is true, false is true, and a police stop is true. Police stop is not really being used. So green is true, we're going to execute the green statement here, and we're going to say go. That's what we're going to say. Let's try and run this. We're going to build with GCC, bring this up a little bit so that we have some breathing room. And we're going to clear and run rooster, and you see that it is saying go here. You can try and change these Boolean variables to different things and see what is printed out here. This is a great way to learn. But what we really want to try here is nested statements, and let's go down and do that. Okay, so again, we don't want what we have on top here to disturb us, so we're going to comment this out, and we are going to go down and put in our code for nested if statements. So what we're going to say is if the light is green, we should go, but the police officer has the right to stop us even if the light is green. At least these are the laws in the country where I live. So we have a variable called police stop here. So if they stop you, even if the light is green, you're going to stop. And we're going to see what we see here. So if the light is green, we're going to fall in this body again, and we're going to run this inside or nested if statement. And if the officer has stopped us, we're going to stop. If they haven't stopped us, we're going to go and go on our merry way. This is what we want to see here. And again, I want you to stop for a moment, try to run this through your brain, and try to come up with the value we're going to see when we run this in Visual Studio Code. Pause for a minute. We're going to run this. We're going to build with GCC, and we're going to run a program, and you see that police officer stops, stop. And why is that? The light is green, okay, so we should usually go, but the police stop variable here is also true. So if we fall in here, this is going to execute, and it is going to succeed, and we are going to say stop. And once this statement executes, the else statement is not going to execute. Control is going to fall outside here, and we're going to keep doing whatever we have outside this if statement here. This is really critical to understand. If one block of any statement succeeds, all the others are not going to execute, and try to really understand this. Okay, we have seen this. We can now comment this out because we have something else I want to show you. We're going to comment this out. And that's that you can combine the if statements here or conditional programming with the logical operators we have learned about earlier in the course and do really powerful stuff. For example, here we can actually not use these nested statements and do this in one go like this. And I think this is much cleaner. So we're going to say if the light is green and the police officer hasn't stopped us, we're going to go. And if they have stopped us, we're going to stop. And you're going to see that we're going to get exactly the same result that we had before, but this is really much more compact. So we're going to run and see the result of this, and we're going to clear, and run rooster. We're going to see that they're going to stop us, and this is really cool. You can go up again and change up these variables to really anything you want and see what you get and try to really understand what is going on here. It is not difficult, and the if statement is really fundamental to any programming you're going to do. So this is really all we set out to do in this lecture, to learn about conditional programming using the if statement. It is a powerful thing, and you're going to see it all over your software development career, so make sure you really understand this. But even if it's not clear now, we're going to have a chance to do many examples, and you're going to really understand what this is all about. We are going to stop here in this lecture. In the next one, we're going to see how we can use the else if clause. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the else if clause that you can attach to your if statement. And that's going to allow you to test for several conditions in your if statement. And to really understand this, suppose we are building a drawing application, and at any given moment, the user might be using the pen or the marker or the eraser, or really whatever tool that it is we provide in our application. And if we want to draw, we need to know which tool is currently selected by the user. And we can do a piece of logic like this. We can have the tool stored somewhere in our application, and when we get to the moment moment where we want to use when the user clicks with their mouse and they want to drag and start doing things, then we're going to test for the current tool. If the tool is the pen, we're going to use the settings for the pen. If the tool is the marker, we're going to use the settings of the marker. And we're going to keep doing this and select one tool that is actually selected as the current tool by the user. And when you do something like this, only one block in this whole chain of statements is going to execute. So for example, if we have the marker as the current tool, the code inside this block is going to execute and say active tool is marker, but nothing else in this block is going to execute. After we run this statement, control is going to jump at the end of this whole chain of if and else if statements here. I really hope you understand this. And this is really powerful stuff. For example, this is one of the applications I have done in one of my advanced course about Qt and C++. Qt is a framework that allows you to do graphical user interfaces like this, and you can build applications like this. So what I did here is I did the exact same thing that we have here. I had a chain of if and else if statements, and whatever tool was selected as the current tool was used to draw things on the canvas here. For example, if the current tool was the pen, and the pen is this little pen tool here, if it is active, we're going to draw things like hello world here. If we have the star selected, we're going to draw stars. If we have the rectangle selected, we're going to draw rectangles. We could do all kinds of crazy things using this piece of logic here. But it is powerful stuff. And you really have to make sure you understand this. So this is how the else if clause can really help you. The main thing is to allow you to test for, really have to make sure you understand this. So this is with a lot of if statements, but that's not going to be really cool. It's going to be ugly and hard to read. This is what you should do. Now that you have an idea about this, we're going to head to Visual Studio Code and actually see this in action. Here we are in our working directory. We're going to grab our template project pretty quick, and we're going to use the else if project here. That's our current project. So we're going to do that and open this up in Visual Studio Code as we always do. We're going to open this up. We're going to open main CPP, and we're going to remove what we don't need. The first thing I am going to do is to put in a set of variables that are going to store our tools. And we can do something like this. We have a variable for pen, marker, eraser, rectangle, circle, and ellipse. I have to say that this is not the way to go about this. We're going to learn about another way we can do this, but that's going to be later in the course when we have enough tools to understand this. For now, we're just going to be happy with this. Okay, 10 is going to represent the pen, 20 is going to represent the marker, 30 is going to represent the eraser, and we can go on until we hit ellipse, which is represented by 60. Now, if we go in main and set up a variable and call it tool, for example, and initialize it with whatever tool we think that the user is currently using, for example, we can use circle, and initialize this, we can set up a chain of if and else if statements to do whatever it is we want to do when this tool here is selected. Okay, we're going to go down and put in our code. I don't want to type all this, so I'm going to put this up here. And if you want, you can copy the code from the resource section. The code is going to be there. You can copy it and paste it in here and do things with it. Okay, we have a chain of if and else if clauses in here. And the first one is going to test and see if the tool is the pen. And notice that we are using double equal signs here. This is what you use to test for equality. You don't use one equal sign, you have to use two equal signs. If you use one equal sign, that's going to be an assignment, and this is going to always evaluate to true, so you don't want to do that. Again, to test for equality, you're going to use double equal signs in C++. So if the current tool is the pen, we're going to say active tool is pen. If the current tool is marker, we're going to say that. So we are basically going to do this for all the tools that our application supports. So what do you think we'll see when we run this? The active tool is circle, so we should print active tool is circle here. Let's try this out. We're going to open the terminal so that we can see the output nicely, and we're going to build with GCC, and the build is going to go through. If we run this, we're going to see active tool is circle. You can go up here and change the tool to rectangle, for example. If you build again, you're going to see that the correct block of code is going to be executed. We're going to clear and run rooster. Active tool is rectangle. If we try to put in something that doesn't exist, let's put in bird, just to mess with our compiler here. We're going to get a compiler error because that type is not known by our code here, so we're going to get bird was not declared in this code. We don't know what it is. You have to put in whatever thing you have declared beforehand here. So if we put in eraser, for example, we're going to build with GCC. The build is going to go through, going to clear, run rooster. The tool is going to be eraser, and this is exactly what we expect. Again, the main message in this lecture is that you can use this else if clause if you have several conditions that you want to test for, just like we have here. And again, one of these blocks is going to execute, and once we hit the end of this chain of if and else if clauses, we're going to fall here, and code after that is going to execute. So let's say moving on, so that you can really see this here very clear. Moving on, and if we build this, we're going to see only one block from this whole chain. And once one block executes, control is going to go after all this chain and execute whatever is after that. So we're going to say moving on after we print that the active tool is eraser here. I think we have built this, so let's try and run this. And you see active tool is eraser and moving on. So after we print the code from the eraser block, we're not going to execute rectangle or circle or ellipse. It's going to jump at the end of this whole block. This is really what I want to be super clear. And again, make sure you understand the syntax here. The else if statement is followed by a set of parentheses. And inside the parentheses, we have the condition we want to test for. The condition has to evaluate to Boolean. And after that, we have the block of code that we want to execute. And this is really all you have to do to get this to work to your advantage. We are going to stop here in this lecture. In the next one, we're going to learn about switch. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the switch statement. And this is an alternative way to do what we did with these else-if clauses in the last lecture. Basically testing for several different conditions, but it's going to be in a much more compact way than what we did in the last lecture. We are going to be using the exact same example we did in the last lecture, and we're going to look at the switch statement and how it works in C++. And this is how it works. We have our variable, which is going to store the current tool, and we're going to say switch. Inside the parentheses here, we're going to pass the variable that we're going to be basically switching on or testing the conditions on. And inside the block, we're going to be basically testing for each case. So we're going to say if the current tool is the pen, we're going to say case pen. We're going to put a colon in here, and we're going to put the code we want to execute for the case where the current tool is the pen in these curly braces here. And one thing you should notice from the start is this break statement here. This is a statement that tells C++ that after we successfully execute a block of code, we're going to jump out of this switch statement. If you omit this break statement, everything after the case that you just executed is going to execute, and that's not probably going to be what you want. If this is not making sense yet, please bear with me. You're going to see it run in Visual Studio Code, and you are going to understand. So what you're going to do, you're going to put all the tools you want to test for in separate cases. You see here we have marker, and after that, you can put a default case that is going to be matched when nothing has been matched in whatever it
playground area where we felt pretty out of place.
We're just coming to look for a basketball court.
Then we saw it.
Oh boy. This couldn't be better. Or worse in a way. Oh wow, this is perfect. Hey man. Hi man. How's it going? Right, should we just get right in, man?
There was a family playing on the court closest to us, but the real action was going on over on the far court.
I feel like we want to get in with like the kind of like cool track.
We do, yeah, but we don't know.
And so it was time to see how our slightly strange offer would go down.
What we want to do is try and challenge some guys. We can't play basketball at all, just to stress that. What we want to try and do is get it in from the halfway line and challenge some like local guys. So I don't know if you guys would be keen for that.
Yeah, you do it. If you get it in before us, you can keep the ball. Yeah? And you'll be on YouTube?
Yeah.
That's the catch.
Welcome to any friends to join in, like a couple of us, and yeah.
Yeah?
What's your name, man?
Mo.
Mo, Greg.
Mo,
Nice to meet
I'm
you.
Tom.
What's your name, man? Omar, Greg.
Omar.
I ain't never shot a GoPro before.
Mo, who insisted he film some clips of the recently revamped courts, and his crew were quite reserved to begin with, but things loosened up a bit when we got onto the court.
Cool. What's your name, man?
Nate.
Nate, I'm Tom.
How you
Tom,
doing, Tom?
good to meet you, man.
Nice to meet you, Greg, man. Nice to meet you, Nate.
Yeah, I'm here. Good to meet you, man. I'm Tom. Okay. We're cooking now, we're cooking. Thanks, man.
No problem. I'm on here, go first.
Oh, he's hit the rim. Oh shit, that's in. Oh, okay, we've got to have a couple of goes.
Okay, you go.
This could be really bad.
This could be really bad.
Yes, sir.
So you push it from the back.
Yep. Run up.
Yeah, we need to run up, man.
Go ahead, Nate.
One of you guys is gonna do.
Oh!
Give me my ball. Give me my
Oh! First try. I got that on tape.
Let me see the ball.
I got that on tape.
Open the closed case, you already know.
That's it. Our work here is done, isn't it?
Yeah, we've done it. Well, we haven't.
I mean, unless anyone wants these, we could do another round. Oh, he's done it, mate, that's sick. The youngsters had made mincemeat of our halfway challenge, leaving us little option but to take things up a notch. So what we're saying here, you want the jersey, but it's got to be from the other side.
It's got to be from that point there. The heart, yeah, the heart is.
I'm not shooting from over there.
I back you, man. I reckon you can do it.
Yeah, I don't think I can do this.
Mine and Greg's only hope from this distance was using the overarm technique.
Nah, it's a lot harder than you think.
This is wishful thinking.
By this point, the big boys, whose game had thankfully come to a natural break, were starting to take stock of what was going on.
If anyone gets it from this line, they get the shirts.
Oh yeah?
Yeah, man. We don't need them. We haven't got room in our bags. So.
It's got to be from behind here.
Yo, look. My fault, bro. Oh, he made that.
Oh man, he's got the power. Gets one of our shirts. Yeah, man.
Check for me.
Oh man.
At this point, our original idea of alternating attempts by them and then by us was well and truly out the window.
Do you want to go?
Yeah.
But we were more than happy to stand by and watch as these guys got their eye in and relished our challenge. Greg tried his luck once, but we got the feeling that that might be our last attempt.
Oh! Oh! You're nearly there. Yes.
Come on.
Yeah, Tom, hold up. Let me give my shirt.
Which one's gonna fit you better, man? This one.
That was class.
Mate, you're famous. That's gonna be seen by 1 million people.
Yeah.
Is that all right by you?
That's cool. Yeah.
And with that truly sensational swoosh,
you have tested for in this switch block here. And when we run this piece of code, we're going to get exactly the same results that we had in the last lecture, but hopefully you can see that this is much more compact than the series of else-if clauses that we had in the last lecture. Again, the break state is much more compact than the series of else-if clauses that we had in the last lecture. Again, the break statement is really useful. If you don't put it in, C++ is going to be confused, and after you hit your successful case, everything after that is going to be executed. So the break statement is basically telling C++, if you hit it after a successful case is executed, jump out of this switch block because you are done. You don't have to do anything else in here. And another thing you should know is that the condition, which is what we have inside these parentheses here, can only be an integer or an enum. So basically it can be int, long, unsigned, or char, basically every integral type we have seen before, but it can't be another type such as a string because that doesn't really make sense. So be sure to keep this in mind. Now that you have an idea about this switch statement, let's head to Visual Studio Code and actually see this in action. Here we are in our working folder. The current project is going to be Switch, so we're going to grab our template files and we're going to bring that in here. We're going to go up a little bit and open this up in Visual Studio Code as we always do. And we're going to open up our main file. We're going to get rid of what we don't need. We are going to go outside the main function here and put in our tools, just like in the last lecture. We are using integers. Each one is represented by 10, 20, 30, up to 60. And these are the tools we have. And I don't think I explained this, but we are flagging them const because we don't want them to be modifiable. We have seen about const. earlier in the course. We are going to jump into main and set up our variable. It's going to be int, and we're going to call it tool, and we're going to initialize this whatever tool we want. Let's use eraser, why not? And then we're going to put in our switch block. We're going to say switch. To initialize this whatever tool we want. Let's use eraser, why not? And then we're going to put in our switch block. We're going to say switch, and if I type this, you see that Visual Studio Code is going to give me intelligence or suggestions on what thing I could do. One cool thing that Visual Studio Code does is give you snippets to really help you type things out. So we can click on this, and it is going to autocomplete a starter version of our case, and we can type in our expression here, which is going to be what we're going to be switching over. So we're going to switch over the variable tool here, and we can put in our cases. So in our case, we're going to start with pen, which is what we have here. So we're going to say case pen. We're going to remove all this. Let's remove this and say pen. We're going to put a colon, and we're going to put a block of code that is going to execute when the current tool is the pen, and we're going to put that in here. Let's bring this to the right a little bit, and inside the block we can say stdc out active tool is pen. Okay, so after that we're going to put this break statement. If it's not here, we're going to have a problem, because when the current tool is the pen and this code here executes, every case after that is going to execute, and that's not what we want. We have to remember to put this break statement here. Okay, so we're going to put in all our other cases. So we're going to copy this and look at the next one. It's going to be marker, so we can go on the next line and put in marker. We're going to paste this in. We're going to say marker, and we're going to say active tool is marker, and we can keep doing the same thing. We're going to go down there and paste this in. The next one is going to be eraser, so let's do that. We're going to say eraser, and we're going to say current tool is eraser, and we're going to go down again. I am doing this live because it really is important for you to see me type this. Otherwise, you may be confused, because this is a slightly confusing construct we have in C++. The next one is rectangle, so we're going to use that, and we're going to say current tool is rectangle. The next one is going to be circle and ellipse. So let's do that. We're going to put in circle. We're going to go down and paste this in, and bring this back a little bit. And we're going to say circle, and we're going to go down and put the next one in, which is going to be ellipse. And after that, notice that Visual Studio Code also inserted a default block, and this is a block that is going to execute when none of the cases here is hit. So this is really important. So you can also add a block of code and say no match found. Okay, so we want to see this print out, and we're going to try this out in a minute. Okay, after we do this, we should get to this to work and do whatever we were doing in the last lecture. So the current tool is going to be eraser. The block here is going to be matched, so code here is going to execute. After that, we're going to meet this break, and what it's really saying is, you have done what you have to do, jump out of this switch block here, and we're going to go to the end of this switch block, and we're going to execute whatever is after that. So just like in the last lecture, we can say moving on, and if we execute the program as we have it now, it's going to say active tool is eraser, and it's going to print moving on. Let's bring up the terminal so that we can really see this, and we're going to build with GCC. The build is going to be good, and if we run rooster, let's clear a bit. We see this, and we're going to build with GCC. The build is going to be good, and if we run rooster, let's clear a bit. We're going to see that active tool is eraser, and we are moving on. This is really cool, and it is exactly the same thing we had in the last lecture, but now we are using a much cleaner construct which switch provides. Okay, we can try to change the tool and see that this really works. We can put in circle, why not? We're going to build with GCC. The build is going to go through, as you see here, And if we run rooster, we're going to see active tool is circle. We are moving on. You can try and change this however you want. If we put in ellipse and build again, we're going to build with GCC. And if we run, we're going to get active tool is pen and moving on. Why is that? Ellipse, we are saying active tool is pen. We didn't change that. So we just code a really bad bug here. So let's fix this. And we're going to build again. I'm glad I found this. So we're going to clear and rooster. And we're going to see active tool is ellipse and we are moving on. Okay, so let's see what could happen if you forgot your break statement after your case here. So the current tool is ellipse, and it is the last thing we have in here, so it's not a good test case. What I am going to do is make the current tool the pen or the marker. Let's use marker, that's going to do. And I am going to remove the break statement here. Okay, so, and I am going to remove all the break statements we have until we hit the last default case. So we're going to go down, and we're even going to remove that for the default case here. And if we build, we're going to build fine. You're going to see that the build was good. But if we run this, try to guess what we're going to get. The current tool is the marker. So we should print marker and hit the end of the switch block and do moving on. But let's see what we get. Did we build? Let's build again just to be sure. So we're going to run rooster and notice what happens. Active tool is marker, active tool is eraser, active tool is rectangle. We basically print every other case after the marker case is hit. And if we try to change this, for example, not use marker and use eraser, let's change this. You're going to see that we're going to match the eraser case and everything after that is also going to execute, and it is not what you want. So let's clear and run rooster. You're going to see eraser, rectangle, circle, ellipse, and no match found. So you have ready to remember to put in these break statements. I am going to hit Ctrl Z a couple of times and bring those in, and I think this is enough. We have to hit again so that marker also has it. And if we run now, we're going to get what we expect. Let's try to use an eraser again, and if we build again and clear and run rooster, we're going to see active tool is eraser, and we are moving on. This is what we expect. Okay, this is really how you work with a switch block. You have to pass in your expression or your test case, and you catch each case using this case syntax here. You say case, you pass in whatever it is you want to match, and you put a colon, and you put your code inside this block here. And remember, after each case, you have to add this break. Otherwise, everything else after this is going to execute, and it is not going to be what you want. Before I let you go, I want to show you that you can actually group these case statements if this is what is making sense for your application. So for example, for rectangle, circle, and ellipse, these can be grouped into the group of shapes. So we can actually say case rectangle and put them on different lines, something like this. So let's delete this and say case rectangle, and we're going to delete the other things and say case circle, just like this. And we're going to say drawing shape. I think this syntax is supported in C++. Okay, so let's try and build. And we're going to build with GCC. And the build is going to be good. So if we have eraser, which is what we have in here, we're going to say drawing shape. Let's clear and run rooster. You're going to see drawing shapes moving on. We have grouped different cases and handled them with one block. And this may come in handy in some situations. One thing you should keep in mind is that there are limitations on what you can use as an expression or a condition in your switch statement. And that has to be an integer, something like int, char, unsigned, short, or things like that. We have seen all of these things. But it can also be an enum. But enum is something we haven't learned about yet. We will learn about it later when we have enough tools to understand that. But know about this limitation. So if we came in our project in Visual Studio Code, for example, and say std string name and say John, for example, and use this as a switch condition or expression, we have to include string for this to work. So let's go up and include the string library. We're going to do string. And if we go down again and try to do switch and use name as an expression and take out everything we have in here and try to compile this, you see that the compiler is not happy. Okay, it's going to say expression must have an integral or enum type. So this is not even going to compile. This is a limitation you have, and you have to make sure what you pass as a condition here is an integer. Something like int or char or other integral types we have learned about in this course. In this lecture, we're going to learn about ternary operators. And this is an alternative way to do tests with the if statement. Suppose here we have a variable called max. We have two variables called a and b, and we want to find the maximum between these two things. One easy way we can do this is say if a is greater than b, we're going to store the maximum in max, else then b is going to be the maximum, and we're going to store that in our maximum value, and we're going to print this out. If we do this, we're going to get whatever is the maximum between a and b to be printed out on the console, and this is going to work really well. But we can also use a ternary expression, and a ternary expression looks like this, and it starts with a pair of parentheses. You're going to put your condition inside the parentheses, you're going to follow that with a question mark, you're going to put your option 1, and after that you're going to put a colon and option 2, and because this is a statement in C++, we're going to end this with a semicolon. Here is an equivalent version of that using if, as we have been doing all along. So we say if condition result equals option 1, if condition is false, result is going to be equal to option 2. And this is exactly the same thing we are doing with our ternary expression here. If the condition is true, we're going to take option 1 and assign that to result. If it's false, we're going to take option 2 and assign that to result. So this is really a syntactic sugar or a shorthand for this thing here, and it's going to make your code shorter, and you're going to see this all over the place in C++ code out there. So you really need to be familiar with this. Okay, so here is our example of computing the maximum. You see that we have the same variables, max, a, and b, but we have a one-liner that is going to store the maximum and max, and we can print this out. And hopefully you can see that this is shorter and better than this. Okay, one other thing you should know is that option 1 and option 2 should be of the same type, or at least the types must be convertible. And if that fails, you're going to get a compiler error. We can also do ternary initialization. Here we have a boolean called fast. We initialize this to false. We can use this to initialize our speed variable here. We are basically saying if fast, initialize this with 300. If not fast, initialize this with 150, and we're going to print the speed here, and this is going to work. And here you see that I lied a little bit in my explanation to make it really obvious what we had in our ternary expression. You don't have to always wrap your condition in parentheses, but it makes the code much cleaner. Okay, now that you have an idea about these things, it's time we headed to Visual Studio Code. And actually tried this and solve for ourselves. Okay, here we are in our working folder. The current project is ternary operators. We're going to grab our template files and put those where they belong. It is in this lecture here on ternary operators. And we're going to open this up in Visual Studio Code as we always do. We're going to open this, and we're going to open main CPP and take out whatever we don't need. We are going to go down and put in our test code. We basically have a few variables. Let's kill these spaces so that our code is not cluttered here. And we're going to print our maximum. And we're going to be using a regular if. We have three variables, max, a, and b. We are saying if a is greater than b, we're going to store the maximum in max. Otherwise, we're going to store b in max. And this is going to allow us to print whatever is the maximum between 35 and 20. If we build this, let's bring up a terminal. And we are going to build with GCC, as we always do. Let's bring this up a little bit. And we're going to clear and run rooster. We're going to see that the maximum is 35. If we put our maximum in b, we're going to get the maximum still. So we're going to run the task to build with GCC. And we're going to run this, clear, rooster. Max is 200, so we're going to get the maximum regardless of where it is stored in A or B. This is how our code works, but we can use ternary operators to do the same thing. So what we're going to do here, we're going to comment out our if statement and use a ternary version. So what we're going to do, we're going to say result equals, and we're going to say A greater than B. We're going to put a question mark to signal the start of our two options. Option 1 is going to be A. Run this, clear, rooster. Max is 200, so we're going to get the maximum regardless of where it is stored in A or B. This is how our code works, but we can use ternary operators to do the same thing. So what we're going to do here, we're going to comment out our if statement and use a ternary version. So what we're going to do, we're going to say result equals, and we're going to say A greater than B. We're going to put a question mark to signal the start of our two options. Option 1 is going to be A, because if A is greater than B, then A is going to be the maximum. So we're going to grab A here, and if A is not greater than B, then B must be the maximum, so we're going to put that as a second option here. This is what we mean with this statement. And we don't have a variable called result, that's why we have a problem here. We're going to put our result in max, and this should solve this problem. You see these squiggly lines go away, and we can build this, and we're going to get exactly the same result. So this is our ternary operator. If we build this, it is going to go through, and if we run this, we're going to get exactly the same result. Max is 200, and it is what we expect. Okay, so take some time and really make yourself familiar with this syntax. It is really nothing complicated. You just have to make sure your brain is aware of something like this, and you're going to recognize it everywhere you see it in code out there. Okay, we have mentioned that you can't pass types that are not compatible, and the requirement is that A and B be of the same type, or at least types you can do conversions between. So for example, if we try to do something like pass a hello in here, we can't really turn a string into an integer, and this is going to give us a compiler error. And let's look at the error we see from Visual Studio Code. Operand types are incompatible, int and const char are not compatible, and they have to be compatible. If we ignore this and go ahead and build, we're going to also see an error from the compiler, and it should be the same error. So operands to question mark and colon have different types, int and const char, and they have to be things you can really compare. So for example, we can take out this string here and put in a floating point. Let's put in a 22.5 and say that this is a float. You're going to see that the problem is going to go away here. Let's wait for a minute. It's not going away. We're going to build anyway. You see the build is good. We're going to clear so that we don't have all this clutter. You see, problems went away. And if we build again, let's try to do that. The build is going to go through, and if we run this, we're going to get max is 22 because we are comparing a and 22 here. And the compiler inserted an implicit conversion from this floating point to integer. That's why we are seeing this here. So what is the type that the compiler really used here? Okay, to make it really clear what is going on, we're not going to use max here. Let's say auto max 1 and see what the compiler is really deducing to. So we're going to take this out, and by this we're going to see what implicit conversion the compiler really did here. Because what we had before, we were doing an assignment, so whatever was on the left was being turned into an integer because we were doing an implicit conversion from an assignment. So whatever is on the left is turned into the type of whatever we have on the left of the assignment. I hope you know this already. But if we do things like this, we're going to deduce whatever is on the left and assign that into max 1. So we're going to see the implicit conversion that the compiler did in here, and it is good to be able to see things like that. It is a curiosity thing. So let's see what happens here. We're going to print max 1, and we're going to build with GCC. This is going to go through, and we're going to see what is printed. So let's run rooster. And you're going to see that the implicit conversion happened from int to float, and we deduced the float here in max 1. So this is really interesting. One might have thought that we had a conversion from float to int, but it was actually the reverse, and this is quite interesting. This is really all we set out to do in this lecture. I hope you found it interesting. Again, make sure you have this syntax here drilled in your brain, because you're going to be seeing this a lot in your career as a software developer, not only C++ developer actually, and it is going to be helpful for you to know this. Congratulations on hitting the end of this chapter. This chapter was all about flow control, and we had the chance to learn about many of the tools that C++ provides to do conditional programming. And we were able to see all kinds of crazy things. We had a chance to do things like, if red is true, we're going to run the code inside. If yellow is true, we're going to run code inside. If green is true, we're going to run code inside. And we had a chance to play with those things on many occasions. We have seen that the tools that C++ provides really revolve around these four things here. We have if statements, we can do else clauses on these if statements, we can do else if to really do long chains of things where we do different decisions to do things in our applications. We also saw that switch is an option if you have several decisions you can make in your application. And we saw that a ternary operator can really be used to do two decisions. If you have two decisions, you're going to be able to reduce the number of lines you used to do these decisions to one line. And we had a chance to really look at that in detail in the lecture on ternary operators. This is really all I had to share in this chapter. I hope you found it interesting. We are going to stop here in this lecture. In the next chapter, we're going to start and learn about loops. Go ahead and finish up here and meet me there. In this chapter, we're going to be learning about loops. And this is a construct that is provided by the C++ programming language to allow you to do repetitive tasks relatively easily. Suppose we have a task to print a message 10 times. We can go down and do it like this, and it is going to work. But what if they try and tell you, do this 100 times? Then you're going to start scratching your head, you're going to type this 100 times, and you're going to run your program, and it is going to work. Then your manager comes up and they say, I want you to do this 10,000 times, or even 100,000 times. And then you're going to start pulling your hair or running around breaking things because that's impossible to do. Not to worry here. C++ provides a way to do this relatively easily, and we're going to be learning about ways we can do this in our program in this chapter. The constructs we're going to be using are these you see here. There is a for loop, a range-based for loop, a while loop, and do while loop, and we can make use of these tools to not go crazy printing a message 1 million times because that's really bad. Okay, so that's what we are up against in this chapter. We're going to be learning about these loop constructs, and you're going to find that they are really cool for your application. I am excited to be teaching you this, so let's get started in the next lecture and learn about the for loop. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about for loops. For loops are one of the constructs we have in C++ to do repetitive tasks. They allow us to do something like this much more easily. For example, we don't have to type stdc out I love C++ 10 times or 100 times. We can do this in less than 5 lines, and you're going to see how cool this is. The syntax for loops look like this, and it may look intimidating for first users, but we're going to break this down. We have a few parts in here. The first part is the iterator, which is a variable that we're going to be using to navigate through the loop. And that variable is this unsigned int I here. We are going to initialize this to 0, and the value we initialize this with is going to be our starting value. And that's another key point of it. The value we initialize this with is going to be our starting value, and that's another key point of any loop. Any loop is going to have a starting point. We are also going to have a test which is going to control when our loop ends. For example, this loop is going to start with I equal to 0. It is going to keep doing stuff until I is no longer less than 10. As long as I is less than 10, it's going to keep doing whatever it is we want to do. And the first part of the loop is this plus plus I thing here. And this is an incrementation part. That's how I'm going to call it for simplicity, but it is a part that keeps changing our iterator to make our loop move forward. After these 4 points, we are going to have a pair of curly braces, and inside these curly braces, we're going to have the body of our loop. And this is the code we want to execute multiple times. And inside this loop body, we can really do all kinds of crazy things. You're going to see how cool this is. Again, we have a few parts with our loop. We have our iterator, which is this variable I here. We're going to be initializing this with a value that denotes where we want our loop to start. We then have a test, which is going to control when the loop is going to end. We're going to have our incrementation part, which is going to allow our loop to move forward, and it's going to be doing that through incrementation or decrementation. But to make explanation easier here, we're going to call this part the incrementation part of the loop. After that, we're going to have the body of the loop, and it's going to be within these curly braces, and it's going to be whatever it is we want to execute inside this loop. Okay, these are the parts of a loop, and you need to keep this in mind. Okay, now that you know the main parts of a loop, how does it really work? Let's go through this and see how it's going to print I love C++ 10 times. So when this code gets executed, we're going to start with I equal to 0, because that's what we are initializing this value with. After the implementation part, we're going to run the test, and the test is going to say is I is 0 less than 10, and that's going to be true. So if the test turns out to be true, we're going to jump into the loop body, and if it's false, we're going to jump to the end of the loop and execute whatever is after our loop. This is how it works. So if we jump in for the first time when I is 0, we're going to print I love C++ for the first time. Then after the body is executed, we're going to execute the incrementation part. This is going to make I equal to 1. Then we're going to come back to the test. We're going to say is 1 less than 10. That's going to be true. We're going to come in the body and print I love C++ for the second time. After that, the incrementation part is going to run. We're going to have a 2 inside I here. 2 is less than 10. This is going to be true. So we're going to fall in the body again and print I love C++ for the third time. We're going to keep doing this until we hit 9. For example, if we increment and get a 9, we're going to fall in the test and say is 9 less than 10. That's going to be true. So we're going to fall in here and print I love C++ again. And after that, we're going to run the implementation part again. This time, I is going to become 10. We're going to do the test. 10 is not less than 10, so the test is going to fail. And we're going to fall on the outside of the loop here. And by that time, we'll have printed I love C++ 10 times. And this is really how a loop works. For the first time, we're going to run this initializer part here to initialize our iterator, which is this value I. And then after that, we're going to run the test. If the test is good, if it's successful, we're going to fall in the body. We're going to execute whatever code is in the body. And after that, we're going to keep doing the cycle, increment test body, increment test body, increment test body, until we hit a point where the test fails. And if the test fails, we're going to fall outside this for loop here. We're going to execute whatever is after this close-in curly brace. And this is how a loop works. I want you to go through this one more time by printing I love C++ and making sure that this is printed 10 times. And one thing you should have noticed now is that we use this test to control how many times the loop is going to start. For example, if we wanted it to run 20 times, we would start from 0 and end at 20. And you don't always have to start from 0. You can really start from anywhere. For example, you can initialize I with a value like 30 and end when I is equal to 55. Let's say that as an example. You can really do anything. The main important thing is to understand how a loop works. One thing, 2 or 3. I'm going to say is if the light is green, we should go, but the police officer has to get max is 22 because we are comparing. Be successful, and we're going to clear less than. We're going to go down and run and after that, it's not easy to follow this. And again, how this is going to work, we are going to run our code to declare and initialize the iterator. After that, we're going to do the test. We are going to start with I0, so 0 is less than 10. This is going to succeed.
That would have made Kobe proud. Our work was truly done.
Yo, pleasure.
No, yeah.
Pleasure. Cheers. Cheers for letting us do that. Thanks for letting us do that, guys. Thanks. Thanks.
Geo Wizard, right?
Geo Wizard, yeah. In December, this video will be released. All right, man. Yeah. Mate, we did it.
We did it, man.
Can't believe that. We came out to shoot some b-ball. Someone get it from the halfway line. Nearly the end of the court, man.
Yeah, nearly the end of the court. I mean, it's further than the halfway line.
That last shot by the guy in green was sick.
Just plopped in, all net.
Nothing but net.
Just unbelievable. We
Amazing.
were awful as well.
I got
mean,
nowhere near.
We didn't even hit the backboard.
Yeah.
Although, to be fair, we had like 2 shots, so.
Yeah, I thought it would be quite regimented, like we go, they go, we go, they go, like a competition, but no, they just lined up.
Yeah.
They were hungry for those Iverson shirts.
Isn't it Irving? Irving.
Sure. I hope I didn't say that too many times. Irving, yeah. J-man.
Dr. J.
Dr. Fuck's
Dr.
sake.
J.
Proper Philly experience that was.
Yeah.
A scary one.
Real Philly experience.
A scary one that still isn't over, but it was true Philly, that was wicked. That is a good chunk of our Philly checklist ticked off, man. Yeah. All we have to do now is eat a fucking cheese steak.
Cheese steak and
easy.
About it,
yeah.
Not only had we just beaten the darkness, which was something that we were very keen to do, but we'd completed the challenge that we were most nervous about. I mean, I'm not sure what Will Smith's exact definition of shooting some b-ball is, or whether this falls under that bracket, but all things considered, we were very happy.
So where are we going?
We're going to the birthday bar.
Specifically Ray's
Happy Birthday Bar.
Ray's Happy Birthday Bar, the most quintessentially Philly joint you could ever wish to go to. South Philly joint, right next to a big, infamous grilled, what is it?
Oh, grilled cheesesteak.
Fuck, sorry, I keep getting it wrong. Philly cheesesteak place, and we're just going to do both, aren't we? We're going to indulge in both.
Have a few beers.
A few beers.
Some live music.
Watch this particular band, who are literally carrying an amp all the way to the bar. Yeah, it's open mic night.
Yeah.
Let's have a good time.
No, my parents went without me.
You've never been in this bar?
I've never been here. I've been dying to go.
Just gotta hope that it's good then, haven't you? Yeah.
If it's not good, you can take it up with my aunt.
Okay.
And Ray, if you want.
Auntie who?
He's dead. Aunt Anna.
Ooh. Oh, Ray's dead?
Yes.
Oh shit, that's a... I was gonna say, where's Ray?
I was gonna say, mate, glad we got that bit of intel before going in.
Here it is, Ray's Happy Birthday Bar.
Look at that, man.
The bar was a proper locals dive. To give you an idea of how local it was, I was told to be quiet at the bar because everyone in the room was watching a game show called Jeopardy. So we joined in.
April is rustic, correct for 2000.
Really good. Cheers. April's is not. I'm going King George III, so we'll see.
Who is Prince Albert? Yes, Queen Victoria. Husband, Prince Consort.
Yikes, that's bad.
You guys should have gotten that one.
A couple of 100 years later than what I said, but this is gripping.
The open mic night in the other room wasn't quite as riveting, so we turned to the trustiest of entertainment sources.
Here we got Greg here playing GeoGuessr.
I hope he gets it still.
What do you reckon, guys? What do you reckon to that?
Got that and this kind of.
What are you thinking, Greg? He's never played GeoGuessr before.
Oh, go my heart.
This could be...
Oh, it was Estonia. It was Estonia.
I can't believe that. I thought that was Finland. Yo, genuinely, mate. I really thought that was Finland. I thought it was southern Finland.
So pretty much where I went.
Yeah.
Okay, so
we've got...
what's happening here, Tom?
We're kind of torn here. We've got Pat's King of Steaks. And we've got
Over there.
Gino's, which just looks
like a beacon of hope, really, isn't it?
So which one? I mean, Ella says they're both great, so...
Gotta flip a coin.
I think we've got to flip a coin, we've got to flip a quarter. Heads is Gino's, Tails is Pat's, because Pat is a woman's name, even though it's probably a guy. Here we go.
Go on then.
It's Pat's, unfortunately.
So I can't get anything annoyingly.
Oh, really?
Yeah, because that's the only one that does vegetarian.
Oh, we'll go Gina. Sorry, so what am I ordering?
So you're gonna want to get a cheesesteak, American way.
Cheesesteak.
We are going to follow in the body here, and after that we're going to print stdc out I love C++, and this is going to be 0. We're going to increment I, and we're going to do the test again. We're going to have to do is 1 less than 10. The test is going to be successful, so we're going to follow in here, and we're going to print a 1. And we're going to run the incrementation part again. We're going to run the test, and we're going to keep doing this until we hit a point, for example, when we increment this to be a 9. And after that, we're going to run the test. We're going to say, is 9 less than 10? The test is going to be successful, so we're going to follow in here, and we're going to print 9. And after that, we're going to increment again. We're going to run the incrementation part, and we're going to make I a 10. If we run the test, we're going to say, is 10 less than 10? The test here is going to fail. We're going to stop running the loop altogether, and we're going to fall on the outside of the loop and say, loop done. Let's say that so that we can see this on the terminal. And this is going to run and print I love C++ 10 times, and we expect I to go from 0 all the way to 9. Try to run this in your mind. Take a piece of paper, try to print this as you fall into the body of the loop. You're going to see that's exactly what is happening here. So what we're going to do, we're going to build this again. So we're going to run the task to build with GCC. The build is good. We're going to go down and run this. We're going to clear and run rooster. And you're going to see that we have 0, I love C++, all the way to 9, I love C++. Our loop is working exactly the way we want. Okay, so this is the first step. We are able to run our code a lot of times without really having to manually do things like this. And the benefit of this is that if we want this to run, for example, 100 times, all we have to do is change our test to go until I is equal to 100. And we're going to stop when I stops being less than 100. And if we run this, we're going to see the message from 0 all the way to 99. And this is pretty cool. The total is going to be 100 times. So let's build again to show you how cool this is. We're going to run this task to build with GCC again. And we're going to clear, run rooster, prepare to be amazed, run, and it's going to run all the way to 99. We can change this to even 1,000 or even 10,000. Why not? We're going to build again, and we're going to be successful, and we're going to clear and run rooster. And this is going to go all the way to 10,000 times. We're going to wait for this to get there. Now 3,000, 4,000, 5,000, 6,000. 7,000, 8,000, 9,000, 10,000. It's going to go all the way to 9,999, and it is going to stop. And the total of times the loop run was from 0 all the way to this stopping number here. Okay, now we can see that our loop is really working fine. We don't have to do these stdc out statements a crazy amount of times. Okay, and the benefit again is that regardless of the number of times the code here is going to run, our loop is going to stay relatively the same. It's just going to be 1, 2, 3, 4 lines of code, and this is really cool. Okay, so I think this now makes it very clear how loops work. So we're going to comment this out and show you another thing. And we're going to show you that you can use size t to actually denote the type of your iterator. And it is easy to do that. So we're going to say use size t. And for us to be able to see all this here, let's hit this file icon here to close this pane. And we're going to have a better chance of seeing our code here. So what we want to do, we're going to declare a loop. We're going to say for. We're not going to say unsigned, and we're going to say size t. And this is going to be the type of our iterator. We're going to say I. We're going to initialize this with a 0. And we're going to put a semicolon, like we just did. We're going to put in the end test. We're going to put in the test, so we're going to say I less than 10. No problem with this. And we are going to increment to put in place our incrementation part. We're going to follow in the loop. We're going to say stdc out. This is the code we want to run. So we're going to put in our current value for the iterator. And we're going to say I love C++ again. And we're going to put in our new line character. And if we build and run this, it's going to build and run the same. So let's say loop done here, so that we know when it's done. And we're going to build and run. We're going to build with GCC. The build is going to be good. And what we're going to do, we're going to clear and run rooster. And this is going to say I love C++ 10 times from 0 to 9. Again, the message here is that you can use size t to represent the type of your iterators. And this is a type that is even used in the C++ standard library. So this is going to be something people expect from your code if you are representing sizes in code that should be compliant with the C++ standard library. Nothing stops you from using unsigned int like we do here, but we're just going to follow the convention from the C++ standard library and use this type here to represent our sizes. And some of you might be wondering, how big is this thing? We have the tools to know how big it is, so let's do that pretty fast. So we're going to go down here and say stdc out, and we're going to say size of size t, and we can print this out. And let's say what we are doing here so that it is easy to use this code as the reference. And if we print this out, we're going to see the size of this thing on the system where this code here is going to run. So we're going to build with GCC again. The build is going to be good. We're going to go here and clear and run rooster. You're going to see that it is 8 bytes on my system. So you're going to have quite a huge range of numbers you can put in here, because this is going to only be positive. Okay, if you try to put in a negative number, you're going to get an underflow, and we have learned about overflow and underflow in a previous chapter. Okay, so let's comment this out and keep learning more things about for loops. Okay, the next thing I really want you to focus on and learn is the scope of the iterator. And we're going to grab our code again here so that we can use this as a learning tool. So we're going to go down here and put that in. And what we're going to have, let's move this a little bit to the right. I think we can do something like this. I am going to select the entire thing here and hit tab, and it is going to be aligned with whatever we have here. Okay, so we have our loop. It is going to run 10 times. It's going to print I love C++ from 0 to 9. But what is the scope of this I thing here? And the fact is, it is scoped inside this loop here. You might have guessed that. If you try to use it outside the loop, you're going to get a compiler error because it is only usable inside the body of the loop. You can also use it inside the control part of the loop here, but you can't use it outside the loop. So if you try to print I here, for example, you're going to get a compiler error. So let's try and do that and show you how wrong this can be. So if you try to print I here, let's say I, to make it clear what we want to print. If you try to do this, we're going to get a compiler error because I is not in scope. It is only in scope inside these curly braces that show the body part of our loop. Okay, Visual Studio Code is showing the problem here. It's saying I is undefined here, so you shouldn't really do this. But if we move on and ignore the message from Visual Studio Code and compile, we're going to get a compiler error, and it's going to say, I don't know what you're doing here. I was not declared in this scope where you are using it. And I think it's even going to give me a line number. It's going to tell me 46. That's where you are doing something wrong. And if we go in our code, we're going to see that this is the line where we are making the mistake. So I is not in scope here. We're going to comment this out and say compiler error, I is not in scope. That's what you're going to get if you try to do this. And the main message is that if you declare your loop like this, I is only going to be scoped in the body of the loop, and that's the only place where you can mention its name and use it. If we comment this out and build again, the compiler error is going to go away. You're going to see that the build is good. Let's clear so that our output here is good. We're going to build again and show you that the build is good, and this is really cool. Build finished successfully. Okay, this is one way we can set up our loop, but there is a way we can make our iterator usable outside the body of the loop, and we're going to show you how you can do that next. So let's comment this out and go down again, and we're going to grab the code because we don't want to type all this again, and we're going to say iterator declared outside the loop. We're going to go down and put in our code, and we're going to align this nicely, and we're going to take the iterator and declare it on the outside of the loop. So we're going to say size t, and we're going to say I and initialize this to 0, and we're going to say this very clearly, iterator defined outside, and we're going to say in our declaration part of the iterator, we're going to just say I, and this is going to work pretty fine. If we build this, you're going to see that the build is good, and if we run this, it's going to do the same thing it's been doing. It's going to print I love C++ 10 times, and if you want I usable on the outside of the loop, now you can use it. We can grab the code here that was failing in the last run of our code and put that out here, and we're going to align this a little bit. And if we compile this, the build is going to be good. And if we try to run Rooster, we're going to see I love C++ 10 times, we're going to say loop done, and we're going to print the value of I. And you see that if we do things like this, I is going to be usable on the outside of the loop body. And sometimes these may come in handy, depending on the logic of the application that you are designing. Just know that this is something you can do in your loops. Okay, you can go even crazier and leave out this iterator declaration part in your loop altogether, so you can remove that. And we're going to show you how you can do that in a minute, so let's comment this out. I don't want to remove code because I want you to have this as a reference if you need to look at this later. So we're going to say leave out, and what you can do is grab the code we had before. We're going to grab it, and we're going to paste that in here. And what we're going to do is take out this I. This can work, and you may see code like this out there in the wild. So we're going to run this test build with GCC. The build is going to be good, and we're going to clear and run Rooster, and it's going to do exactly the same thing. So this is one way you can set up your loops. Okay, the last thing we need to see about loops is that this test here is using a hard-coded value. And if we needed to change this loop to run, for example, for 1,000 times, we would need to manually hunt for this line of code, change this, and this is really not good design. So what is recommended is to store this value in a variable and test against that variable name instead. Let's comment this out and show you that. So we're going to comment this out and go down and copy this entire thing. I don't think I want to do my loops like this because this is really unintuitive most times. So I am going to declare my iterator inside, and I'm going to copy the code that does that here. We're going to go down and say, don't hard code values, okay? We're going to say that it's really bad, and we're going to go down and show you a better way to do things. And again, right now, we are hard coding again this value, but we can say const size t, and we can call this value count, for example, and we can initialize it with whatever we want. In this case, we want to control our loop to run 10 times, so we're going to put in a 10, and instead of hard coding and this 10, we're going to say count, okay? And if we build and run it, the loop is going to do exactly the same thing. It's going to print I love C++ 10 times, so let's do that. And run Rooster, it's going to do the same thing, but now we have one point of control. If we want this to run for, let's say, 100 times, we can change the count value to 100 times, and if we build again, that's how many times the loop is going to run, and this is much cleaner. So I do recommend you store the values you use in your loops in variables like this, and it's going to make your code look better. So it's going to run 100 times, and this is exactly what we want. This is really all we set out to do in this lecture. I hope you found it interesting. I am sorry that this lecture turned out lengthy because we had a lot of things to talk about, but now I hope you really know a lot of things about ways you can use your for loops to make them do things. And again, many loops that we're going to use in our C++ code are going to have 5 parts. We're going to have an iterator, which is going to be a variable we use to manipulate how our loop moves forward and does things. The starting point is going to be where the loop is going to start. We're going to have a test in place, which is going to control when the loop ends, and we're going to have the endpoint encoded in that test. We're going to have the incrementation part of the loop, which is going to control how our loop moves forward. And we are going to set up a pair of curly braces that are going to contain the body of our loop. In this lecture, we're going to learn about while loops. And this is another construct we have in the C++ programming language to allow us to do repetitive tasks. The syntax for a while loop looks like this. We have 5 parts in our loop. We have the iterator, the starting point, the test, the incrementation, and the loop body. It's just going to be set up differently for while loops. The iterator is declared on the outside. And you see here we have unsigned int I, which is exactly the same type of iterator we've used in the last lecture. But note that you can also use size t here. I am just using unsigned int for this case. After you have your iterator declared, you're going to fall to this part here and say while, open a set of parentheses, and inside you're going to put in your test. After that, you're going to open a pair of curly braces, and inside them you're going to put the body of your loop. And you're going to do whatever it is you want to do in the loop in there. And after your code to do whatever it is you want to do is executed, you're going to put in your incrementation part after your code, and that's what we have here. And this is the setup we're going to be using for our while loops. Again, we have the iterator declared on the outside, and we can initialize it with whatever it is we want to start with. Then we're going to put in our test. It's going to be within these parentheses. And after that, we're going to set up a pair of curly braces. And inside them, we're going to put whatever code we want to run in the loop. And then we're going to follow that with our incrementation part. And if we try to run this, we're going to run this line. We're going to declare the iterator I, and it's going to start with 0. So the test is going to run, and 0 is less than 10. And we're going to succeed. And we're going to run the body here. We're going to say, I love C++. And after that, we're going to run the incrementation part. I is going to become 1. We're going to run the test again. So 1 is less than 10. We're going to succeed. We're going to fall in. Print I love C++. We're going to increment again. Then we're going to have a 2 in I here. We're going to run the test again. We're going to say is 2 less than 10. That's going to be true. So we're going to be successful. We're going to fall in the body of the loop. We're going to increment and get a 3. We're going to test against our 3 value. 3 is less than 10. We're going to succeed. We're going to print I love C++. We're going to increment again. We're going to test again. And we're going to say is 4 less than count or 10. We're going to be successful. And we're going to keep running until we increment and get a 9. Once we get a 9, we're going to run the test again. And we're going to say is 9 less than 10. That's going to be successful. So we're going to fall inside. Print I love C++, we're going to increment and get a 10, and if we run the test again, we're going to say is 10 less than 10, that's going to fail, and we are going to fall on the outside of the loop, and we're going to run whatever code is on the outside here. This is really how a while loop works, and I hope you can see the similarities between the for loop we have seen. It is really the same thing, we just have different syntaxes to do these things. Okay, if you look at these things, we really have the same pieces of information, it is just different syntaxes that C++ provides to do the same things. And sometimes you're going to find it convenient to use while loops, and sometimes you're going to find it convenient to use for loops, and you're going to have to decide what works better for whatever it is you are working on. For now, we're going to head over to Visual Studio Code and try this out. Okay, here we are in Visual Studio Code. The current project is while loop. We're going to grab our template files, and we're going to go in our project and put those in. And we're going to open this in Visual Studio Code, so let's do that. We're going to open the folder, and we're going to work on while loop here. We are going to open our main CPP file pretty quick, and we're going to get rid of this. And what we're going to do is remove what we don't need. And again, we're going to show you the bad way to do things. You don't really want to do this manually. We want to print I love C++ 10 times. So we're going to build. Let's bring up a new terminal so that we can use this when we run things. And we are going to build with GCC. Let's do that pretty quick. The build is good, so we can clear and run Rooster. And we're going to have I love C++ printed out 10 times. So what we can do is comment this out and use a while loop like we want to do in this lecture here. And as we have seen with the slides, the first thing we need to do is declare our iterator on the outside. So we're going to say size ti, we're going to initialize this with a 0, and that's going to be our iterator declaration. And we're going to say while I is less than the value where we want to stop. And again, we don't want to hard code these values in, so what we're going to say is really const size t, and we're going to call this count and make it uppercase. This is a convention we use to declare constants in C++, but you don't have to make them uppercase. It is just a convention that is going to make your code easier to read for other people. So we're going to put a 10 in here because we want our loop to run 10 times. And we're going to say while I is less than count, and we're going to set up a pair of curly braces, and they are going to delimitate the start and the end of the body of our loop here. And inside, we're going to put in whatever code we want the loop to run multiple times. And the code is now very familiar. We're going to say stdc out, and we're going to print the current iteration. and we're going to say I love C++, stdendl for our new line character. And after that, we will need to put in our own incrementation part. If you forget that, you're going to get something really bad happen. We're really going to look at that later in the chapter, but for now, remember to put the incrementation part. And we're going to say ++I, this is really easy, and we're going to say that this is the test, and this is going to do what we want. But let's go down here and say that loop is done when it is done. So we're going to say loop done, and we're going to say stdendl. And before we run this, we're going to go through it and see how it is going to work. So let's click on this file icon here to close this pane so that we have some breathing room. I am going to open a notepad file we're going to use to see these things really happen. When this loop runs, we're going to initialize the iterator here. What we're going to do is put in a 0, and we are going to run the test to see if 0 is less than 10, and the test is going to be successful. So we are going to fall in here and say 0, I love C++. So let's say that here to make this super clear. Inside the loop, we're going to print this message 0, I love C++, and after we execute this line, we're going to increment. I is going to become 1. We're going to go up again and run the test, and we're going to say is 1 less than count, or is 1 less than 10. The test is going to be successful. We're going to run inside the loop, and we're going to print 1 I love C++. That's what we're going to do here, so let's do that. And after we do that, we're going to run our incrementation part again. I is going to become 2. We are going to run the test. We're going to say is 2 less than 10. That's going to be true, of course. And we're going to fall in the body again and say 2 I love C++. So let's say that. We're going to increment and we're going to get a 3. We're going to run the test again. The test is going to be successful because 3 is less than 10. We are going to fall in here and say 3 I love C++. Okay, so we can really follow this. And we are going to increment to get a 4. And the test is going to say is 4 less than 10. That's going to be true, so we're going to succeed and fall in the body again. And we're going to say 4 I love C++. We're going to keep doing this, and we're going to increment again. We're going to get a 5. The test is going to run again. We're going to say is 5 less than 10. That's going to be true, of course. And we're going to run the code to print 5 I love C++. We're going to increment again to get a 6. We're going to run the test. We're going to say is 6 less than 10. That's going to be true, of course, again. And we're going to print 6 I love C++. And we're going to increment to get a 7. We're going to run the test, our iterator. We're going to say is 7 less than count. That's going to be true. We're going to print the message again and say 7 I love C++. And we're going to increment again to get an 8. We're going to say is 8 less than count. That's going to be true. We're going to fall in the body and say 8 I love C++. We're going to increment to get a 9. We're going to run the test against our 9. Of course, 9 is less than 10, so that's going to be true. We're going to fall inside and we're going to say 9 I love C++. And after that, we're going to increment again and we're going to get a 10. Now, if we run the test, we're going to say is 10 less than 10. And that's going to be false because 10 is not less than 10. And if the test here fails, we're not going to fall in the body of the loop. Control is going to fall at the end of the loop body. And we're going to print loop done. That's what we're going to say here. We're going to say loop done. And our loop will have run 10 times by the time we print this loop done message here. If you count here, you see that the loop is going to run 10 times, and it is going to say, I love C++ 10 times, which is really what we want. Okay, I really had to show you this manually so that you can really see what is happening. But now we can build and run this and let the computer do the heavy duty of running this and showing us all these messages. So the build is going to be successful. Of course, we're going to run Rooster, and it's going to exactly show the same thing we just came up in our trusty notepad file here. You see, it is the same thing. But the beauty is that we don't have to do all these crazy computations again. What we can do is we can even change the count to 100, so it is going to run for 100 times. And that's pretty cool. So we can clear and run Rooster, and it's going to do that 100 times, and that's pretty fast for computers. This is really all we had to share with you in this lecture. The main thing is to learn about the syntax of a while loop. And again, notice that we have these 5 parts that make up our loop. We have an iterator, we have the starting point, we have a test, we have the implementation part, and we have the loop body. It is just set up differently with a while loop like we can see here. In this lecture, we're going to learn about do while loops. And this is yet another construct we have in C++ to do repetitive tasks. Let's look at the syntax here. We have our declaration of the iterator on the outside. And after that, you're going to say do. You're going to put a pair of curly braces like this. You're going to put whatever code it is you want to run inside the loop. And then you're going to do your incrementation. And after the closing curly brace, you're going to say while, and you're going to put in your test. This is really the structure. Again, notice that we have those 5 parts, and this is, you're going to say while, and you're going to put in your test. This is really the structure. Again, notice that we have those 5 parts, and this is the declaration of our iterator, and we're going to initialize this in place, for example, if we want to do that. After that, we're going to fall in the body of the loop, and after that, we're going to do the implementation. After we run the code, we want to run in the body of the loop, and then we're going to do the test later. And the special thing about a do-while loop is that it is going to run first and then do the test last. And this is really something you need to be careful about. Make sure that when it runs, it is doing whatever it is you want to do, because the test is going to run after your code has actually run. And you can tweak this to do whatever it is we want it to do, as we are going to see when we hit Visual Studio Code in a minute. Okay, again, one thing you need to keep in mind is that the do-while loop is going to run the body of the loop and then do the check or the test, and that may come in handy in some of the applications you'll be doing within your career as a C++ developer. Okay, this is really the syntax we're going to be using. We're going to head over to Visual Studio Code and play with us. Okay, here we are in our working folder. The current project is going to be do-while loop. We're going to grab the template files pretty fast, and we are going to put them in our current project. Let's open this up and put them in there. And we are going to open this in Visual Studio Code. Do-while loop is our project. We're going to open this, and main CPP is opened up. So let's remove whatever it is we don't need. And we are going to show you the bad way to do things. The bad way to do things is typing your code to do things manually if you want them to be done multiple times. And this is something bad. If we build this and run, we're going to go down and run this. Clear, not that's gibberish. We're going to run Rooster, and we're going to get I love C++ 10 times, and you don't want to do something like this. What we want in this lecture is to use do-while loops to solve this problem. We're going to comment this out because it is really bad. And we're going to go down and set up our do-while loop. The first thing we need to do is to set up the count, because we want to store this in some variable. So we're going to say constant count. And we're going to put in our value. Let's put in a 10, not 190. We're going to say 10 times. And we're going to set up our iterator. We're going to say size t. And we're going to say I and initialize this with our starting point. We're going to start from 0. And what we're going to do is say do and put a pair of curly braces. And inside this pair of curly braces, we're going to put whatever it is we want to do multiple times. So we want to print I love C++, so that's what we're going to say. We're going to put in the current iteration, and we're going to put a colon and say I love C++. And then we're going to jump to the new line with stdendl. And after that, we don't want to forget our incrementation part. So we're going to say ++i, and this is going to be the part that moves our iterator to the next step. This is going to be the incrementation, and this is going to be the iterator declaration. And after the closing brace, we need to say our test. So we're going to say while, and we're going to put in our test here, and we want to keep doing this as long as I is less than count, of course. And we're going to put in our closing semicolon here. Now, this code is going to run 10 times, but let's go through how it's going to run so that you can really see everything that is happening here. Okay, so when this code here is run, we're going to hit the initialization line here. We're going to declare I, and we're going to put in a 0. We're going to say do, and inside we're going to print whatever we have in I and say I love C++. So we're going to say 0, because I is 0 at this point, and we're going to say I love C++. And after that, we're going to increment. I is going to become 1. And we are going to do the test at this time. We're going to say is 1 less than 10. That's going to be successful. So we're going to run the body again. And we're going to say 1 I love C++. Let's copy this and print this again so that we don't have to type this all the time. We're going to say 1 I love C++. And after that, we're going to run the incrementation part again. So we're going to get a 2 inside I. We're going to test and say is 2 less than 10. That's going to be true. So we're going to run the body again and print 2 I love C++. And we're going to increment to get a 3 in there. We're going to run the test against our 3. Is 3 less than 10? That's going to be true. So we're going to fall in the body again and print 3 I love C++. Let's do that. We're going to do the incrementation. We're going to get a 4 inside this I variable here. We're going to run the test. We're going to say is 4 less than 10. That's going to be true, of course. We're going to say 4 I love C++ when we fall in the body again. We're going to do the implementation and get a 5. We're going to do the test. Is 5 less than 10? That's going to be true. So increment 11 I love C++. We will that we have done this, we can build this and let the computer do the heavy work for us and run these things multiple times. The build is going to be good. So what we're going to do, we're going to say clear and run Rooster, and it's going to say exactly what we expect. I love C++ 10 times, and then it's going to say loop done. Okay, one thing I want you to see is that the do-while loop runs before it does the test. And this may cause crazy things happening in your program if you're really not careful. Let's say that you wanted this program not to run and initialize this thing with a 0 for the count. So it's going to run 0 times. But that's not going to do what you expect with a do-while loop, because it runs things before it does the test. So if you run this program, it's not going to just say loop done. It's going to say I love C++ and have 0 value in here, and it's going to say loop done. But that's not going to be probably what you intended by putting a 0 in here. You put a 0 in here if you want this code to run 0 times, or the code in the body not to run. That's another way to say that. But in this case, a do while loop is not going to do what you expect because it runs before it does the test here. Let's build this and show you this. So we're going to go through, the build is successful, and we are going to clear and run rooster. You're going to see that it's saying 0, I love C++ loop done. It is running, even if we set our count to 0 here. So be sure the do while loop is doing what you want. But if you are careful about this, you're going to have no problems. And if you want the loop to actually not do anything, when you have 0 count in here, you can use the while loop or the for loop like we have seen before. I would like to welcome you in this new chapter where we're going to be learning about arrays. And arrays are a way to set up collections in our C++ program. So far we have been working with single variables. For example, you have a bunch of integer variables. You can even have 10 or 20 variables of integer type, and that's going to be fine. But sometimes you don't want to manage all these variables. It is really desirable to group all these variables into one single unity and manage them as one single entity. And we can do something like this, group them together and give them a name so that we can refer to them or manipulate them under this name here. And C++ has the array construct to help us do this. Okay, so again, if you look in memory how things are laid out, you're going to have a bunch of zeros and ones. For example, here, each read thing is an int. It is 4 bytes in size, and it can be used to represent an int. So if we have a bunch of ints like this, we might want to group them together and give them a name and manipulate them under this name. This is another way to look at what we just talked about here. And again, arrays are a way to do these kinds of things in C++, and we're going to be learning all about it in this chapter. We are going to stop here in this lecture, and we are going to start and look at how you can declare and initialize an array in the next lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can declare and use arrays in our C++ program. And again, arrays are a facility we have in the C++ programming language to group many variables together and manipulate them as a single unit. For example, here we have a bunch of integers in memory. Each of these read things is going to be 4 bytes in size, so you can think of it as an integer. And we can group them together and give them a name. We call them scores here, and they are going to be living under that scores entity. So if we want to refer to each of these things, C++ provides an indexing system, so we can use angle brackets like this and refer to the first of these integers as 0. So we can go from 0 all the way to 9 here, but your array can even be bigger than this, many times bigger than this. And we're going to see examples of how we can do that. But this is an example of how you can take many variables, group them under one entity, give them a name, and be able to reference each of these things that are under that entity. And now that the idea is pretty clear, let's see how we can do this in C++. The way to do that is to say int. You have to specify the type of your collection, you have to specify the name after that, and then you're going to put a pair of angle brackets like this. And inside those angle brackets, you can specify the size you want that collection to have or that array to have. And after this statement is run, we are basically going to have something like this in memory. We're going to have 10 integers, so if you count here, this statement is run. We are basically going to have something like this in memory. We're going to have 10 integers, so if you count here 0 all the way through 9, that's 10 integers. They're going to be grouped together under one logic entity. That logic entity is going to be called scores, and we can go through that name to manipulate all these things that are in this entity. Okay, after your array is declared and you have space for it in memory, basically something like this, we need a way to read data from it, and we're going to see how we can do that. And it is what we have here. For example, if we want to print the first of these elements, we're going to say scores, angle brackets, and specify the index of the first element in that array or that collection of integers that is called scores. Okay, one thing you should really keep in mind is that arrays are indexed from 0. They don't start from 1. So the first element is going to live at index 0. It's not going to live at index 1. So here scores 0 is going to print the first element, and scores 9 is going to print the last element, which happens to be the last in our collection here of integers. Okay, once our array is declared, it's not going to have data in it. There is going to be data in, but it's not going to be data that we put in. So we can think of this data basically as garbage. Another thing I wanted to bring to your attention is that your array has clear boundaries. When we declare an array like this, notice that we specify 10 as the size of our array. It's only going to have 10 elements inside. And you can see that we have from index 0 all the way to 9. And inside we have garbage data, but we're going to fix that in a minute. What I want you to see here is that you can't try and read outside the bounds of your array. C++ is funny in that it allows you to do that, but if you do that, you're going to get weird problems. For example, your program would crash or do something really bad, so you shouldn't really do this. Be aware of the boundaries of your array. If you try to read data from the outside of your bounds, you may read garbage data. You may even cause failure of the operating system because you don't really know whose memory you're reading. It's not going to be memory that is allocated to your program. So array boundaries are something you need to keep in mind when working with arrays. Okay, we just saw that we could read data from the array using this angle bracket syntax. We can even do that through the loops and read all the elements in the array. And this is how we could do that. And you can see that the loops we learned about in the last chapter are starting to come in handy. Okay, we have seen how we can read data from the array, but what if we want to put something back in? What if we want to write our own data in an array? Well, the syntax is pretty much what you would expect. We also use this angle bracket syntax, but we're going to assign data to that element in the array. For example, if we want to assign data to the first element in our array, we're going to say scores, angle brackets 0, and we're going to assign a 20 in it. And we can assign a 21 into the element at index 1 and a 22 in the element at index 2. And if we do that, we're going to have something like this in our array. So index 0 we have a 20, index 1 we have a 21, index 2 we have a 22, and the rest is still garbage because we didn't put in our data. We can also write data in a loop. For example, here we have our array declared, and we're going to loop around putting data at different indexes. Notice that the index is going to be the current iteration we are at, so this is a common way to do things in C++, and you need to be familiar with this. And after we put in the data, we can read that back and make sure that it is the actual data that we put in. And we're going to have a chance to play with this in Visual Studio Code in a minute, so don't worry if some of these things don't make sense yet. But again, the main thing here is this angle bracket syntax. We can use that to either write data in the element of the array or read data from the element of the array. And this is the syntax here, scores angle brackets I. Okay, so far our array has been declared and we didn't really put in data and there was junk data inside. But there's a way you can declare an array and put data in one single statement. And this is how you would do it. Here we have another array. It's going to be grouping double variables. We call the array salaries and we specify that it's going to be of size 5, and we can put these elements in a comma separated list using braced initialization like this, and it is going to work. If we try to print it out, we're going to see these elements here, and you see that we can read this using the same syntax we've learned about salaries. We say the array name, we do angle brackets, and inside we put the index of the element we are reading from, and this index is coming from our loop here, and it is going to work. You're going to get these elements printed out. This is pretty cool. When initializing your array, you can leave out elements. For example, here we have an int array. It is called families. It's going to be of size 5, but we are just putting in 3 elements. The rest are going to be initialized to 0 when we do things like this. And this is something you need to be aware of. And we are going to try this out in Visual Studio Code, and you're going to see that this is actually true. It is possible to also omit the size when you are declaring your array, and the compiler is going to deduce the size from the elements that you initialize your array with. For example, here we have in 1, 2, 3, 4, 5, 6 elements. This array is going to have a size of 6. And if we print elements, we're going to get those printed out. Notice here that we are using a ranged-based for loop, and hopefully you can see that it is easier to read data from a collection like this using a ranged-based for loop because we don't have to set up an iterator, initialize it, do the test, do the implementation. We can just read the value and use it and be on our merry way. This is pretty cool. It is possible to also declare your array constant, and when you do that, you won't be able to modify elements of that array. That's what it means if you make it constant. You basically want it to stay constant, and you don't want to allow modifications of your array. And we're going to see this in a minute when we get in Visual Studio Code. The last thing I want you to see is that you can actually do operations on the data that you have stored in an array. For example, here we can sum the elements up and store the result back in our variable sum, and this is something you would do, and it might come in handy in many times. Okay, one thing I want you to see before we head over to Visual Studio Code and play with us is that arrays store elements of the same type. Repeat after me. Arrays store elements of the same type. You can't try and store variables of different types in an array. I don't even know how you would actually declare that. And if you try and store a different type than the type that was declared for the array, you're going to get a compiler error. So this is something you should keep in mind, but it makes sense because when you declare an array, you're going to be given a bunch of bytes in memory, and those bytes are going to be collections of data that is of the same type. For example, here we have a bunch of integers. Again, each of these rate things is an integer, and if you try to put in something that is smaller or bigger than an int, then the compiler is going to be confused as to how to read these things. So for arrays to work, the types that you store in the array have to be the same, and they need to be consistent. This is something you should know, and if you try to break this rule, you're going to get a compiler error. Now that you know about arrays, we're going to head over to Visual Studio Code and play with them a little bit. Okay, here we are in our working folder. The current chapter is arrays. The current project is declaring and using arrays. We're going to grab our template code, and we're going to copy and move the files over. And we're going to open this thing up in Visual Studio Code pretty quick. We're going to open up the main CPP file and remove things we don't need. And we're going to see how we can declare an array of ints. Okay, the way you do that, you say the name of the array, and you put these angle brackets and specify the size of your array. If you want, you can put a space in here. It's really not going to make a difference. And you're going to put a semicolon at the end. The moment this line executes, we're going to have the space for 10 integers allocated to us in memory, and that space is going to be called scores, and we're going to be able to read data from it or even write data back into it. For now, let's see how we can read data, and it is really simple. We're going to use this angle bracket syntax that we just saw in the slides. So if we want to read the first element, we can say stdc out. We want to print it out, and we're going to say scores. Specify the index we want to read from, so we say 0, and we're going to say std endl to move to the next line. If you have this typed out, you're going to see that this is going to work, and it is going to print whatever is stored in the first element in this array here. And again, I want you to keep in mind the memory structure of your data when you are working with arrays. So what we're going to print right now is whatever junk data is in this first element here. Okay, in here we're going to say that we have in junk data. And let's bring up a terminal so that we can play with this. And we're going to build this with GCC as we always do. The build is going to be good, and we're going to clear and run rooster. You see that this is the junk value we have in here. We don't have any useful data in here. It's just junk data because we didn't initialize this array. We can also read the element at location 2 and see what we have in there when you run the program. I'm not even sure if it is guaranteed that you're going to get the same data if you run the program multiple times, but we don't really care. We know that it is junk data, so we can't use this in our program. What we're going to do is run this and see the value for the element at index 1. Let's build with GCC. The build is going to be good. We're going to clear, and we're going to run rooster, and you're going to see that at index 1 we have a 0 end. But doing it manually like this is really time consuming, and it is possible to actually do this in a loop. We know the size of this array, so it's a 10, and we can loop around 10 times, printing each element at each iteration. And the way we do that, we're going to read with the loop, and we're going to say for, okay, size t, and we're going to start from index 0. This is really important because arrays are indexed from 0. They don't start from 1 again. This is something you need to drill in your brain. And we're going to put in our test case, we're going to say I less than 10, because we want to go from 0 through 9. And we are going to increment our iterator. After we do that, we're going to have to jump into the body of the loop, and we didn't name our iterator. That's why we're having this squiggly line here. Let's do that really quick. We're going to jump into the body of our loop, and we are going to say stdc out, and we're going to say scores. And we need to be careful about how we format this because I is not something we have. We're going to be getting that from our iterator here, so we're going to print it like this, and this is going to work. No big deal. And we're going to say scores, and we're going to say I. That's going to be our index that we want to print the data for. And we're going to say std endl. And because we don't want this to confuse us, we're going to comment that out. And we're going to go up and make sure our comment is nice and neat. And we're going to try and run this. And what do you expect to see? Well, we don't have any real data in here. We're going to have some junk data, so it could really be anything we get printed here. So let's build with GCC, and we're going to give ourselves some breathing room. We're going to go down and clear and run rooster, and you see that this is really some junk data. And if we run it again, let's see that we get the same output. It is the same data in here. If we want to have in some reliable data, we need to write in our own data, and we're going to see how we can do that. We're going to see how we can write data into an array. And the syntax is really simple. So the way you do that, you just say the index for which you want to write data in, and you say scores, and you specify the index, let's say 0, and we're going to put in a 20, for example. This is how you do this. You say 20, let's say scores. We're going to grab the index 1, the first element, and we're going to put in a 21, why not? And we're going to say scores. We're going to say 2 for index 2, and we're going to put in 22, why not? And after we do this, we can print this out or read data with the loop and make sure that the data we did write in is actually in. So we're going to copy this and comment this out because we don't want this to confuse us on the console. And we're going to do that. We're going to come down here and print the data out. Let's say what we're doing here. And if we build this, we expect to see that at index 0, 1, and 2, we have the values 20, 21, and 22. Let's build and see. We're going to run the test to build with GCC. The build is going to go through. We're going to clear and run rooster. And look at this. Scores is 0, 20, scores. 1, 21, scores 2, 22, and our data is actually getting in. Now we're going to see that we can also write the data using a loop to make it really easy without us manually doing things like this. For that, we're going to copy what we have here to print data out, and we're going to comment what we had out here. So let's comment this out, and we're going to go down and print the data again. We're going to put in the code here, and before we print the data, we're going to put data in with a loop. So the loop is basically going to be the same thing. We're going to say size ti, we're going to initialize this, we're going to say I less than 10 because we want to loop 10 times. We're going to increment, and we're going to follow in the body of the loop. What we're going to do is write data at the index of the current iteration, I should say. So what we're going to do, we're going to say scores I, and we can really put in anything. For now, let's say we want to put in I multiplied by 10. So we're going to take the current index, multiply it by 10, and we're going to store that in the index at the current iteration. This is what we are doing here. And if we print this out, try to think about what we're going to get here. So at index 0, let's put in a 0 to be super clear here that we are starting from index 0. At index 0, we're going to take 0 and multiply that with a 10. So we're going to store 0 at index 0. The loop is going to run again. At index 1, we're going to take a 1, multiply with 10, we're going to get a 10. At index 2, we're going to multiply 2 with a 10 and store a 20 at index 2. And we're going to keep going and basically have 0, 10, 20, all the way to 90 stored in our array here. So if we print it out, we expect to see 0, 10, 20, all the way to 90. Let's build and see that that's actually what we have in our array. We're going to build successfully. Let's clear and run rooster. And you see that this is exactly the same thing we have in our array. How cool is that? Okay, another thing I want you to see is that we can declare and initialize an array in place. But before we do that, let's say what we were doing here. We were trying to write data in a loop, and we're going to comment this out because we don't want a lot of confusing output in our console. And we're going to go down and put in the data because I don't want to type all these things. So we can declare and initialize an array in place. And the way we do that, the array is going to store doubles now. We can really declare an array of anything, but so far we have seen that we can do that for int. Now let's try a little bit and show you that you can do the same thing for double types. So we can declare an array of double types. The size is going to be 5, and we're going to initialize that with this data here. So at index 0, we're going to have a 12.7, index 1 is 7.5, index 2 a 13.2, index 3 an 8.1, and index 4 a 9.3. And that's what we're going to have if we print this out. Here we have a simple loop to print it out, and it's going to basically say salary 0, 12.7, and it's going to go all the way to salary 4 and print a 9.3. And this is something you can do if it makes sense for whatever you are designing with C++. We're going to build this with GCC. Let's clear and run, and you see that this is exactly what we expect. Okay, now this is super clear. The next thing we're going to see is that if you don't initialize all the elements in the array, those you leave out are going to be initialized to 0. And we are going to put in a piece of code to play with that. So here we have an array. It's an int array. It's going to be called families, and the size is going to be 5. But we are only initializing 3 elements. And these elements are going to be elements on the front. So elements at index 3 and 4 are going to be left out, and they are going to be initialized to 0 by the compiler. So if we print this out, we expect to get 12, 7, 5, and 0, 0 at different indexes in this array here. Let's build this with GCC. We're going to clear because the build is successful, and we're going to run this. This is exactly what we expect. We have a 12, a 7, a 5, and the last 2 elements are initialized to 0, and this may come in handy sometimes. Okay, let's comment this out. Another thing we want to see is that we can actually omit the size when we are declaring our array and initializing it. So here is a simple example. We have an int array called class sizes. We don't specify the size, but we initialize it. And the compiler is going to deduce the size of this array from the elements we put in here. So if we put in 2 elements, so it's going to be of size 2. If we put in 10 elements, it's going to be of size 10. And this is how this works. But if you do something like this and not initialize the array, let's take this out, for example, you're going to get a compiler error because the compiler now doesn't know which size it's going to give to this array. So be sure to either put in the size or initialize your array like this, and it is going to work. In this case, we're going to have 6 elements in, and you see that a range-based for loop is going to come in handy here because we don't really know the size of this array. If somebody comes and adds in another element, let's say 23, the size is going to change, and if we hard-code the size in our for loop, the code is going to break. But a range-based for loop is going to use whatever size this array has. So we're going to try and build this. We're going to build with GCC, as usual. And the build is going to go through, if we run rooster, we're going to get the elements. We have 10, 12, 15, 11, 18, 17, 23. If we add a new element, this is going to work. You see that we don't need to modify the loop here to put in the new size. And this is really cool. I like this about range-based for loops. We're going to build again. And we're going to clear run rooster, and this is going to give us exactly the data we have in the array. So this is one way you can do things. Another thing we saw is that you can't modify const arrays. So let's do an example here. For example, we're going to grab this thing and put an array declared down here. We're going to copy that and use that here, and we're going to make this const. Let's give it a name. Let's say birds, for example. For example, we want to keep track of lines of birds or whatever. This is just an example to show you that you can't modify this array. So if you're trying to do something like birds and index 2, for example, and you want to change this to an 8, the compiler is going to complain. You see that Visual Studio Code is complaining already. Expiration must be a modifiable value, so it is saying that the array stores const elements, so you can't modify elements of this array. Okay, so this is something you can do if you don't want people to be able to modify data in your array. And the last thing I'm going to show you is that you can do operations on the data in an array. So let's bring up our scores array again. So we're going to go up and copy it because the code is using it. So let's put in our own scores array. It's going to be pretty fast. And we're going to say that it is an array with these angle brackets. We're going to initialize this. Let's put in a bunch of values. And what we can do is sum these things up. We're going to store our result in the sum variable. And we're going to loop around with a range-based for loop because we don't really know the size of this array. It can change anytime with however many elements. And a range-based for loop is really cool in that we don't have to keep track of the size ourselves. So we're going to go in here and get each element and add that to sum. So for example, for the first time, sum is going to be 0 because that's what we initialize it with. We're going to get into this loop here. The first element is going to be 2. We're going to add that to 0 and get 2. We're going to add a 5. We're going to get a 7. We're going to keep adding these elements. And at the end, sum is going to contain the sum of all these elements in the array here. And this is one cool way you can sum up the elements in your array. So if we run this, we're going to get the sum printed out. Let's do that pretty quick. We're going to run the task to build with GCC. And we have ourselves a compiler error. What is happening here? It's going to say redeclaration of scores. Where did we declare scores before? Let's go up and make sure it is not declared somewhere, and it is declared here. So we want to comment this out, come back to our code so that we can see it, and we're going to build again with GCC. And now the build is going through. We're going to clear, and if we run Rooster, score sum is 37. And if you sum these things up, I'm sure you get 37. This is really all we set out to do in this lecture. I hope you have a better idea of how you can declare your arrays, put data in, read data out of those arrays, make them const, or even do all kinds of operations on them. And this was really what this lecture was all about. We are going to stop here in this lecture. In the next one, we're going to see a cool way we can use to get the size of an array. Go ahead and finish up here and meet me there. In this lecture, we're going to see a way we can query for the size of an array at runtime. If you remember in the last lecture, we had an example like this, showing how we can declare an array and initialize it in a single statement like this. But the problem we had with this is that if we tried to print the array using a for loop, for example, we would have to use the size. And the size of this array may change if somebody decides to add elements or remove elements, then the size is going to be irrelevant. C++ provides a way we can query for the size of an array at runtime, and we're going to get the real size, accounting for the current number of elements that we have in the array. And for that, we use the std_size function. This is a function that comes with the C++ standard library, so you're going to have it already if you have a compliant compiler. If you see here, see that it was introduced in C++ 17, and it is a cool addition. We can use it to make our code easier to work with. If you look here, we have a simple loop, which is going to print data out. It is going to loop starting from 0 all the way to the size of the array. You see that we use this to control when this loop is going to end. We then put in our incrementation part, and then we jump into the body of the loop and print the current element in the loop. And if we do things like this, we're going to be able to print all elements in the array, regardless of the number we initialize it with. Okay, so this is one way, and it was introduced in C++ 17. But some of you must be asking, how did we do things before C++ 17? Well, we had to kind of do a hack to get something like this. We use the size of operator. We have seen a lot of times right now. And the way you use this, if you do size of and pass in the array, you're going to get the entire size of the array. So if we take that and divide that with the size of a single element in the array, we're going to get the number of elements of the array. And this is really what we are doing here. We are setting up a count variable, and we are taking the size of the array and dividing that with the size of a single element in the array, and we are just grabbing the first element because you can really use any element here. And once we have this, we can use this count to do a loop like this, and it is working pretty well. Please remember that you don't have to go through this craziness we're doing here. You don't even have to use std_size, because you can use a range-based for loop and get access to the elements you have in the array, and it is going to work pretty well. Now that you have an idea about this, let's head to Visual Studio Code and actually play with this. Okay, so here we are in our working folder. We are going to be working on this project, size of an array. We're going to grab our template project. We're going to copy the files and put them in place. And we're going to open this up in Visual Studio Code. Let's do that. It's going to open up in Visual Studio Code, and we're going to try and clean it up a little bit. And we are going to declare an array. If we want to print this thing, we need to know how many times we're going to loop and print elements in here. So one thing you might want to do is to say, okay, we have 10 elements in here, so I'm going to loop for 10 times. You might think this is going to work, and it is going to work. If we bring up a terminal and build this with GCC like we usually do, and clear and run Rooster, we are going to get our numbers. This is what we have in the array from 1 to 10. But what if somebody comes and changes the elements we have in here? Let's add an 11 and a 12. And the moment we change this, we will.
And what am I saying? Wit, and then American.
American wit.
This is your moment, mate.
American wit.
Yeah.
Okay. I feel compelled to do it in an American accent.
You're gonna have to. I think you're gonna have to. Go on, hit it.
Can I get a cheesesteak, American wit? Thank you. Did you have to burst out laughing? Yeah. Yeah.
Oh, sorry, I thought you said you want a veggie cut, as if that's like a specific thing. Thanks, man.
You Brits are so clueless.
Yeah.
And then one thing left to do, and that's to tuck in.
Yeah.
Well, Greg's already tucked in, fair enough. Here we go.
Big moment.
Damn, homie. That's some good shit. That's good. Can't lie. I mean, look at it. But it does taste good. It's got, the bread's got a good doughiness about it, good
It's
chewiness.
all about the bread.
9 out of 10 from me. Greg, how's yours?
A lot better than expected. Look at the density in there.
Cheers.
Cheers, mate.
And that is a wrap. That's pretty much Philly over, isn't it?
Pretty done. Right, Tom, how's that tasting, man?
It's I really appreciate this, Ella. Thank you.
Go on, go for another bite.
Dig in. You're so dramatic.
I do appreciate it. It's just very, very rich. I am Phillied out. I really am. I'm filled up and I'm Phillied out.
You don't need to finish it.
I will. I probably won't finish it. I'll probably get halfway down the shaft. And then let the white stuff ooze out.
No.
No, I don't know. I don't know, come on. I mean, what do you want me to do? Ella, thanks so much for having us and me. It's been really great. It's been a great Philly experience.
We'd heard negative things about Philly from folks from more northern climes, but I was very pleasantly surprised. Yes, it's a bit rough around the edges, but there was a charm that came with that, and a distinct identity that not many cities can really lay claim to. Regardless of what a nice time we'd had there though, things had gotten far too comfortable and predictable. It was time to leave the order of the city and head back out into the chaos of the countryside.
Okay, 5 minutes to go to get the train.
Thank you very much.
Great timing as always, Greg.
Timing, man.
Didn't get buried 10 feet under by Philly Tom.
Oh, he's there.
Oh God!
He's just there with like shovels.
Yeah.
There were just 2 events on this entire trip that we knew we had to attend. Events that would dictate that we be in a certain place at a certain time. One of them was a huge college football game and tailgate party down in South Carolina on Saturday the 24th of September, where we also hoped to crash a Red Cup party. And the other was a baseball game in Washington, D.C. on Friday the 16th, where we hoped to complete another ambitious challenge. Now, D.C. is less than a 3-hour drive from Philly, and we had over 2 days to get there. However, aside from our eagerness to escape the urban sprawl for a bit, there was another challenge on our list that could only be carried out in the luscious Pennsylvanian countryside that lay to the west of Philly.
We are heading into the heart of Amish country now. So anyone we see from this moment on could have a beard thicker than mine.
We'd been assured by several people, including Ella, that the town of Lancaster and its surrounding areas was the place to go if you wanted to meet an Amish person. So, with that in mind, this was our plan of action. We'd get off the train at Lancaster and begin our hunt for the Amish on foot, heading west along the old historic Lincoln Highway. Once we'd ran our errand, we would then attempt to hitchhike west towards the towns of York, Gettysburg, and Frederick. It was in Frederick that we had successfully sourced 2 bicycles on Craigslist that we planned to cycle to Washington on along the Potomac River Trail. The cycling part of this plan would be challenging, but it would be doable. However, with no guarantees that we wouldn't get stuck halfway to Frederick, and no idea where we were going to camp even if we did get there, it was today's aims that worried us most. It felt like we might need a bit of a helping hand. So this bike guy, the guy who we're buying the bikes off from on Craigslist, is increasingly showing interest in what we're doing, and it seems now he's actually heard of the channel. One of his hiking mates told us about it. So I'm really trying to butter him up, get him interested, because as it stands, we haven't got a
You'll need to come and change the size in here, and this loop here might be buried somewhere deep in your project, and it might not be as easy as it is now to see that we also need to change that. This may be a really big source of hard to debug problems. So what we really need is a way to get the size of the array at runtime and be able to dynamically query for that size and use it in our program. And that's exactly what std size provides. So we're going to say int count, and we're going to put in a value. Let's use a braced initializer. So we're going to say std size, and we're going to pass the array we want to get the size for. And if we do this, we're going to get this size here, and we're going to be looping for this number of times. So we're going to test for I is less than count here. And now it doesn't matter how many elements we have in here, we're going to get them at runtime. We need to only update this initializer here. So what we can do is build with GCC again. Now we're going to come here and run rooster, and we're going to get the numbers here. You see that we get all the elements. If we take out a few of these elements, let's take out a few of these. Let's leave in up to 7 or 8. Let's build again, and we are going to clear and run rooster. We're going to get however many elements we have in there, and this is pretty cool. Again, you might ask, how did we do things before C++ 17? Because std size was introduced in C++ 17. Let's say that here. Before that, we had to get the size of the entire array and divide that with the size of each element in the array. And we could use the size of operator to do that. So before we do any of that, we want to play with the size of method to really show you what it does. So what we're going to do is say std cout size of scores, the entire array, and we're going to print that, and we're going to say std cout size of, one element. Let's say scores, and use the first element. This is the easiest thing we can find here, but you can use any element. So we're going to say size of here, and we're going to say scores, and grab the first element, which is at index 0, and we're going to print its size. If we build and run this program, we're going to build and run, and the build is good. We can clear now and run rooster. You're going to see that we're going to get size of scores is 32, the entire array. The size of one element is 4 because we are storing in integers. And I want you to see that 32 is 4 times 8 because we have in 8 elements. So it's going to give you the combined size of all the elements that we have in here if you do size of an array. But if you do size of a single element, you're going to get the size of a single element. So C++ developers were clever enough to see this and see that we could use this information and get the count of elements inside. So we can do something like int count, and we're going to assign a value to this in our braced initializer. So we're going to say size of, we're going to say scores, and we're going to divide that with size of, and we're going to grab scores. We can really use any element in the array, but we're going to grab the one at index 0. And now we're going to get the count stored in our count variable without using std size, and we can uncomment our array here, or the code to print the array. And if we run now, it is going to work exactly the same thing regardless of the amount of elements you have in here. Let's put a few numbers randomly, and if we build and run, we are going to clear and run rooster, and we're going to get all the elements in here. And you can really use any of these techniques. Just choose what you feel works better for you. Okay, we are going through all this trouble to set up an iterator. We're going to do the test. We're going to increment. This is really too much work to try and get data from a collection like an array. So what we can do instead is comment out all this hard work here, and we can use a ranged-based for loop as we have seen before. And it is ridiculously easy and convenient to work with. So what you can do is say for auto I, we're going to do type deduction on whatever it is we have stored in our array. So we're going to put a colon and say scores, and we're going to print out the element. So let's do that. We're going to print std cout, and here we're going to say value. Let's say value in the array, and we're going to say I. And this is going to print all the elements, and we can work with the values inside if we want that. But you see that we have lost the information on the indexes. So if you really need the indexes, you will need to go through something like this. And if you just need the values in the array, range-based for loops are going to be really cool. Let's say range-based for loop. And if we build and run this, it's going to work pretty well. So the build is going to go through. Let's bring this up so that we have some breathing room. We're going to clear and run rooster. And we're going to get our elements printed out here. And you see that it is the exact same thing we have in scores here. So this is really all we set out to do in this lecture. I just wanted you to be aware of the std size facility that we have in the C++ standard library. If you don't want to use it for any reason, you can also go in and do the division we did here to get the count of elements in the array. And do your best to try and use range-based for loops because they make it easier and cleaner to get data from a collection like we are doing here with an array. We are going to stop here in this lecture. In the next one, we're going to see how we can work with arrays of characters. Go ahead and finish up here and meet me there. In this lecture, we're going to work on an array of characters and show how special they are. We can declare an array of characters just like any other array. So here we have an array called message. It stores elements of type character. The size is 5, and we initialize it with a bunch of characters. If we want to print it out, we can loop like we loop through any other array. In this case, we're going to be using a range-based for loop. We say for auto C, we pass the message, and then we're going to be printing each character in the message. And if we do this, we're going to see hello printed out on the console. We can also modify elements in our array. For example, we can say message1 and change the E here to an A. And if we print out, we should see hello printed out on the console. Nothing really special so far. The cool thing you can do with character arrays is that you can print them to the console directly without even doing the loop. You can do something like this. You can do stdc out, you say whatever you want to do in quotes here, and you're going to print the message. But sometimes this won't do what you expect because only proper C strings can be printed on the console. And what makes up a proper C string? A proper C string has this thing you see on the end here. This \0 is called a null termination string. And it is what is going to tell C++ that we have hit the end of the string and we are going to stop printing it if we are printing with things like stdc out. So this is really important to be in your strings. If it's not there, it may work, but sometimes it's also going to print some garbage characters after this, because what tells stdc out that we have reached the end of the string is this \0 here. If it's not there, it's going to keep printing until it sees one, and then you're going to probably have some garbage characters added to your string, and that's not what you want. So to have your strings printed out correctly, be sure to have in this null termination character here. And if we print it out, we're going to get it, and we're going to see the size printed out properly if we do things like this. But it is possible to get this autofilled for us. If you look here, we have a character array called message2. Inside we have said that we need 6 elements, and we say hello. So we have 1, 2, 3, 4, 5 elements, and the elements we don't initialize properly is going to be initialized with a 0 version of a character. And that happens to be the null terminator of the null termination character. So this is going to print correctly, and we're going to have the \n appended to this for us by the compiler. But be sure you understand the difference between this and this. Here we have specified the size to be a 5, and we are putting in 5 elements, so we have no null character appended to this string. But here we have said that we can put in 6 elements, and we have only put 5, and the compiler is going to autofill in the null terminating character. These two things are different, and make sure you understand the difference. Okay, so now take a look at what we have here. We have a string, we didn't specify the size, and we just initialize it with hello. Someone might think, this is also going to autofill, but it's not, because the compiler is going to deduce the size of this array using what you initialize it with. And you didn't put in a null character, so it's not going to be accounted for. You're only going to have this here, and if you print this out, you may get garbage characters appended to your string here, so be careful. But it is possible to do literal C strings and only say hello like this in quotes, and you're going to get the null terminating character appended to your string here. So if we print this, this is going to print nicely, and this is the recommended way to initialize your character arrays. If you want to put in string data like this, you have to use double quotes. And the cool thing about this is that you can even put in spaces between words like this. It is going to work. This really looks like how you would like to type text and store that in your character arrays. And we're going to be using this a lot in the course. Again, I want to bring to your attention that character arrays are special in that you can directly print them on the console like we are doing here. You see, this is a character array, and we are saying stdc out message 4. You can't do this with other arrays. And this is really all I had to share about character arrays. So what we're going to do next is head to Visual Studio Code and play with us. Okay, here we are in our working directory. The current project is arrays of characters. We're going to grab our template project, and we're going to copy the files, bring them in here, and we are going to open our folder. We're going to open the main CPP file, and we're going to get rid of what we don't need here. Let's put in some starter code so that we can start playing with this without typing this too much. So we're going to declare an array of characters. It's going to be called message. The size is going to be 5, and we're going to fill it with characters like this. So if we do this, we might want to print it like we print any other array. We're going to use loops, and in this case, we chose to use a range-based for loop. So we take auto C for character in message, and we're going to print out each character. Notice that we're not adding stdendl here because we want the characters printed close to each other so that we can read this easily. And after this, we will need to go to the next line so that the next thing we print doesn't disturb us. So we're going to say stdc out stdendl. And if we do this, we're going to see hello printed out on the console, but we had to do too much work to print something simple like hello. But let's do this. We are learning. So we're going to bring up our terminal, and we're going to build with GCC. Let's do that. The build is going to go through, and we're going to clear and run rooster. You're going to see that it's going to say message is hello, and this is what we expect. And this is really how you would declare an array of characters and initialize it with whatever it is you want to initialize it with. But you notice that it's really not convenient to put data in here. if you want to store a message, for example, for someone, you don't want to do this thing you see here. It's really ugly, it's inconvenient, and nobody would definitely use your program if you required your users to type things like this. So we need to change this, and we will. But before we get there, let's also see that we can change characters in our array. So if you look here, this E here is at index 2. So what we can say is say message, and we're going to target the element at index 2, oh, it's index 1. Let's use that. So this is index 0, the H and the E is at index 1. Let's make sure we get this straight. And we're going to store in an A in quotes. Remember, characters are surrounded by single quotes like this. Once we do this and we try to print the array out again using our technique here, we're going to copy the code and we're going to paste it down here just to do this simply. And if we do this, we're going to see the message printed out here to be hello. And the second message is going to be hello with an A because we changed the second element to an A. It's no longer an E. So that's what we expect. We're going to run the task to build with GCC, and we're going to bring this up and clear, and we're going to run Rooster. You see that we have message hello, and we are able to print things successfully. This is really cool, but we are doing too much work really to print something on the console, and there should be an easier way to do this, and there is. So what we're going to do is comment this out, because we don't want noise output in the console when we try to do something else. So what we're going to do is comment out all we've done so far. We're going to leave in our message here, and we're going to try and print it directly on the console. So we can say stdc out and say message, and we're going to print out the message. And take a moment and look at this and try to compile this. It is going to go through, it is going to compile, because C++ supports printing character arrays like this, but in most times this is not going to do what you expect. Let's try and run this and see what we get. We're going to run Rooster, and you see that we're lucky to get something that really isn't what we expect. It's printing hello, and you see that we have a bunch of other run this and see what we get. We're going to run Rooster, and you see that we're lucky to get something that really isn't what we expect. It's printing hello, and you see that we have a bunch of other things, and the reason is what we have discussed in these slides. For character arrays like this to be printed out properly on the console, they need to be null terminated. In other words, they need to have the null character, which is a \0, appended to the string for stdc out to know that it has reached the end of the string. So this is what makes your character strings legal. Now you see that we are getting a compiler error because we have overflown the size of the array. I think that's the message, too many initializer values, and this is exactly what we have done. Now we can try and change this guy to a 6 to say that we have 6 elements in here. This squiggly line should go away, and if we try to build and run, we're going to build with GCC. Let's bring this up a little bit, and we're going to clear and run Rooster now, and you see that now we have hello printed out correctly. If we turn this back to 5 elements and take out the null terminator, we're going to try and build again, and we're going to clear and run Rooster. You're going to see that we get the garbage back. So for your strings to be printed out correctly, they need to be null terminated. That's why it is not safe to print something like this when your character array is not null terminated. I really want you to understand this. So in C++, we have a proper name for these strings that are null terminated. A null terminated string is called a C string because these things come from the C programming language. Okay, and we're going to see a few ways we can set up C strings now. And the first one is to say car. We can call this message1, and it's going to be an array of characters. And we're going to initialize this with hello. Let's copy this because I don't want to type all these things here. So let's copy this and initialize this properly. Notice that we didn't specify the size, so the compiler is going to get the size from however many elements we put in here, and we're going to put in our null terminator here, and if we print this, this is going to work. And we are going to comment this out, and we're going to say that this will give you garbage. Okay, if we come down here, we're going to see that we have a car array. It is called message1, and we have initialized it with data. We have hello, and we have a null terminator here, and the compiler is going to reduce the size. So this is going to be a proper C string, and we will print it correctly. Let's try and build this. The build is going to go through. If we clear and run Rooster, we're going to get to a message here. And this is one way we can set up a proper C string. The second way is to actually not put in the null terminator, but let the compiler add that in for you. And the way we can do that, we can say car message2. And we're going to say this array is of size 6. Let's say that. We're going to put in a 6 and fix how we end things here. We're going to put in our code and end this with a semicolon. Now what is going to happen is the compiler is going to see that this array is of size 6, but we are putting in 5 elements. So the remaining slots are going to be autofilled, and it is going to be using null terminators to autofill this then. If we try to print the size here, we're going to get a 6 because the null terminator is added in by the compiler. Let's try and print the sizes here actually, so that you can see these things. So we're going to say size, and we're going to say that size of message 1, and we're going to put in a new line character, and this should be what we expect. So what we're going to do, we're going to copy this and put that down here, because we're going to be doing the same thing for message 2. So we're going to say message 2, let's select this, and say size of message 2, and do size of message 2. So what we're going to see is message 1 and message 2 printing out, and we expect to see a size of 6, because both of these guys have 6 elements inside. So we're going to run the task we built with GCC, and bring this up, clear, rooster, and this is exactly what we expect. Message 1 is hello, the size is 6. Message 2 is hello, and the size is 6. And these are a few ways you can declare your character arrays and initialize them with proper data that is going to print correctly with stdc out. Make sure you don't do something like we did here by printing message here, because it is not null terminated. This is going to give you a lot of problems. Again, I want to make it really clear that message 3 here is not a proper C string, because the compiler is going to deduce however many elements we have in here, and this thing is going to be of size 5. And we're not going to have a null terminator, and if we print it out, we're going to get some garbage. So let's try and copy this so that we are consistent with what we've done above here. And if we compile with GCC, we are going to compile successfully, but we may get weird things if we print out message 3 like we do here. And you're going to see that the size is 5 because we only have 5 elements in here. So let's clear and run rooster, and you're going to see that we have hello for message 1, we have hello for message 2, but for message 3, we have things we don't expect, because it's going to keep printing, and it's going to go overbound, and it's going to stop when it hits the first null terminating character like what we have in here. Okay, so this is not safe, don't do it. Make sure your strings are null terminated if you intend to print them with stdc out like this. Okay, so working with character arrays like this to print messages and do all kinds of crazy things is nice, but it really isn't convenient. As I said before, you wouldn't expect your users to type characters like this by surrounding them with single quotes. This is really ugly, and it is painful to do if you want to do some productive work. So C++ allows you to use what we call string literals, and we're going to see an example of that down below. We're going to say string literals, and what we can do is car message 4. It's going to be an array as usual, and we can initialize it with a string that is surrounded by double quotes. And what this is going to tell C++ is, you know, take these things, break it into characters, and store this in this array here, and make sure you properly null terminate this string here. So if we print the size of message 4, we're not going to get 5, we're going to get 6, because C++ is going to see these double quotes and know that we intend for these things to be properly null terminated, and it's going to add a null terminator. So let's try and print this out so that we really are sure, and we're going to build this with GCC as we always do. The build is going to go through, let's go up and clear, and we're going to run rooster, and you see that message 4 is hello, and the size is indeed a 6. So this is one way we have to do things, and we can even put spaces and do all kinds of crazy things, and it's really cool. And if we try to build this, we're going to get the proper message printed out. You see the build is good. If we clear and run rooster, we're going to see hello world, how are you doing? And this is really cool. So from now on, if we need to store a string in our program, this is how we're going to do it, because this is much more civilized, and it is how you would really like to type characters in your program. I have said that character arrays are really special because you can directly print them out with stdc out like this. I want to prove this, so we're going to try and declare another array. So we're going to call this numbers, and we're going to make this an array, and we're going to initialize with 1, 2, 3, 4, 5. This is going to do, and we're going to put our closing semicolon, and we're going to try and print this out. We're going to say stdc out and say numbers. Let's see what we get. Let's try and compile this and see what we get. It is not actually going to give us a compiler error, but it's not going to print what we expect. And let's put a message here so that we know that it is this thing we are seeing here. So we're going to say numbers, and we're going to put a column here, and we're going to build this with GCC, and we're going to clear. And if we run rooster, look out for the output that says numbers here. So let's run rooster. It's not a 1, 2, 3, 4, 5. It's something we don't really know, and we will get to understand what is happening here in the next chapter. For now, know that you can't directly print arrays other than those of characters. If you try to do that, you're going to get weird numbers printed out, and we're going to understand why this is in the next chapter. So let's say that here. Okay, this is really all we set out to do in this lecture. I hope you found it interesting. Character arrays have a few things you need to be careful about, and we try to cover those in this lecture. We are going to stop here in this lecture. In the next one, we're going to try and look at array bounds. Go ahead and finish up here and meet me there. In this lecture, we're going to look at what could happen if you try to manipulate data out of the bounds of your array. We have seen that when you allocate space for an array, the computer is going to give you a bunch of memory locations you can use to store your data. And it's going to be of the size that you have specified or that is deduced by the compiler. So here is an example of an array that is going to store 7 elements. And we have green slots for these elements, and these are the locations we are allowed to manipulate in our C++ program. If we try to go overbound, for example, if we try to modify something before our array or after our array, it might be a memory location that is owned by another program. It might be a memory location that is even being used by the operating system. So bad things can really happen if you try to use data that is outside the bounds of your array. Let's try to look at a simple example here. Here we have an array called numbers. We have 10 slots inside. So we are only allowed to modify the memory locations for these 10 numbers. And if we try to access something outside the bounds of this array, something might happen. But some people say that C++ is really funny because it should be stopping you from doing something like this. But C++ allows you to do this. If you look at code here, we have an array, we have 10 elements in, so the valid indexes we can really use are from 0 to 9. But if we try and access something at index 12, the code is going to compile, and if we run it, we're going to get something printed out. But that's something, this is going to give you garbage data, or you might be even trying to read some restricted memory, and your program is going to terminate immediately, and we're going to say that it has crashed. If you try to write over bounds, the compiler is also going to allow it, but you don't own the memory, so other programs might come and change that memory location, and if you try to read from it again, you're not going to get what you expect. Another thing that could happen is that you try and modify data that is owned by other programs, and you might imagine how bad that really is. So the message here is don't go over your array bounds, and you're going to be playing in the safe zone. Let's head over to Visual Studio Code and play with this a little bit. Here we are in our working directory. The current project is array bounds. We're going to grab the template files, and we're going to put them in place. And we're going to open this up in Visual Studio Code. We are going to declare an array and try to read beyond the legal bounds of our array. So let's try and bring up a terminal here, and we are going to build this with GCC. The build is going to go through. You're not going to get a compiler error, but if we run this, we can really get anything. And you see we have a number. We don't really know what it means. And this means that you have read out of the legal bounds of your array. And C++ allows you to do this. And the reason they do this is because they expect you, the developer, to know what you're doing when you try manipulating things like array. And now you know this, and be careful when you are working with arrays like this. So don't go over bounds, that's the message. We may also try to modify data beyond bounds. So let's go down and put in the code to modify things. And I have put a clear message here as a comment to let you know that this is really something you should be very, very careful about. So we're going to try and change that number to 1000, and we're going to try and print it out and see what we get. But this memory location at index 12 is not something we own. So other programs might come and write to this location, and if we try to read from it again, we might not get what we put in here. Even worse, this memory location might be owned by other programs, and if they read, they're going to get what they didn't put in, they're going to get what you put in, and this is something bad. We might try and really go crazy with this. Let's put in a really huge number and see that we can do that. This is a good way to learn, by the way. It's going to compile, and let's try and print what we have in there, and we're going to say this location here, and that's what we're going to say here. And we're going to build. Again, the build is going to go through. You see that we are doing something really crazy. Our array has 10 elements, but we are trying to modify something 1 million memory locations away. And this is really crazy, and C++ allows you to do this. So let's clear and run did we build. Let's make sure we have build. So let's build with GCC and clear and run rooster. Our program is crashing because we are trying to access something that isn't really ours, and you see it has crashed. Okay, for example, if we have something printed out after this, let's say std program, and then so that you can see it is really crashing, and say std ndl. This statement here is not going to print because once we hit this location, we're going to try and modify this, and the program is not going to be able to do that. It's going to crash. The operating system is going to notice that we are trying to do something crazy, and it's going to say, this program is really crazy, it doesn't know what it's doing, I am going to kill it, and it is going to stop. That's basically what is happening here. So let's build again with GCC, and we're going to clear. Let's clear. And run rooster. You see that it's going to try and do this. It's going to try and put a value in here. The program is going to end here, and this is really bad because memory locations you have allocated for before here are not properly released and returned to the operating system, and this is something really bad. So the message is, don't go over bounds. Make sure you are working within the legal boundaries of your array. Welcome to this new chapter, and we are going to be talking about pointers. Pointers are one of the important topics in C++, and they allow you to do some of the things very conveniently, and we're going to be learning about all those tricky things you can do with them in this chapter. But now, I want you to have a basic understanding of what a pointer really is. So far, we have been working with variables like this. We set up a variable in our C++ code. We get to a point where we put a value inside that variable, and we could use it. For example, we could print it out on stdcout, or we could even store a value or assign another value to the variable. We've been doing that quite a lot, but there is a point we haven't really been talking about. Those variables have an address in memory, and here, for example, you see that our var is stored at location 1008. Of course, this is a simple example I came up with, but I hope it drives the point home. all the variables you use in your code have some kind of address in memory. And we can grab that address and store that in a special kind of variable, which is really a pointer. So we can say that a pointer is a special kind of variable that stores addresses of other variables. Make sure you really understand this. Here we have pvar, so it is a pointer. Its type is int pointer, and we denote pointer using this star symbol after our type. If you see something like this, you're going to know that this type is a pointer to int. Its name is going to be pvar because it's a variable, and its value is going to be the address of another variable. You see, it is storing 1008, which happens to be the address of our var here in memory. Pointers and variables we've been talking about can work hand in hand, and we're going to be seeing how this is done in the next few lectures in the chapter, but the basic idea is really the same. Here you see that we have a pointer to int, but you can have a pointer really to anything in your code. You can have a pointer to car, you can have a pointer to double, you can have a pointer to float, even pointers to custom types we haven't really talked about now, but we will learn about them later in the course. Again, a pointer is a special type of variable in your C++ program that is going to store addresses to other variables. That's what it really is. And we're going to start and see how you can declare, initialize, and use them in your code starting in the next lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can declare and use pointers in our C++ code. In the last lecture, we said that a pointer is a special kind of variable that can store addresses to other variables in our C++ code. And we have seen a slide like this to drive the point home. Now we're going to see how we can actually code, you say int, you put a star after the type to mean that this variable is not a regular variable like we have seen before. It is a special kind of variable that is going to store addresses to other variables. And here I have to say that you have to be really careful and only store addresses to valid types of variable in your pointers. For example, this is a pointer to int. It can only store an address of a variable of type int. For other types, if you try and put in their addresses in here, you're going to get a compiler error. Down here you see we have another example, and it's called p fractional number because it's a double. And you see that our pointers here are initialized using braced initializers, and this is going to initialize the pointers with a special address that really denotes that these pointers are not pointing to anything yet. Okay, you can also say that explicitly and put null PTR inside, and this is going to mean that these pointers are not pointing anywhere. You can't really use the values at the addresses where they point. This is the message here. Don't use pointers that contain null pointer. All pointers on a given system are going to have the same size. For example, if you have a pointer to int and a pointer to double, they are going to be the same size because they really store the same thing. They store addresses to variables, and addresses to different variables, even if they happen to be of the same type on the same system, are of the same size. That's why all the pointers you're going to use in your code are going to have the same size, and this is something you should keep in mind. And here is a simple example to really play with that. We have a size of int printed out, we have a size of our pointers printed out, and we're going to compare these things when we get to Visual Studio Code in a minute, and you're going to see that all pointers are of the same size. A question I get from many people is if the position of this star symbol really matters, and I have to break it to you, it doesn't. But I prefer to put it on the left. Some people prefer to put it on the right, but definitely don't put it in the middle. I've never seen anybody do this, but it's going to work. It's going to be legal C++ code. Another thing I see people do, which is really confusing, is to declare your pointers on the same line and do a comma like this. This is really going to be confusing. And now I want you to guess and see what is happening here. Is either int var a pointer or it's a regular int? I want you to keep this in mind. I'm not going to tell you. We're going to try this out actually in Visual Studio Code, and we're going to figure this out together. But now I want you to try and think about it. We're going to leave this question unanswered, and we're going to answer it in a little while. But for now, don't really do this because it's confusing and it's going to make your code less readable. If you have to do something like this, make sure you just put them on different lines and it's not going to be confusing. For example, if you look down here, you're going to know that p number 7 is a pointer, other int var is a regular int, and there is no room for confusion this time. Use code like this and don't put things on the same line like we have on top here. Okay, now we have seen that we can declare and initialize pointers with null pointer. Now is the time to see how we can put actual data in those pointer variables. Here we have a variable which is called int var. It is of type int and its value is a 43. We can also set up another pointer variable, int pointer. Its name is p_int, and we can initialize it with the address of another variable. And here is a new operator we haven't seen before. This ampersand variable here really means the address of this int variable. That's what we mean here. So we're going to initialize this p_int variable with the address of int variable, and this is how we do it. If we go down here, we print int var, we're going to get the value printed out. If we print the pointer directly, we're going to get the address of this little guy printed out on the console, and we're going to see it. Okay, so this is how you can store things in your pointer variables, and what you have to store in has to be an address of another variable. Down here you see we have another variable called int var1, inside we have a 65, and if you go down here you see that we are storing something else in our pointer variable here. We had in the address of int var, now we are putting in the address of int var1 using an assignment operator, and this is something you can definitely do. It's legal C++, it's going to work. If we print it out, we're going to get a different address printed out. This is how you can store values in your pointer variables. Again, you can't cross assign before different pointer types. Here we have an int pointer which is called p_int1, and we have a double variable, it's called double var. We can't take the address of double var and store that in p_int1. This is going to be a compiler error. The variables whose addresses you store in p_int1 have to be of type int. Again, the basic idea is that a pointer is really a special kind of variable that is going to store addresses to other variables, and if your pointer is a pointer to int, the variables whose addresses you can store in this pointer to int can only be int. If you try and put in doubles, you're going to be in trouble, you're going to get a compiler error, and it's not going to work. Now we're going to head over to Visual Studio Code and actually play with these things. Here we are in our working directory. The current chapter is pointers, the current lecture is declaring and using pointers. We're going to grab our template files and put them in place. So put them in our project here, and we're going to open this in Visual Studio Code. The first thing we're going to see is how we can declare and initialize pointers, and we're going to use a pointer to int. As a first example, we're going to set up an int pointer and we say int star. We're going to give it a name, we're going to call this p number, and you can leave it like this uninitialized. But it is really advised to always initialize your pointers, so we're going to do that with a braced initializer, which is going to do that for us. This is going to implicitly initialize it with a 0 equivalent of pointers, and that happens to be null pointer, so we'll initialize. Okay, so this is what we're going to initialize with, null pointer. We say null PTR, and this is how you should do things. We can also do a pointer to double, why not? Let's do double pointer. And we're going to say fractional number, pointer to fractional number, and we can also initialize this with null pointer implicitly. And once you do this, the program is going to be legal. If we try to build it with GCC like we always do, the build is going to be good, but we don't really have any useful thing we can see if we run this program. We are just getting started. We will get to see things later. For now, just understand that p number is a variable we have in our code. This variable can only store addresses to other variables that happen to be of type int. If you try and store in an address of a variable which is of type double, for example, or float, you're going to get a compiler error. You shouldn't do that. The same for p fractional number. It can only store addresses to other variables which happen to be of type double. Keep this in mind. We can also explicitly initialize with null pointer. So we can say int pointer and say p number 1, why not? And we're going to explicitly use null ptr like this, and this is going to work as well. We can also say p fractional number and say 1, why not? And say null ptr. This is going to work. This is something you can do. You're going to see that if we compile this, the compiler is going to be happy with this. The build is good. Okay, now you know how you can declare and initialize your pointers. Now we want to see that pointers to different variables are actually of the same size on whatever system you are working on. It's not consistent across operating systems or even systems, but it is guaranteed to be of the same size on the same machine. I am going to go down and put in a piece of code that is going to show us all these things on the console, and I am going to click on this file icon here and give ourselves some breathing room so that we can see the entire thing here. If you look here, we are printing the size of int. We know that this is going to be a 4. Size of double, this is going to be an 8 on our system here, but we don't know what the size of a double pointer is or the size of an int pointer, and we're going to see that in a minute. Here you see that we are also using the pointer variables immediately. This is something you can do. You see that Visual Studio Code is not complaining, and we can go on top here and build with GCC. Let's do that. The build is going to be good. Now we can open up a terminal and actually run this program here. We're going to clear. If we do dir, we're going to see that in our directory here. So you see that we have rooster.exe, and we can run this. And it's going to say size of int is 4, size of double is 8. This is expected, but pointer types are of size 8 on my system. They occupy 8 bytes in memory. So it doesn't matter the type we are pointing to. A pointer to it is always going to be 8 bytes in memory. This is something you should really know and keep in your mind. Another thing we have said that I want to play with right now is the location of the star symbol. Some people say you should put it on the left, some people say you should put it to the right. I don't really think any of these things matters. I prefer to put it to the left, but if you put it to the right, it's also possible. It's going to work. You see that even if you put it in the middle here, which is really crazy, the compiler is going to take this. We can run the task to build this to make sure the compiler is really happy, and you see that there's no problem. The compiler is going to accept this, and we are going to build successfully. If you put your declaration on a single line like this, what is other int var going to be? Is it going to be a regular int variable? Is it going to be a pointer to int? We don't really know now, and I don't want to tell you. We're going to find out together. So what we're going to do, we're going to print the size of these things. I am going to go down here and put in the code and come back in a minute. Here is our code typed out, and we're going to see the size of these things. What we're going to do is run the task to build with GCC as we always do. Let's clear properly and run rooster. And you see size of p number 5 is 8 because it's a pointer. Size of other int is 4, and the same applies to the second line here. So from this we can tell that other int var and other int var 6 are not pointers. They are regular integers, and this can be really confusing. So to avoid this confusion, I would advise not to declare your things when you have pointers inside like this, because that's going to be really confusing. What you can do is put them on separate lines and do something like this. So here it is very clear that p number 7 is a pointer, other int var 7 is a regular int variable, and there is no room for confusion with this way of doing things. So make sure you put things on separate lines like this, and you're going to be fine. Now what I want you to see is that we can actually store data in our pointers. I mean valid data that is not null pointer. In this case, we're going to set up a variable, a regular int variable. It's going to store a 43 inside, and we're going to set up another pointer and initialize that with the address of this int variable, and this is going to work properly. What we can do now is print the int var. We're going to print it out. If we try to print the pointer, we're going to get the address of this int var in memory, and this is something you need to see with your eyes. This is the first time we are printing out an address that is stored in a pointer, and we're going to see that on the console here. What I am going to do before we build and run this, I am going to comment out everything we've done before because our console is now cluttered. So let's come and comment out everything. And let's go down again. Now if we print, we're going to see these two statements, and that's going to be easier to follow on the console here. The build is good, so we are cool. Let's run rooster. And the var is 43, and its address in memory is this number here. It is in hexadecimal. So this is the address in memory, and we can print that out and see what it is. Okay, so this is really cool, but we can also change what is stored in our pointer here. For example, we can set up another variable, call it int var1, and change pint, which is a pointer, to contain the address of this new variable, and we can do that. Now if we print pint, we're going to see that it contains a different address, and we can do that. So let's build with GCC again. We're going to go down and clear and run rooster, and we're going to see that now we have a different address. The one we had ended in DE4, now we end in DE0. These are different addresses, and we are storing different things in our pointer. This is really cool. You can do something like this. And the next thing we want to see now is that we can't cross assign between pointers of different types. And what I mean here is that, for example, if we have two variables here, one is a pointer to int, it is initialized with null pointer, and we have another variable which is a double var, it's going to be of type double, and we can't do something like pint equals address of double var. You can't do something like this. If you do it, you're going to get a compiler error. And you see that we have squiggly lines in Visual Studio Code. This is a good indication that something might be wrong. If we open the problems tab, we're going to say a value of double pointer cannot be assigned to an entity of type int pointer. So this is not something you can do. If you do this, you're going to get a compiler error. Be aware of this. Visual Studio Code has warned us enough, but we can also try and get a clear compiler error by building this with GCC, and we're going to get basically the same thing. You can't cross-assign between pointers of different types. We are trying to assign a double address into a pointer to int, and this is not going to work. So let's comment this out because we don't want this compiler error. Now you know this. And before we close this lecture, I want to mention what is called dereferencing, and that is the act of reading something through a pointer. So if we have an address in a pointer, we can go through that address and actually read the value contained in that address. And we can do something like this. So if we have, for example, an int pointer, let's call it pint2. Do we have a variable like this? So let's say we initialize this with null pointer, and we have an int variable, and this is a 56, for example. And we do something like, we do say pint2. We're going to make it contain the address of int data. This is something you know you can do now. Now we want to go through pint2 to read what is contained in int data, because pint2 contains the address of our integer here. So what we can do, we can do stdc out and say value. And the syntax we use in C++ is like this. We say star and we say our pointer variable. We're going to say pint2. And now if we run, we're going to get the value here printed out. Okay, now if we try to build, we're going to build fine. Let's try with GCC. The build is good. We can clear so that the errors from a previous run are cleared out. You see, the build is good. We can now run Rooster, and we're going to see that value is 56. We are successfully reading the value stored in the address pointed to by our pointer here. And this is the syntax you use, and this is called dereferencing a pointer. We are basically reading something stored in the address of a pointer. This is what we mean here. And this is really all we set out to do in this lecture. The lecture turned out to be lengthy, but we had a lot of ground to cover. And now I hope you have a good grasp on how to declare, initialize, and use your pointers to do all kinds of crazy things. We are going to stop here in this lecture. In the next one, we're going to learn a little more about pointer to character types, because they are also special. Go ahead and finish up here and meet me there. In this lecture, we're going to explore pointer to characters. And you can declare a pointer to a character just like this. We have car pointer, and we say pcarvar to give it a variable name. We initialize this with a null pointer, and after that we set up a character variable, and it is called carvar, and we store in an A, an uppercase A. After that, we take the address of carvar and assign that to our pointer variable. This is how we store data in a pointer, and we can go through this pointer to access data in this character variable. If we do something like this, we're going to print A. Down here, we declare another variable, we store in a C, and we assign the address of this new character variable to our pointer variable, and if we print this again, we're going to get a C printed out. This is really what we have done in the last lecture. We are just extending that to character pointers. But with character pointers, you can do something really special. What you can do that is special, you can initialize that with a string literal, something like hello world, which is wrapped in quotes like this. When you do something like this, the string here is going to be expanded into a character array, and the first character of our array is going to be pointed to by p-message here. This is what we mean. I realize I might be throwing a lot of things at you right now. I am mixing up arrays and pointers, but they have a really strong relationship, and we're going to learn about that in detail in a few lectures ahead. But for now, think of it like this. This hello world string is going to be turned into a character array, and p-message is going to point to the first character in this array here. This is what is going to happen. And this is going to give us the flexibility of treating our strings as character pointers. And this is going to come in handy at many occasions. One thing I should tell you though is that some compilers will refuse to compile this code. For example, Visual Studio 19 that I have installed on my computer right now is going to refuse to compile this code. And the reason is the compiler is going to expand this string into a character array of const char. And here, what we are using to point to that is not a const char pointer. So this pointer here can be used to try and modify data into an array of const chars, and that's going to be disastrous. Because if you try to modify that, that's going to fail, and that's not going to be good. So some compilers are going to try and protect you from this and force you to use pointers that are qualified with const to really mean that they are const char pointers. And to get the code to work, we will have to do that, and I will show you how we do that in Visual Studio Code. But I have to tell you this, in case you just want to jump ahead and try this code out, if you get a compiler error, that's going to be the reason. Now that we have our string stored in memory, we can really print it out like this. If you print p-message, you're going to get the string printed out. But I want to give you a question here. What do you think we will get if we dereference p-message? Try to think about this. I told you that the compiler is going to expand this hello world string into an array of characters, or to be specific, an array of const chars. And p-message is going to be pointing to the first character in that array. So if we dereference p-message, we're going to get that character printed out. In this case, we will get an H. And that's what is going to happen here. But character pointers are special in that if you print them out directly, the compiler is going to do its magic and make it possible to print out the entire string that is stored in pmessage here. That's how character pointers are special, and you really need to be aware of this, because this is going to come in handy many times. Just to emphasize that this is going to be expanded into an array of constant characters. If we try to modify something inside pmessage here, for example, we try to change the H into a B, we can try to do that because pmessage is pointing to the first character, so we can try to dereference and assign a new value. And if we do that, we're going to get a compiler error, or even worse, we might get a crash at runtime. So this is something you shouldn't really do, and you should really flag your pmessage here as the const char pointer, and that's going to prevent you from doing things like this, which may turn out to be very bad. But most compilers are going to even prevent you from compiling this thing in modern times. For example, if you are using a very recent version of Visual Studio, you're going to get a compiler error, but I don't believe GCC is going to give us a compiler error, so we will have to try this out and see how it behaves. But the message is, if you have to do something like this, make sure you use the const char pointer, and you're going to be playing on the safe side. Okay, now I think you know enough about character pointers. What if we want our users to be able to change this string and make it be something else? For example, change the first character here into a B. Well, in that case, don't use character pointers, use regular arrays, the first character here into a B. Well, in that case, don't use character pointers, use regular arrays like we have seen before. So you can set up an array like this. It's going to be a character array, and you can initialize it with a string literal, and this is going to allow you to modify things inside. So if we do something like this, we will get the message printed out, and the message is going to be tello because we changed the H to be a T, and this is going to work. So this is something you really need to be aware of. But character pointers are very helpful in many cases, and in most cases you just want to store the string and print it out. You're not interested in changing it, so that's why this is going to come in handy in a lot of occasions. Now that you know this, we're going to head over to Visual Studio Code and actually try this out. Okay, here we are in our working folder. The current project is pointer to car. That's what we are exploring here. So we're going to grab our template files and put them in place. And we are going to open this thing into Visual Studio Code. And we're going to jump into here and set up our first const car pointer. Let's do car pointer to see how this thing behaves. We're going to call this message, and we're going to initialize this with our trusty message here, hello world. Okay, once you do something like this, your string is going to be referred to by message. Let's try and compile this and see that GCC is happy. We can compile with GCC, and it's going to tell us we can't really do that, and this is really good for base converting a string to constant car pointer. So what we are doing really is making an array of const characters and refer to it as a car pointer, and this is not going to work. This is a good thing. So you can't really do this, and this is a good thing. And let's try and see if Visual Studio can actually do this. We're going to build with MSVC. In this case, let's delete Rooster. Before we do that, we can right-click to it and say delete. Let's click to it first. Make sure it is selected and hit delete to remove it. Move to recycle bin in this case. Now we're going to clear here. Let's bring up our terminal again. And we're going to clear. And we're going to build with GCC. We're going to choose the MSVC compiler. If we're trying to build this, build finish it with arrows, and the arrow is going to be basically the same thing. This line here won't work. What we can do is make this const and make it super clear. That message here is going to point to an array of const car. If we're trying to build again, I think we're going to be good now. So let's try and do that. We're going to build with MSVC this time, and build finished successfully. Now this is really cool, and we can print this out. We can say stdc out message, and we're going to say message, and this is going to work. Let's go back to GCC because that's my favorite compiler. And you see that the compiler from Visual Studio is going to clutter our folder here with a lot of files. We don't want that. What I'm going to do, I'm going to select all this clutter here and remove that. And I'm going to hit delete with the right click, and it's going to go away. We're going to go back to GCC and use it and build with GCC. The build is going to go through because we qualified our character pointer with const here, and everything is going to be good. Be sure you know what is happening here, because this kind of problems can be really hard to solve. Okay, now that we have this, we can try and change something inside, but the compiler is not going to allow it. So if we try and do something like, this is not going to work because message is a pointer to const car. And we can't go through this pointer to modify something, so we're going to get a compiler error. This is something you should know, but we can dereference this pointer and print something that is inside. And I want you to guess again and see that you can come up with what is going to be printed if we dereference message and print out when we run this program. If we have this thing printed out here. Again, we are dereferencing the pointer and printing whatever result we get from that. Remember that this string literal is going to be turned into an array of const cars, and the first element of that array is going to be pointed to by this message car pointer here. So if we dereference this thing, we should get the H here printed out. That's what I think we should get. Let's try and build with GCC, of course. The build is going to be good. Let's clear and run Rooster. See that message is H. This is exactly what we expect here. Now that we have this working, what if we really want this thing here to work? What if we wanted to allow our users to go through this message thing and modify what is stored inside? Because sometimes that's going to be useful. Okay, we wanted to allow our users to modify this string. If you want to do that, you can use row character arrays, and the way we do that, we can say car message1, and we can make it an array and initialize that with hello world. And once we do this, we can go through the angle bracket syntax and modify the first character or whatever character we really want to modify in this string here. In this case, we are going to target the first, so we're going to say message1, and we're going to grab the index 0 because that's going to be the first character here, and we're going to assign a new character, let's say B, like we just said. And if we print this out, say message1, and put that out, we're going to see what comes out. If we run this program, we're going to build with GCC, so let's do that. The build is good, so we're good here. If we run, we're going to get below printed out, and we have successfully changed this thing here. So if you don't want to allow modifications to your string, use this thing here. If you want to allow modification to your string, use this syntax here. And this is really all we had to say in this lecture. In this lecture, we're going to revisit our idea of a C++ program memory map. We have seen that the C++ development workflow really goes like this. We have a program typed out in our IDE, we pass that through the compiler, and we get a binary executable, which is a binary representation of the code we have in our C++ program. You can then run that program on an operating system. For example, here I am on Windows. If I double click on my .exe file, for example, our applications are called rooster.exe. You've seen me run this 1,000 times by now. If we double click, this program is going to be loaded in our computer memory. And by memory, I mean random access memory, the memory that is going to be actively running things when they happen in your computer. It's different from the hard drive storage that can also be called memory, and this can throw off a lot of beginners. We are talking about RAM here when we mean memory, random access memory to be exact. If you double click on your program or open it on the terminal like we've been doing, the program is going to be loaded in memory, and it's going to be stored in a special section of memory called program area. And so far we have been thinking that our program is really loaded in real memory on our computer, but that's not the case. It is an idea of the memory that the program thinks it has, but it's not the real thing, and I am going to explain. But before we explain, let me elaborate on the reason why this is done. If we have many programs and each program is going to use real memory on our computer, we could quickly run out of memory. Because there are many programs, you might even have hundreds or thousands of programs running on your computer, you may never have enough memory to run them all if real memory was used by each program. So the idea was born to create what is called virtual memory. And it is a trick that fools your program into thinking it is the only program running on your operating systems and it owns all the address space or all the memory on your computer. That's what your program thinks. And the view that your program has of that memory is called a memory map. Each program is abstracted into what we call a process. You can think of rooster.exe that we have been building as a process on the system. And each process has access to the memory range between 0 and 2 to the power of n, where n is the number of bits that your operating system supports. For example, I am on a 64-bit operating system, so the range for my memory is going to be between 0 and 2 to the power of 64, and that's a lot of memory. My program is going to think that it owns all, and it can never run out. It's going to do whatever it wants. If you are on a 32-bit system, that's going to be between 0 and 2 to the power of 32, and that's going to be your virtual memory, the amount of memory that your program thinks that it owns, and it happens to be the entirety of your RAM that you have on your system. Each program basically thinks that it owns the entire memory, and it can do whatever it wants. Okay, so we have the real memory, which is random access memory, and we have virtual memory, which is going to be between 0 and 2 to the power of n. Okay, so now we're going to update on the idea of the program execution model, because now we know more. We know about virtual memory. Here is our C++ program. It's going to go through the compiler, and we are going to generate a binary file, which is going to be a representation of how things are going to be laid out in memory in our program. And if we run the program, it is going to go through a section of the CPU called Memory Management Unit, or MMU for short. So that MMU is going to be basically transforming between the memory map of each process and the real memory layout that we have in RAM. What the Memory Management Unit does is really transform between the representation we have in the memory map and the real thing we have in RAM. The entire program is not loaded in real memory by the CPU. Only parts of the program that are really going to be used soon are loaded in memory, and this is going to make effective use of the memory. Parts that are not likely to be used are going to be discarded from memory and stored on the hard drive instead, and this is really cool. Please note that the real way these things are done is really complicated, but it is buried down into the logic of the CPU and whatever. You don't really need to worry about this as a C++ programmer, but there are a few things you need to know as we are about to see in this lecture. So Memory Management Unit helps out in mapping between the memory map you have in your program, basically the idea that your program has of memory, and the real thing that we have in memory. Okay, here is a slide that is going to drive this home. We have a few programs with their own separate memory maps. We have program 1 through 4. If we execute them, they are going to go through the Memory Management Unit, and the Memory Management Unit is going to assign them sections on the real RAM that we have in our computer, and they are going to be using that section on the real random access memory that we have on our computer. The thing is, your program is going to really think it owns the entire thing. but it's not. It's just going to be using a part of it, and the memory management unit is going to be transforming between the idea that your program has and the real memory that we have on our computer. And the memory map is a standard format that is defined by the operating system. This is why, for example, you can't take an program is defined by the operating system that is going to be running that program. So all program written for an operating system must conform to the memory map that is defined by that operating system. So all programs on Windows, if you had a way to go in and look at the memory map, they are going to be pretty similar. So we have been talking about the memory map, but what does it look like? Well, here is a slide that is going to try and clear that out. So we're going to have a bunch of memory locations from 0 all the way to 2 to the power of n. And the memory map is really divided into a lot of parts. For example, we have the text section, we have the data section, we have the heap, stack, and system. And this is one view you can have on this. There are a few different versions of this slide that you're going to see on the internet. But what is really important is stack and heap for our purposes here. Stack is what is going to store our local variables. Think the A that we have here in main BC, things we had inside functions, those things are stored inside the stack section of our memory map. Besides the stack, we also have the heap, which is going to be the location where we get additional memory we can use to make things better for our program. We also have the text section, which is going to load the actual binary of our program so that the CPU can execute it. But we're not going to worry too much about this section in this course because it is out of scope for what we are trying to do here. We are going to focus on stack and heap because heap is actually going to be very important from the next lecture when we start talking about dynamic memory. Heap is going to be additional memory that you can use in your program if you run out of stack memory, and we're going to see a few other reasons why you might want to use this as we progress in this chapter. So our memory map is going to have a lot of parts, but the parts that we really care about in this course are stack and heap. This is really all we set out to do in this lecture. I hope you have a better idea of the memory map and how this really works. We introduced another view that you can have on how your C++ program is executed, and I hope you have a better idea of the memory system. And we are going to start and see how you can work with dynamic memory allocation, which is going to really use the heap starting in this lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to start and learn about dynamic memory allocation. And this is a technique we can use to start using heap storage that we have in the memory map of our C++ program. We can use that to get additional memory we can use and do stuff if stack memory isn't enough for our purposes. This is how we have been using pointers so far. For example, we have a variable, we set up a pointer, and we store the address of the variable n. So we can go ahead and use this pointer to manipulate the variable or do all kinds of crazy things. If you go down here, we have a pointer p number 1, and we have a number 1 variable, and we can store the address of number 1 into this pointer. It's really the same thing like we have on top here, but the pointer is not initialized at declaration here, and you have to make sure you put in valid data. And one thing I haven't really stressed enough is that it is really bad to try and use a pointer that is not initialized. For example, here we have p number 2, which is a pointer. It is not initialized, it contains junk, and we try and write into it. Okay, so try to think about what we really are doing here. This is a pointer that we have set up. We haven't really initialized that. So it's going to contain whatever address is possible. It can contain an address that is used by another program. It may contain an address that is being used by the operating system. It's not your address to mess with. And here we are actually trying to mess with that by storing in a 55. So this is going to cause a crash, possibly, or even corrupt data that is being used by other people. So don't do this. Another thing is to try and use a pointer that is initialized to null. For example, here we have a pointer, p number 3, and it is braced initialized. This is going to initialize it to null pointer, but we are trying and storing in a value here. So this is also going to be bad. It's not guaranteed what you're going to get. Actually, C++ doesn't give you any guarantees. This is called undefined behavior. So you're going to get a crash, and don't do it. As a good practice, the first thing you should do is initialize your pointers before you use them. You can initialize them with null pointer, and make sure that you are modifying valid addresses into those pointers. If you don't know what is in a pointer, don't use that pointer because bad things can happen. Okay, rule number 1, don't try to use a pointer that you didn't initialize. Rule number 2, don't try to work with a pointer that is pointing to null PTR. That's going to give you bad things you don't want to really deal with. Okay, so far we have been using memory that lives on the stack section of our memory map. We were using variables that we have declared in the main function. We were using variables that we have declared inside some functions, and that's all stuff that live on the stack. Now we want to see how we can use the heap. Okay, let's take a closer look at our memory map. We have the stack, we have the heap, and the differences between these two guys are laid out here. The stack memory is finite, so you don't have infinite memory, but the same is true for the heap. But heap is additional memory that you can use if you don't want to run out of stack memory. For stack memory, the developer isn't in full control of the memory lifetime. So if you declare something on the stack, for example, if you say int var1 and you initialize that to 23, you don't control when that variable is wiped out of memory. The variable is going to be killed when the scope in which it was declared is going to run out. And you, the developer, don't really say when the variable dies. And sometimes you really want to control when your variable dies. So this is a limitation we have with the stack memory. Okay, so for stack memory, lifetime is controlled by the scope mechanism. We just said that. For heap, the developer is in full control of when the variable comes to life and when the variable dies. And this is a benefit you might have with heap storage, and you might want to use this, and we're going to see how we can use that in the next few lectures. Okay, so make sure you understand the difference between stack and heap here. If you look at the example here, we have a variable which is called locus scope var. It is within this block delimited by the curly braces, and the variable is going to come to life when this statement is executed, but it is going to die when we hit the closing curly brace here. So the lifetime of this variable is controlled by the scope mechanism. But it is possible to use dynamic memory or use memory on the heap, and we're going to see a syntax you can use to do that. The first thing you want to do is to set up a pointer that is going to be pointing to that heap allocated memory. The way you do that, you set up a pointer. Here we have p number 4. We initialize it with null PTR. But what we do to allocate memory is the second statement here. We say p number 4 and we say new int. The moment this statement is going to be executed, the operating system is going to allocate a piece of memory on the heap. The memory is going to be large enough to accommodate for an integer, so it's going to be 4 bytes long. And it is your memory now. Your program can use it to do whatever it wants, and no other program on the system can use this piece of memory. So it is going to be yours until you explicitly return this piece of memory to the system, and we're going to see how you can do that in a minute. Once this memory is yours, you can use it. You see here we are dereferencing the memory and storing in 77, and if we're trying to print this 77, we're going to get it printed out. Okay, this is how you can use dynamic memory, and when you do this, things are not being stored on the stack. Things are being stored on the heap. I really hope you understand this because it is very important. Okay, so here is our view of stack and heap. So if you use new to allocate for memory, stuff are going to be stored in this heap section here of your memory map. Here is another example to try and understand the lifetime of our variables. Localvar again is limited to this scope. It is going to come into life when this statement here is executed, and it is going to die when we run out of this scope here. So if you try executing code out of this scope, localvar is no longer going to be available. You can't use it. But that's not the case for local PTR var, because this is a pointer. It lives on the heap. And if you go out of this scope, the memory is still going to be yours. So if you have a way you can access it and use it, you're going to be able to use it. And it is going to be yours until you decide to return it to the operating system. So we have been talking about returning the memory to the system. How do we do it? Well, you use the delete keyword in C++. Here we have our memory, which is allocated using new int. So the operating system is going to give us a new piece of memory. It is going to be 4 bytes because we're going to store in an integer. And we are going to be pointing to that memory through p number 4 here. We can use this memory however we want through the referencing and do all kinds of crazy things. And when we are done with this memory, we are going to say delete p number 4, and this statement is going to return the memory to the operating system. The memory is no longer going to be ours after this statement. And a good thing to do after you release your memory is to reset it to null PTR so that other people know that you don't really have any valid data in that memory. Because if you try to use a deleted memory section, bad things are going to happen. That's not going to be your memory. We're going to fall into the same problem of trying to use an uninitialized piece of memory. Don't do that. So whenever you release memory, also reset it to null PTR to play it safe. We can also initialize our pointers with dynamic memory when we declare them, and this is how you can do it. We say p number 5, and we initialize it with new int. This is going to give us a new piece of memory on the heap, and it is going to be pointed to by p number 5. We get the same thing here, but here we are just pointing in new values in p number 6 and p number 7. The memory locations on the heap are going to be containing 22 and 23 for p number 6 and p number 7. And here we have a few examples of how we can print the contents of these memory locations on SDDC out. And after you are done using your heap memory, you're going to release it using the delete keyword, and you are going to reset that to null PTR to really play it safe. This is how you should use dynamic memory allocated on the heap. Another thing you should know is that it is really bad to call delete twice on a pointer. So here we have a memory location that we allocate on the heap. We stored this in a pointer, and we are trying to use it here in SDDC out, reading whatever is inside. And if we delete it for the first time, that's going to be equal. It is going to be returned to the system. But if you try to delete it for the second time, you're going to get a crash. Don't do this. This is really bad. Okay, now that we have a slightly clear idea about pointers and dynamic memory allocation, I think it is time we went to Visual Studio Code and actually played with a few of these concepts. Here we are in our working directory. The current project is dynamic memory allocation. We're going to grab our template files and we're going to put them in place. Dynamic memory allocation. Let's do that. And we're going to open this in Visual Studio Code. The first thing we're going to do is review how we have been using pointers so far. We have been using them like this. We had a variable stored somewhere on the stack. Again, this is the stack memory that we are using here. And we stored addresses of some variables in our pointers, something like this. And we could go through the pointer to manipulate that memory location. For example, we can print the address of that memory. We can even dereference and print the value in here by doing something like we do here. And we are not printing here. So let's say that. Let's say p number. We can do something like this. And we have been doing this quite a lot so far. We can also have a piece of memory that is uninitialized, and we store the address of some variable in that piece of memory, and we can do the same thing. For example, if we print p number 1, we're going to get the value 12 printed out here. And we could run this, so let's try and do that. We're going to bring up a terminal first and close this pane so that we have some breathing room. And we are going to build with GCC, like we always do. We're going to build successfully, we're going to clear and run rooster, and we're going to see that we have these things printed out here. The variable we have in here is 22, so we're going to get that if we print the variable directly. If we print pointer, we're going to get the address printed out. We can also go through the address of operator to print the address of this variable here, but we can also print our value through dereferencing our pointer, and we can get access to it here. Down here we have a pointer that is not initialized, so it will contain a junk address that you shouldn't really use, but we're not going to do that because we're going to store in the address of number 1 here, and we can manipulate the value here through the pointer using the dereference operator here. And if we print this p number 1, we're going to get 12 printed out. This is pretty cool. Okay, so this is how we have been using pointers so far. Let's comment this out because we're going to see some other things. Okay, before we really look at how dynamic memory works, we are going to show you a few bad things you need to be aware of. So let's put in a piece of code for us to play with. And here we are saying that writing into uninitialized memory is really bad. So here we have a pointer, it is uninitialized, and we are trying and directly write into it through the reference end, and this is going to be bad. You see that Visual Studio Code is not complaining. It thinks that we know what we are doing here, and it's not going to warn us. But this pointer could really be pointing anywhere, including operating system specific memory. And here you may be trying to modify things that your operating system is going to need. So clearly, the operating system is not going to be happy about this, and bad things can happen to this program. So now we have this memory location. We're going to try and write into it, and we're going to see what happens if we run this program. For now, let's try and take this little section here and comment it out. And we want to see what happens on the program here, the code here that we might want to run. Let's try and build it with GCC. We're going to run the task to do that. The build is going to be good. You see that we don't even get a compiler error. And if we're trying to run Rooster, you see that the program is going to try and run, the operating system is going to say, this guy doesn't know what they are doing, and I am going to close them. You see that it's not even running this statement here. Let's go on top here and put in an stdc out statement so that we can really see where this program is failing. Let's say that stdc out writing in the 55. Okay, so this is what we have. We have a few statements added in, and we want to see if we actually get to run these two things to see where the program is actually failing. We are going to build it again with GCC, and we are going to clear and run Rooster. You see that it's going to say writing in a 55, but this statement here is going to fail because we are trying to write into memory that is not ours, and the operating system is going to stop us. So our program is crashing, and it is terminating before it even runs the things that are down here. Hopefully you can see how bad this is. You have designed your program to do things, but it is going to stop without having done any of the other things that you have designed below. So this is really bad. And another bad thing is that you might have allocated some dynamic memory beforehand, and your program is going to end before it even releases that memory properly and returns that to the operating system. So this is bad. You don't want crashes in your programs, and don't ever try and use and dereference memory that you haven't initialized. This is one bad thing. We're going to comment this out. I hope you really know how bad this is, and we're going to go down again and uncomment what we had done here. And it's going to be another bad thing because we are trying to write into memory initialized to null PTR. Okay, here we have a pointer. This is called p number 3, and it is initialized with null PTR. You can think of PTR as an address that says, I don't have any valid thing in me, don't use me. That's what null PTR is saying. So we have the pointer initialized to PTR, but we are trying to store something in here. And you can imagine how bad this is. This is memory that isn't really valid. The memory itself is saying, I don't contain anything valid, don't try to use me, and if you try to use it, bad things are going to happen. So if we try and compile this program, it is going to compile. The compiler is not going to stop us to do something like this. And these are some things you need to be aware of in C++. But if we try to run it, you're going to see that we are also going to get a crash. Again, let's try and put a statement in front of this failing line. And below this line, I can say, done writing. And I can do std_endl here. And build the program so that we can see which std statements run and which do not after our program crashes. So we're going to clear, the build is good, and run Rooster. You're going to see it's going to say what it's doing. It's going to try and fail, and the operating system is going to kill this program because it is crazy. It is doing what it shouldn't really be doing. So this is something bad. Don't do it. Be aware of this thing. Okay, we're going to comment this out and actually look at how we can dynamically allocate memory from the heap. And we're going to put in a piece of code to play with that. It's not really complicated. We have a pointer. We initialize it with null pointer to say that this pointer doesn't point to anywhere valid. Don't use it. And we are calling new int. When we do this, the operating system is going to give us a new piece of memory on the heap. This piece of memory is going to have the size enough to contain in it, so it's going to be 4 bytes in memory, and we are going to be pointing to that piece of memory using p number 4 here. This is what we are trying to say here. The moment we do this, we own this piece of memory, and nobody else on the operating system can use it. So that's something you should know. Once you have it, you can manipulate it through the pointer here. So here we can go through the reference operator and store in a 77. And if we print it out, we're going to get that printed out here. Okay, this is really cool. This is the first time we use heap memory, and I am excited about showing you these things. We're going to try and build this program, and the build is going to be good, and we are going to clear this. And if we run Rooster, we should see a 77 printed out. Let's do that. We're going to get our 77, but this 77 is stored on the heap now. It is not stored on the stack, and this is really, really cool. We can control when this variable comes alive by allocating memory on the heap, and we exactly control when this variable dies if we want. And we're going to see how we can kill this variable from memory. But for now, just take a moment and appreciate how cool it is to be able to allocate stuff on the heap. It is really cool. Now that you have used the memory, it is really time to return it to the system because we have no more use for it. The way you release memory to the system is to call the delete keyword and say the pointer pointing to the memory that you are trying to release to the system. So we're going to say P number 4 here. Let's bring this down a little bit so that you can see the entire story. So we have a pointer here, and it is pointing to dynamically allocated memory from the heap. This memory is 4 bytes large because it stores an integer. We have it dynamically allocated. We use it here, and it is time to return it to the operating system. Okay, I hope this is clear. The moment you call the delete keyword, now the memory is going to be containing some junk, and you don't want to really use that anymore. If you try to use it, it's not your memory, you're going to run into trouble. So for example, after we delete this memory, if we try to use it, I'm going to show you here, I think I can. Let's say P number 4, and store in something. Notice that we are using the dereference operator, and let's try and put in a 45, why not? So let's build this with GCC, as we always do. It is going to build. Compiler is not going to stop you from doing something like this, writing into memory that you have already released to the system, but we're going to see what happens. So run rooster, and it is going to say done writing, but you see that the program has really crashed. Because here we are trying to write into memory that we don't really own, and this is bad. Don't do this. So the moment you delete the memory, or the moment you return the memory to the operating system, it is good practice to reset that memory to null PTR. So we're going to say P number 4, and make sure it contains null PTR. At least when we do this, other people have a chance to check and see that that's valid memory before they use it. That's the use of resetting your memory here. So this is something you should do. Again, the flow to use dynamic memory is really simple. You set up a pointer that is going to point to your memory. You're going to allocate the memory from the heap using the new operator. You're going to specify the type you want to allocate memory for. The operating system is going to give you that memory, and you're going to be pointing to that memory with your pointer. You are going to manipulate that memory using your pointer and doing all kinds of crazy things. And after you are done with that memory, you're going to release it to the operating system. And please remember to reset your pointers after you have deleted them like this. That's going to make your life a whole lot easier, and other developers are going to thank you for doing this when they get to use your code, because your code is going to be much safer to work with. Okay, let's comment this out and show you another example of what cool things you can do with dynamic heap memory. We're going to go down and put in a piece of code and show you that you can actually dynamically initialize your pointers at declaration. This is something you can do. The first one is not initialized, so it's going to contain junk value. P number 5, if we try to print it, we're going to get some junk address printed out. P number 6, we're going to dereference it and print the value inside, so we're going to see that. And we can do the same thing for P number 6 and P number 7. After we are done using the pointers, we are going to release the memory here, and notice that we are resetting the pointers to null pointer to say that they don't really contain anything useful. Don't use them. Make sure you have something valid in before you use them. This is the meaning here. If you're trying to run the program, you can guess what we're going to see, so try and guess. And we're going to build. We're going to build successfully. We're going to clear, not clear. And we're going to run rooster. And we're going to see that P number 5 contains some junk address, okay? And if we try to dereference it, we're going to get a junk value. This is really not useful. Don't use this value because you didn't put this value in the first place. You're going to see that P number 6 is going to point to some other address, but we're going to have a valid value inside because we have put that in at initialization here. The same is true for P number 7. It's going to point to some address, and we're going to have 23n because we put in our 23. This is how you really use these pointers. Another thing I want you to know is that even if we have called, delete, and reset these pointers, they are still available for use in our program. So if we want, we can reuse these pointers. So for example, P number 5, we can take it and use it to allocate new memory. So we can say new int and store in 81. Why not? Okay, so we can go down here and use that. This is going to be valid C++ code. Okay, take a moment and look at it. It is P number 5, not P number. And Visual Studio Code is going to take this because it is valid C++ code. The memory has been returned to the operating system, and the pointer has been reset to null PTR, but we can reuse the same pointer to allocate new memory. So we are allocating new memory on the heap. The memory is going to be 4 bytes because it is going to contain an integer, and we are using this pointer to point to that new memory. So this pointer is being reused. It was pointing to the memory that we allocated here, which was uninitialized, and we are using that to point to new memory location on the heap. I really want you to understand these things because many beginners get them wrong, and it is hard to correct these things in your mind once you have a wrong idea about them in the first place. So make sure you understand this. So if we print this, we're going to get the 81 printed out, but we have allocated new memory. We have to remember to release it again. So we have to come and say delete P number 5, and we need to reset it to null pointer. And we're going to do that right here. Once we do this, we're going to be playing it safe. Let's try and run and see that we see the 81 printed out. We're going to build with GCC. The build is going to go through, and we are going to clear and run rooster. And you see that we see our 81, and we don't have any crazy crash. For example, to prove that we don't have a crash, we can say that our program is ending well. And we're going to know if the program has actually reached the end before it dies. We're going to build again with GCC, and we're going to clear and run rooster, and you're going to see that the program is ending well. The other thing I want you to see is that it is really bad to call delete twice on a pointer. Again, it is really bad to call delete twice on a pointer. Don't do that. Okay, we're going to see an example of that here. So we're going to allocate new memory using p number 5, why not? So we're going to say p number 5, and we're going to say new int. We're going to allocate new memory on the heap, and we're going to store in a 99 in that memory. We can print out the 99, so we're going to say, and after we are done using this memory, we are a good C++ citizen, so we're going to call delete, and say p number 5. Okay, this is good, it is going to work. If we will then run, we're going to get what we expect. We should get a 99 printed out last in our program before it ends, and we see that printed out here. Program ending well, this is really cool. But if we try to call delete twice, and say p number 5 again, and try to build, you see that the compiler is not going to stop us because it thinks we know what we are doing. So this is something you need to be aware of in C++. If we run this program, you're going to see, the program is not going to end well. The C++ runtime or the operating system is going to get here and see, this guy is trying to release memory twice, and I don't do that. This is a bad program, I am going to kill it, and it is going to be killed. The bad thing again is that anything you have in your program after these lines is not going to run, because the operating system is going to kill your program at this line here. So if you had memory allocated that you planned to release later on in your program, your memory is not going to be released because those statements to release the memory will never be run. This is where the program is going to be killed. The operating system is going to see that you are a rogue program, and it is going to kill the program. So don't delete your memory twice. This is something you should really watch out for. And you might think, I know this. Why would I call delete twice in a single line here? Well, you may not do it like this, but your program might have multiple files where you have pointers pointing to the same memory. And if you try to delete that memory twice, you're going to get this error, and this is really good. So watch out for these kinds of things, and we're going to see different ways you can use to really make sure you are doing things right in C++. This is really all we set out to do in this lecture, giving you first-hand practice on how to do dynamic memory allocation. I hope you found this useful. We are going to stop here in this lecture, and the next one we're going to learn about dangling pointers. Go ahead and finish up here and meet me there. In this lecture, we're going to focus on dangling pointers and show you how they can be bad. A dangling pointer is a pointer that is pointing to a valid address, and we have seen a few examples of this already. But in this lecture, we're going to focus on that and show you common solutions we can apply to these problems here. And dangling pointers are really bad. They are going to lead your programs to undefined behavior, and we have seen that that can crash your program many times. There are three kinds of dangling pointers we're going to look at in this lecture. The first one is a pointer that is not initialized. The second one is a deleted pointer. And the third case may come if you have multiple pointers pointing to the same memory location. And let's look at these cases one by one. Here we have an example of a pointer that is not properly initialized. This is p number 5. It is a pointer to int, and it is not initialized. It doesn't really point anywhere, and it is going to contain junk address. If we try to dereference it, we're going to get bad things to happen because we don't really know which address is stored in there, and putting something in there might lead to a crash. So this is something you need to watch out for. The second kind of dangling pointer that can really lead you to bad places is a deleted pointer. Here is a pointer, p number 1. It is initialized with dynamic memory, and we can use it. For example, here we are dereferencing the pointer and printing the value inside and deleting the pointer. After we delete the pointer, don't really use it before you properly initialize it with some kind of memory. If we try to do that, this is going to be undefined behavior and your program might crash. So make sure you don't do something like this. Another case is if you have multiple pointers pointing to the same address, and here is a simple example to drive the point home. We have pointer 3, which is pointing to dynamic memory here. We are using new int in our braced initializer, and we are putting value 83 in that pointer location. And here we set up another pointer, p number 4, and we initialize that with another pointer. And if we print these things out, we're going to get that they contain the same address and they contain the same value. We're going to see that. If we delete p number 3 and try to use p number 4 later, we're going to get problems because this memory has been deleted by p number 3, but p number 4 is still pointing to that. And if it tries to use that, it's going to be deleted memory basically, and we're going to get undefined behavior. So be sure you know these problems and try to avoid them in your programs. Okay, these are problems, but how do we solve them? Well, there are a few solutions. One is to always initialize your pointers. The moment you declare a pointer, make sure it is initialized. If you don't know what you can initialize that pointer with, put in null pointer first, and then you're going to put in an address later when you have a clear idea of which address you can store in. The second solution is to reset your pointers to null PTR after you delete the memory. That's the second thing you should do every time you call delete. That's going to give other developers, or even yourself, a chance to check and see if that memory location contains a valid address before you do that. And for multiple pointers pointing to the same address, you have to choose and make one pointer the master of the controller of the memory. And all pointers are basically going to be slaves, which can't release the memory, but they can read and do something with that memory, but they don't have the task of releasing that memory. And here is how you can apply solution 1, for example. We have pointer number 5, and we're going to brace initialize it. This is going to initialize it to null pointer. The other thing you can do is initialize the pointer with dynamic memory, like we are doing here with p number 6, and this is going to put in the value, and we are going to be playing on the safe side. Now, if your pointers are initialized, developers have a chance to check your pointers against null PTR to see that they contain something valid before they use it. And if they see that it contains null PTR, they are not going to try and use it. And this is going to be very safe. For the second problem with deleted pointers, we are going to reset our pointers after we call delete. For example, here we have pin number 7 initialized with dynamic memory and 82 is stored in. We can print it out or do things with it. When we delete the memory, we're going to reset it to null PTR so that other developers or even ourselves can check this memory against null PTR. And if it's different from null PTR, we can use it. If it's equal to null PTR, we're going to leave it alone and do something else. This is going to be very safe. If you have multiple pointers pointing to the same address like we have here, then you're going to have to decide which pointer is the master pointer and other pointers are going to be slave pointers. And before use, all the other pointers are going to check against the master pointer and see that it contains contains valid memory because the master pointer has the task of deleting this memory. Let's go through this and see how this could work in practice. So P number 5 is our master pointer. We are setting P number 5 and initializing it with P number 8. We are creating things using P number 8. We can either use P number 8 or P number 9. This is going to work. But before we use the memory location, we're going to check against the master pointer. If the master pointer contains null PTR, we're not going to use this memory. If the master pointer doesn't contain null PTR, we're going to use this memory here. Okay, if you go down, you see that the master pointer is going to be releasing the memory. And if we try to use that memory after it was deleted, we're going to see that it contains null PTR, and we're not going to be using it. This is something cool, and it is really easy to implement these safety guidelines in your programs. Now that you know about this, we're going to go to Visual Studio Code and show you this in action. Okay, here we are in our working directory. The current project is dangling pointers. So we're going to grab our template files pretty quick and put that in our project. And we're going to open this in Visual Studio Code. We are going to look at the first case of a dangling pointer, and this is a pointer that is not initialized properly like P number here. If we try to dereference it, we're going to get something bad to happen. So let's see that, and let's go down and say that program is ending well. Just to know that we didn't get a crash, because a crash is basically going to terminate your program on the offending line. That's what it's going to do. So if the program works well and ends well, we're going to print this line here. Let's bring in GCC to build this program, and let's open a terminal so that we can run it. We're going to clear. The build was good, and we're going to run roster. You see that the program didn't end well. It crashed, and it crashed because we are trying to use uninitialized memory. When the operating system is going to try and run this thing, it's going to see, this guy is trying to modify memory that doesn't really belong to him. It is a road program. I am going to kill it, and it is going to be terminated on this line here. This is really bad. You should avoid these kinds of situations, so don't do this. We are going to comment this out and show you another offending thing we can do in our program, and that is using a deleted pointer. If you do that, you're going to get something bad in your programs. So here we have a small example. We have a pointer to int. We initialize this with a dynamic piece of memory, and we're going to store in a 67. And we can print this out. This is going to work pretty well. But we delete the memory down here, and we try to use it after we have deleted the memory. So the operating system is not going to be happy about this, because once the memory is deleted, it is no longer our memory, so we have no business dereferencing pointer 1 and trying to use that here. And we're going to get a crash, and this is something you should avoid. So let's try and build this and show you this in action. We are going to clear and run roster, and you're going to see that program is ending well, but in some cases it might crash. And hopefully this shows you the danger that these things might put you into. Sometimes your program is going to seem working fine, but sometimes when this memory that we are pointing to in P number 1 here is being used to do something really important by the operating system, you are going to get a crash. So you're not guaranteed to get the same behavior every time you run your program. Some of you might be saying, the program is working here, Daniel. Why are you making this such a big deal? Well, it is a big deal because you are not guaranteed to get the same results every time you run this program. So be sure you really avoid these kinds of situations. Let's try and clear and run the program again. Hopefully we're going to see it crash, but we're not. Okay, so let's clear and rebuild again. And see that we have better luck that time. Let's clear and run roster. It is going to end well, but you notice that we are trying to use a piece of memory that has already been deleted, and this is bad. Don't do this. Make sure you don't do something like this. We're going to comment this out again and show you another offending thing we can do with our programs. And bad things might happen if you try to have multiple pointers pointing to the same address, and that's what we have here. We have P number 3 and P number 4 here. P number 3 is allocating new space, and it is pointing to it. We have an 83 inside, and P number 4 is initialized with P number 3. We can do that. So these two pointers are basically pointing to the same memory location. Let's run this and show you that. We're going to comment out this delete statement here and run the program first to really prove that they are pointing to the same addresses and they contain the same values. Let's build and run. We're going to use GCC for that, and we're going to clear and run roster, and you see that P number 3, the address is this, and it contains an 83. P number 4 contains the same things. So let's see what happens if we try to delete using P number 3 and using P number 4 later to try and read stuff. This is what we are doing here. And we're going to see if the program actually gets to end well. We're going to build again. The build is going to be good. Let's bring this up and clear and run roster. And you're going to see that the program is also going to end well, but we are using a deleted piece of memory here, and anything can really happen. Okay, so you might get garbage, you might have really any piece of junk inside, or you might get a crash in some extreme cases. So this is really bad. Don't do it. Don't try to use a piece of memory that you have already deleted through a pointer. And these are problems you might run into in your programs if you try to use dynamic memory allocation. Let's look at how we can solve them. And the ultimate advice is to make sure you put a null PTR in a pointer if you don't know what that pointer is actually stored at. Okay, let's go down and look at solution 1. Solution 1 is to initialize your pointer to null pointer every time. If you don't have a value you can put in, use null PTR. That's what we are using here implicitly, but we can explicitly put that in because it is good. And before you use a pointer, you have to check and see if it doesn't contain null pointer. This is how we do it. If pointer 6 is different from null pointer, we're going to use it. If it is equal to null pointer, we're not going to use it, and we're going to be playing on the safe side, and you're going to see that the program is going to end well here. If we have a null PTR inside, we can say else here and say invalid address, okay? And the user is going to know that they are trying to do something really bad. So let's try and check against P number 5. So let's go and store a null pointer in P number 6 to really try this out and show you that we're going to get this warning if we're trying to use it. And we're going to build with GCC, and we're going to clear and run rooster. You're going to see that invalid address, and the program is going to end well. And if we try to put this statement somewhere where we're not checking against null pointer, we are going to get a crash. So let's comment this out so that it's clear what it is we are running here. So if we run this, we're going to get a crash. We have seen that, but let's show this again and really highlight that we are solving the problem here. If we run rooster, the program is going to crash because we are trying to use an initialized memory. But if we try and check against null PTR, like we are doing here, let's do that. We're going to be playing on the safe side because it's going to tell us invalid address, and we're not going to get a crash, and the program is going to end well. This is really cool. So let's try and do that again. We're going to build. The build is going to be good. We can clear and run rooster, and the program is going to end well. Okay, so if we have a value inside, we're going to get that. So let's put that n and say new int and put in an 87, for example. It doesn't really matter what we put in. So we're going to build again. The build is going to be good, and we can run rooster, and you see that we are getting our value here if we are not storing null PTR in P number 6. And you can do the same checks against P number 5, but I think this is really enough. So this is one way you can avoid dangling pointers. The next thing we're going to look at is if we are using a deleted pointer. And again, the solution is to set our pointer to null PTR after we delete it. Here we have P number 7. It has 82 inside. We are using it here and printing stuff out. We're going to delete it after we are done using it. And after that, the first thing we do is to reset it to null PTR. When we do that, other people or even ourselves have a chance to check it against null PTR, and we're going to know that it doesn't contain anything useful for our program. And if we do something like this, we're not going to run into all these weird problems, and our program is going to have consistent behavior across different runs, and this is really cool. So we're going to run this, we're going to get things printed out, and the program is going to end well because right now we are checking against null PTR. We can even be explicit in showing the warning here. We can say invalid memory access, and if you run this program, you're going to really know this. So let's finish this up, and we're going to build, and the build is going to be good. If we run this and run rooster, we're going to know that we are doing an invalid memory access after we have deleted the pointer, and this is going to save you from possible crashes that you might experience if you don't do this. So this deleted the pointer, and this is going to save you from possible crashes that you might experience if you don't do this. So this is a second solution you might want to possible crashes that you might experience if you don't do this. So this is a second solution you might want to implement in your programs, and I'm going to comment it out and show you how you can get away from the problem of when you have multiple pointers pointing to the same address. We are going to go down and put in the code. It is what you have seen in the slides, and it is really nothing new. So we have pointer 8 and pointer 9 here, and P number 8 here is pointing to dynamic memory, and the value inside is 382. P number 9 is initialized with whatever we have in P number 8, so they are going to be pointing to the same addresses here, but we have made P number 8 the master pointer. So it is the only pointer that is going to be able to delete this memory location, even if we have multiple pointers pointing to that. Okay, so every time we want to use this memory, we have the option to check against the master pointer and see that we have some valid data inside. If it is null pointer, we're not going to use that, and we're going to be playing on the safe side. And this is really what we are doing here. If we run this, we're going to see that the program is going to end well. The build is going to be good, and if we run rooster, we're going to see that we get things printed out. We're going to go through P number 8, we're going to print stuff. We're going to go through P number 9, we're going to print stuff. And if we try to use the pointer after the memory has been deleted, we're going to get a clear warning that we are trying to do something really bad. And this is really what you should aim for in your C++ programs that use dynamic memory allocation and pointers. This is really all we set out to do in this lecture. I hope you know how you can avoid these problems with dangling pointers. We are going to stop here in this lecture. In the next lecture, we're going to see what can happen if this new operator fails to give you the memory that you want to allocate on the heap. And that's possible. Go ahead and finish up here and meet me there. In this lecture, we're going to explore what